For centuries, humanity has looked up at the stars and pondered the vast, uncharted expanse of the universe. Now, with the help of groundbreaking technologies and revolutionary theories, scientists are embarking on a journey far beyond the boundaries of what we can currently observe. Today, we delve into the cutting-edge ideas that are pushing the limits of our understanding and reshaping how we perceive the cosmos. From the theory of cosmic inflation to the mind-boggling concept of the multiverse, we explore what could lie beyond the edges of our known universe. The scale of the universe is nothing short of staggering, stretching across approximately 93 billion light-years in diameter. Within this vastness, there are an estimated 2 trillion galaxies, each one filled with stars and planets, many of which we may never know exist. The sheer magnitude of this celestial expanse challenges every preconceived notion of scale and distance, pushing the limits of human comprehension. When scientists look at the overall shape of the universe, it appears to be flat. This conclusion is based on measurements of the cosmic microwave background radiation, the faint afterglow left behind by the Big Bang. Despite the universe's flatness, however, it is far from two-dimensional. Instead, it exists in three-dimensional space, bending and curving in ways that remain mysterious. Depending on the overall density of the universe and its rate of expansion, different models predict varying geometries. One of the most intriguing possibilities arises from the concept of curvature. If the universe is underdense, it could expand forever, eventually creating an open hyperbolic structure. On the other hand, if the universe is overdense, it might collapse back on itself, resulting in a closed spherical shape. Current evidence leans toward the universe having a critical density, suggesting that it is mostly flat with localized curvatures caused by galaxies and dark matter. This idea opens up a fascinating question. Is the universe truly infinite? While we can only observe a small fraction of the universe, there is a possibility that it extends far beyond the limits of our vision, into regions we may never access. Each point we observe could potentially be part of a much larger, unobservable continuum, stretching beyond our observational limits. This concept challenges the very nature of existence, prompting us to consider the true scope of reality and what may lie beyond our current understanding. The observable universe, defined as the area of space from which light has had time to reach us since the dawn of time, has a measurable boundary. The age of the universe is approximately 13.8 billion years, meaning that light from any object further than 13.8 billion light-years away has not had time to reach Earth. However, due to the expansion of space itself, the observable universe is much larger, with a radius of about 46 billion light-years. This means that while the universe itself is 13.8 billion years old, the expansion of space has allowed us to see light from distant regions that have traveled much farther than that original distance. This observable universe is often represented as a vast sphere, with Earth at the center, and its radius stretches out to 46 billion light-years. While we are able to study everything within this boundary, we must also acknowledge that there are regions beyond this edge that we will never be able to observe. These parts of the universe are receding from us faster than the speed of light, meaning that even over infinite time, their light will never reach us. This realization forces us to confront a profound truth. What we can observe is just a small fraction of what exists. The universe beyond our view may contain galaxies, clusters, and phenomena that are strikingly similar to what we can already see, but we will never know them directly. The implications of this are vast, as it suggests that the true structure of the universe extends far beyond the limits of our observation, perhaps in ways we cannot even begin to imagine. As we peer into the depths of space, we uncover not just the mysteries of distant stars and galaxies, but also the deeper truths of reality itself. The universe, in all its vastness and complexity, continues to challenge and inspire our imaginations, leaving us to wonder what else lies hidden in the boundless reaches of the cosmos. However, without direct observation, these regions remain speculative, inviting scientific inquiry and exploration into the unknown frontiers of existence. The cosmic microwave background, CMB, radiation is one such enigma, an ancient and faint glow that permeates the universe. This glow serves as a remnant of the Big Bang, providing us with a rare glimpse into the early days of the cosmos. The CMB is essentially the leftover thermal energy from the universe's hot and dense state that existed approximately 380,000 years after the initial explosion. At this pivotal moment, the universe had cooled sufficiently for protons and electrons to combine, forming neutral hydrogen atoms. This process allowed photons, particles of light, to travel freely through space, marking the release of light in what is known as the recombination era. As the universe expanded over billions of years, this radiation stretched and cooled, shifting into the microwave range of the electromagnetic spectrum. Today, this faint radiation is detected uniformly across the sky, creating a cosmic backdrop of near-uniform energy, with a temperature of about 2.7 degrees above absolute zero. This subtle but profound radiation, still present today, holds secrets of the universe's infancy, providing vital clues about its early conditions and evolution. Detailed measurements of this background radiation have unveiled fluctuations that represent the initial seeds of cosmic structure, early galaxies, stars, and clusters. The CMB not only illuminates the early universe, but also defines the limits of our observable universe. Since it originates from a time when the universe was just beginning to take shape, it marks the furthest point from which we can receive information, offering a snapshot of the universe's birth. The CMB serves as a cosmic map, providing context for the universe's evolution and revealing how it has changed over time. By studying the minute variations in temperature and density within the CMB, scientists can make precise measurements of the universe's age, composition, and expansion rate. These fluctuations offer valuable insights into the geometry of the universe and the distribution of matter, refining our understanding of the universe's boundaries. They also help map the vast structures that stretch beyond the limits of what we can see. Understanding the universe's boundaries has evolved dramatically over the past century. In the early 20th century, astronomer Edwin Hubble made groundbreaking discoveries that forever altered our perception of the cosmos. Hubble demonstrated that distant galaxies are moving away from us, leading to the realization that the universe is expanding. This discovery laid the foundation for the Big Bang theory, which suggests that the universe had a distinct beginning. As technology advanced, so did our ability to observe the universe. The development of radio telescopes, satellites, and space observatories has allowed scientists to probe deeper into space than ever before. In the mid-20th century, the detection of the CMB provided strong evidence for the Big Bang theory and gave us a direct view into the universe's early state. This milestone led to more refined estimates of the universe's age and the various forms of matter it contains, such as normal matter, and dark energy. In recent decades, cosmologists have further refined their understanding of the universe's boundaries through sophisticated models and simulations. These models incorporate data from cutting-edge telescopes, including the Hubble Space Telescope, which has greatly enhanced our knowledge of the expansion rate of the universe and the distribution of galaxies within it. Newer missions, like the Planck satellite, have delivered high-precision measurements of the CMB, enabling astronomers to make more accurate calculations of parameters like the density of ordinary matter and the influence of dark energy. Today, our understanding emphasizes that while the observable universe has a defined limit, the universe itself may be vastly larger or even infinite. As our observational tools continue to improve, so does the potential to answer some of the most fundamental questions about the nature of space, time, and the very boundaries of reality itself. The journey of discovery is ongoing, with each new piece of information reshaping our comprehension of the cosmos. A wide array of sophisticated tools and technologies are now employed to study the farthest reaches of the universe, enabling scientists to gather essential data on celestial phenomena. One of the most significant advancements in this endeavor has been the development of powerful telescopes, both ground-based and space-based. For instance, the Hubble Space Telescope, launched in 1990, has provided breathtaking images and crucial data about distant galaxies, nebulae, and exoplanets. Positioned above Earth's atmosphere, Hubble eliminates the distortion caused by air, delivering clearer, more accurate observations of the distant universe. As technology continues to evolve, so too will our understanding of the cosmos, bringing us ever closer to uncovering the ultimate secrets of space and time. One of the most revolutionary tools in modern cosmology is the use of radio telescopes, which allow us to detect the faint cosmic radio waves emitted by celestial objects scattered across the universe. Massive arrays such as the Very Large Array in New Mexico and the ambitious Square Kilometer Array, currently under construction, have made it possible for astronomers to peer deep into the cosmos at wavelengths that reveal hidden phenomena. Phenomena such as cosmic pulses, fluctuations in the cosmic microwave background, and the complex structure of galaxy clusters. These radio observations work in harmony with optical data, painting a richer, more complete picture of the universe. Space missions, too, have been indispensable in pushing the frontiers of our knowledge. Take, for example, the Planck satellite launched in 2009. With unparalleled precision, Planck mapped the cosmic microwave background radiation across the entire sky, offering profound insights into the universe's earliest moments. It allowed scientists to probe the conditions of the cosmos shortly after the Big Bang, shedding light on its expansion rate, its composition, and how matter and energy were distributed at the dawn of time. Similarly, the James Webb Space Telescope, a marvel of engineering, is set to revolutionize our understanding of the universe by exploring the infrared spectrum. This next-generation observatory is designed to capture information about stars and galaxies that formed just after the Big Bang, giving us a closer look at the birth of cosmic structures. But technological advancements go beyond hardware. Computational technologies have also become a cornerstone of modern astrophysics. Advanced simulations and algorithms now enable researchers to create detailed models of cosmic structures, predicting their behavior across vast periods of time. These simulations rely on immense datasets collected through groundbreaking observational tools, which allow scientists to test their theories, refine their predictions, and ultimately gain a deeper understanding of the universe's vast and intricate architecture. Together, these advancements in technology and methodology provide scientists with the means to explore the universe in ways never before imagined, pushing the boundaries of what we know and what we can discover. At the heart of our cosmic understanding lies the concept of cosmic expansion, the idea that the universe is continually stretching, with galaxies moving ever further apart. This phenomenon traces back to the early 20th century, when the pioneering astronomer Edwin Hubble made a groundbreaking discovery. Distant galaxies were redshifted, meaning the light from them had been stretched to longer wavelengths. This redshift signaled that these galaxies were moving away from us, a revelation that led to the inescapable conclusion: the universe itself is expanding. This expansion can be traced back to the Big Bang, the event that marks the birth of the universe. In the beginning, all matter and energy were crammed into an incredibly hot and dense point. As the universe expanded, it began to cool, creating the conditions necessary for the formation of atoms, stars, and galaxies. Understanding this expansion has been pivotal not just for mapping the universe's structure, but also for determining its age and predicting its future. The rate at which the universe is expanding is quantified by the Hubble constant, a critical value that measures how quickly galaxies are receding from one another relative to their distance. This constant is vital for understanding the universe's past, present, and future trajectory. But as we push our knowledge further, we also confront the limits of our observable universe. While we can observe a finite portion of the universe based on the light that has traveled to us since the Big Bang, cosmic expansion presents an intriguing challenge. Regions of space are expanding so rapidly that some galaxies are receding from us at speeds faster than light. This means that their light will never reach us, even over infinite timescales. As a result, the universe has a natural boundary, the cosmic horizon, beyond which we cannot observe. In essence, the universe is not only expanding in space, but also in knowledge. Every discovery brings us closer to understanding its vast, uncharted depths. Yet, as we stretch further into the cosmos, we must also accept that there are parts of the universe we will never see, reminding us of the infinite mysteries still awaiting discovery beyond the cosmic horizon. The expansion of the universe is not just a fascinating phenomenon, It's a key determinant of the universe's ultimate fate. The density and composition of matter and dark energy play crucial roles in this cosmic expansion. Depending on these factors, the universe may continue to stretch outward forever, spiraling toward a cold and dark future. Or, in a dramatic turn of events, it could slow down, eventually collapsing back in on itself in a cataclysmic event known as the Big Crunch. Understanding the expansion of the cosmos is essential, not only because it shapes our current observations, but because it profoundly influences our predictions about the universe's future and the very nature of existence itself. Yeah. As scientists delve deeper into these cosmic mysteries, they employ a variety of techniques to measure the rate of expansion. Each method, with its unique perspective, helps to form a clearer, more detailed picture of the dynamic forces at play. One of the most crucial tools astronomers use to measure the universe's expansion is the redshift of distant galaxies. When light from these galaxies stretches to longer wavelengths, shifting towards the red end of the spectrum, it indicates that the galaxies are moving away from us. This phenomenon, known as redshift, reveals the velocity at which galaxies are receding. By studying the degree of this redshift, astronomers can calculate how fast the universe is expanding and, in turn, estimate the Hubble constant, a value that quantifies the relationship between a galaxy's distance and its recession speed. But measuring distance isn't always straightforward. To obtain more accurate distance estimates, astronomers turn to a special class of objects known as standard candles. Among the most reliable of these are Type 1a supernovae, stellar explosions that, regardless of their location in the universe, reach a predictable peak brightness. By comparing the observed brightness of these supernovae with their intrinsic luminosity, scientists can pinpoint their distance from Earth. When these distance measurements are combined with redshift data, they create a more comprehensive understanding of the universe's expansion rate and the precise value of the Hubble constant. Another vital technique involves analyzing the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. The European Space Agency's Planck satellite, for example, carried out incredibly precise measurements of the CMB, detecting minute temperature fluctuations across the sky. These fluctuations, though subtle, contain invaluable clues about the early universe. They allow scientists to infer critical information about the cosmos's density and its overall geometry, shedding light on the universe's expansion and evolution. By studying the CMB, researchers can also obtain independent estimates of the Hubble constant. However, recent years have seen growing tensions between different methods of measurement. While observations from the CMB and nearby galaxies align in certain respects, discrepancies have emerged, suggesting that the expansion rate of the universe may not be as uniform as previously thought. These inconsistencies point to gaps in our understanding of cosmic expansion, gaps that, if filled, could reveal new groundbreaking insights into the nature and composition of the universe itself. This ongoing investigation into cosmic expansion is not just about resolving a mathematical conundrum. It's a quest that could reshape our understanding of the cosmos. As scientists continue refining their techniques and measurements, we are edging ever closer to unraveling the mysteries of our universe's past, present, and future. At the heart of this inquiry lies the theory of cosmic inflation, a concept that has transformed our understanding of the universe's early moments. Cosmic inflation proposes that just fractions of a second after the Big Bang, the universe underwent an extraordinary phase of rapid expansion. This period, lasting from about 10 to the power of minus 34 seconds to 10 to the power of minus 32 seconds after the Big Bang, saw the universe grow exponentially from subatomic scales to nearly the size of a galaxy in the blink of an eye. This dramatic inflation smoothed out any irregularities in the cosmos, creating a remarkably uniform state across vast distances. The idea of inflation arose to address some of the long-standing puzzles of the traditional Big Bang model. For instance, it explained why the universe appears so homogeneous on large scales, despite the presence of tiny fluctuations in matter. According to inflation theory, these superluminal, faster-than-light speeds stretched out any initial irregularities, smoothing the universe into a nearly uniform state. Additionally, inflation helped solve the flatness problem, the puzzling question of why the universe appears so geometrically flat on large scales. Beyond smoothing out the cosmos, inflation also provided a mechanism for the formation of the large-scale structures we observe today. The tiny quantum fluctuations present in the early universe were stretched to cosmic scales during this rapid expansion. Over time, these fluctuations grew into the clusters of galaxies we see scattered across the universe. These fluctuations have been detected in the cosmic microwave background radiation, providing solid evidence supporting the inflationary theory. Cosmic inflation has profound implications for our understanding of the universe's origins. It not only explains the initial conditions necessary for the Big Bang, but also suggests that our observable universe may be just a small, local part of a much larger, possibly infinite cosmic landscape. This opens up intriguing questions about what might lie beyond our observable universe and challenges us to explore the fundamental dynamics that govern the cosmos. As research continues, inflation remains a crucial framework for understanding the universe's evolution, shedding light on the mysteries of the early universe, its structure, and the forces that drive it forward. One of the most enigmatic forces influencing the expansion of the universe is dark energy. Discovered in the late 20th century, dark energy is believed to account for about 70% of the total energy content in the cosmos. Its existence was inferred from observations of distant supernovae, which appeared dimmer than expected. This dimming, in turn, indicated that the universe's expansion isn't slowing down, it's accelerating. Dark energy's role is still largely mysterious, but it has an undeniable impact on the trajectory of the universe. If it continues to exert its influence, it may lead to a future where galaxies drift farther and farther apart, eventually rendering the universe a cold, desolate place. However, the full extent of dark energy's nature and its long-term effects remain subjects of intense study and debate, with scientists working tirelessly to unravel its secrets. As the universe expands, the future of cosmic exploration holds exciting possibilities. Whether through understanding dark energy, refining inflationary models, or investigating the exact rate of expansion, each discovery brings us closer to comprehending the vast, complex forces that shape the universe. What we learn today could illuminate the mysteries of existence itself, offering us a deeper connection to the cosmos and our place within it. The mystery of dark energy, an elusive force driving the accelerating expansion of the universe, continues to captivate scientists and astronomers alike. One of the leading hypotheses to explain this phenomenon suggests that dark energy is a constant energy density that fills the vastness of space, exerting a repulsive gravitational force as the universe expands. This idea, often referred to as the cosmological constant, was first introduced by Albert Einstein in his equations of general relativity. In this theory, as the universe grows, the influence of dark energy intensifies, counteracting the gravitational pull that would otherwise slow the expansion. The result is an ever-accelerating universe, a scenario that complicates our understanding of the cosmos' ultimate fate. If dark energy continues to dominate, the universe could expand endlessly, leading to a chilling conclusion known as the Big Freeze. In this bleak outcome, galaxies would drift farther apart, stars would burn out, and the universe would become a dark, cold expanse, devoid of any active structures. But not all scientists are in agreement. Alternative theories suggest that dark energy might not remain constant. Instead, it could evolve over time, leading to different possible scenarios for the future of the universe. Some propose a dramatic collapse, while others envision a stabilization of the expansion. The true nature of dark energy remains one of the greatest unsolved mysteries in modern cosmology. Current research is focused on uncovering the fundamental properties of dark energy. Is it a static feature of space itself, or does it represent a more dynamic field? To answer this, astronomers rely on observations from an array of ongoing and upcoming projects, including extensive galaxy surveys and precise measurements of the cosmic microwave background radiation. These studies aim to shed light on how dark energy influences the evolution of the universe, offering crucial insights into its role in the grand cosmic story. A particularly fascinating possibility is the Big Rip theory, a hypothesis that envisions a catastrophic end for the universe. In this scenario, if the acceleration caused by dark energy continues to grow stronger, It could eventually overpower the gravitational forces holding together galaxies, stars, and even atoms. The result would be the disintegration of all cosmic structures, from the largest galaxies to the smallest atomic particles. The expansion of space would become so extreme that even the very fabric of space-time itself would be torn apart. Under the Big Rip scenario, galaxies would first drift apart at ever-increasing speeds. Gravitational forces that once bound galaxy clusters together would be undone, followed by the disintegration of solar systems, planets, and ultimately all forms of matter. In the final moments, even atoms would be torn asunder, leading to a completely fragmented universe. The timeline for such an event could span billions of years, depending on the nature of dark energy and how its density evolves over time. If the density of dark energy continues to increase, the Big Rip might eventually become inevitable. Conversely, if dark energy remains constant or decreases, this scenario may not unfold at all. The Big Rip is just one of several possible fates awaiting the universe, alongside others, such as continued expansion leading to the Big Freeze, or a potential collapse into a Big Crunch. Which of these outcomes will ultimately occur depends on the properties and behavior of dark energy, making current research into this force crucial for understanding the long-term future of our universe. As scientists delve deeper into the intricacies of cosmic expansion and the enigmatic nature of dark energy, they continue to refine their models, seeking to unravel the ultimate destiny of the cosmos. The idea of a multiverse is one that challenges our deepest conceptions about the nature of reality itself. It suggests that what we know as our universe might just be one of many, all existing simultaneously, each with its own distinct set of laws, constants, and even dimensions of space and time. This notion, rooted in a range of theories from cosmology and physics, stretches the boundaries of our understanding, urging us to reconsider everything we know about existence. At the heart of this idea lies the possibility that the universe we observe is not an isolated entity, but part of a vast, interconnected expanse where each universe can operate according to its own unique rules. From a scientific standpoint, the multiverse theory invites profound questions. What does it mean to exist in a universe governed by specific physical laws? What if those laws were not the same in another universe? Could they differ in ways that we can't even imagine? One of the most well-established multiverse theories comes from the concept of cosmic inflation. Shortly after the Big Bang, the universe is thought to have expanded at an extraordinary rate, a process known as inflation. According to this theory, the universe didn't just expand into a single uniform space. Instead, it created bubbles of space, each expanding at its own rate. These pockets of space, once they reach a certain size, become distinct universes in their own right, each potentially governed by a different set of physical laws. If this idea holds, it implies an infinitely vast collection of universes, each with its own properties, laws, and even dimensions of time. Similarly, quantum mechanics offers a fascinating contribution to the multiverse discussion through the many worlds interpretation. This theory proposes that all possible outcomes of any quantum event actually happen, but in separate branching universes. For instance, every time we make a decision, or when a quantum event occurs, an entirely new universe is born, where an alternative reality unfolds. This idea suggests that there is not just one reality, but an intricate web of parallel universes that together form an ever-expanding fabric of existence. The implications of the multiverse concept are nothing short of mind-boggling. If multiple universes exist, each with its own set of rules, it raises unsettling questions about the nature of existence. What does it mean for our universe to be the way it is? Are we merely one of countless variations governed by one particular set of laws among an infinite number of others? Could there be universes where the laws of physics differ dramatically, where the constants that define our existence are not even close to the ones we know? These questions push the boundaries of not only physics and cosmology, but also our philosophical understandings of life and existence itself. Despite the allure of the multiverse, it remains an idea that is difficult to test. As of now, there is no direct empirical evidence to support the existence of other universes. This lack of proof has led to intense debate within the scientific community. Is the multiverse truly a valid scientific theory, or is it a speculative hypothesis that, while fascinating, lacks the foundation necessary to be classified as part of science. As our tools for exploring the universe continue to improve and our understanding of physics deepens, the question of the multiverse remains one of the most tantalizing and unresolved mysteries in modern science. Several categories of multiverse theories have been proposed, each emerging from different branches of cosmology, quantum mechanics, and theoretical physics. The cosmic inflation multiverse, for example, offers a way of understanding the apparent uniformity of our own universe by suggesting that other universes could have formed during inflation, each possessing its own set of physical constants and laws. This theory not only provides a possible explanation for the characteristics we observe in our universe, but it also opens up the possibility of an infinite number of other universes, each with its own unique properties. In the end, the multiverse is not just a scientific theory, it's a window into the unknown. The exploration of this concept invites us to question everything we think we know about reality, offering a tantalizing glimpse into a potential future where our understanding of the cosmos is fundamentally transformed. While we may not yet have the means to verify the existence of other universes, the pursuit of this knowledge continues to push the boundaries of science, philosophy, and imagination. The many worlds interpretation, a concept from quantum mechanics, offers a fascinating and mind-bending perspective on reality. It suggests that every quantum event, one where multiple possible outcomes exist, gives rise to the creation of a new, branching universe for each possible outcome. In this view, all potential realities coexist in parallel, with every choice, event, or measurement resulting in the birth of a new universe, each one reflecting a different outcome of a quantum decision. Imagine a vast, ever-expanding landscape where every possible version of reality plays out simultaneously, creating an enormous tapestry of alternate worlds, each with its own history, choices, and consequences. Another prominent multiverse theory takes root in string theory, particularly through the framework known as the landscape multiverse. String theory proposes that our universe is just one of many that exist in a complex and multidimensional cosmos. According to this model, multiple dimensions and configurations of matter arise from the unique ways extra dimensions are compactified. Each distinct configuration can give rise to a separate universe, each governed by its own set of physical laws, constants, and forces. The landscape multiverse paints a picture of a nearly infinite number of universes, each with its own rules and structure, created by the different ways that these extra-dimensional forces play out. Equally intriguing is the concept of the ultimate multiverse, which suggests that every mathematically possible universe exists. This theory emerges from the idea that if mathematical structures exist independently of our universe, then any conceivable universe, bound by consistent mathematical laws, could also be real. According to this view, every logical configuration that adheres to mathematical principles could manifest as its own distinct universe. From this perspective, the cosmos isn't just the universe we know. It's a boundless realm where all possible universes are birthed from the endless variations in mathematical consistency. While each of these theories provides a different perspective on the nature of reality, they share a common theme: the possibility of multiple universes. These ideas offer potential solutions to many of the deepest questions in physics and cosmology, especially in understanding the fundamental nature of our existence. However, the absence of direct empirical evidence remains a major obstacle. Still, ongoing research continues to explore these theories, working to understand their viability and implications for how we perceive the cosmos. A different approach to the multiverse emerges from the bubble universe theory, which links the existence of multiple universes to the theory of cosmic inflation, a rapid, exponential expansion that occurred just after the Big Bang. According to this theory, the early universe underwent a phase of inflation where different regions of space expanded at varying rates. This uneven expansion gave rise to bubbles, each representing a separate universe. These bubbles developed independently, each following its own unique path with distinct physical laws, constants, and conditions. The result is a multiverse where different regions of space evolve independently, creating an ever-growing network of self-contained universes, each one potentially governed by its own set of rules. One of the strengths of the bubble universe theory is that it offers solutions to several cosmological questions. For example, it explains why our universe appears homogeneous and isotropic on large scales, despite containing structures like galaxies and galaxy clusters. The theory suggests that the rapid inflationary phase of the early universe would have smoothed out any irregularities, leading to the uniformity we observe today. It also helps explain why the constants of nature in our universe have the particular values they do, as each bubble could have different values arising from its own unique inflationary dynamics. Moreover, the theory suggests that there may be an infinite number of such bubbles, each containing life, matter, or even entirely different sets of physical laws. This provides a rich framework for understanding the vast diversity of potential realities that might exist, not just in our universe, but throughout the broader cosmos. At its core, the bubble universe theory offers a compelling model for explaining the diversity of potential universes, providing a wider context in which to explore the fundamental nature of space, time, and existence. It invites us to consider a cosmic structure far grander and more complex than we've ever imagined, reshaping our understanding of reality itself. Lastly, the many worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett III in the mid-20th century, offers another lens through which to view the multiverse. In conventional quantum mechanics, particles exist in a superposition of states, meaning they can simultaneously occupy multiple possibilities until an observation is made. However, in the many worlds interpretation, Everett suggests that all possible outcomes of a quantum event actually occur, each in its own distinct branching universe. Rather than collapsing into one reality upon measurement, the universe splits, creating an endless number of parallel realities, each corresponding to a different potential outcome. This interpretation challenges the traditional view of a single linear timeline, replacing it with a far more complex and interconnected view of the cosmos, where every possibility manifests in its own universe. However, the many worlds interpretation of quantum mechanics suggests that rather than collapsing into a single outcome, every possibility is realized, giving birth to distinct, non-communicating branches of reality. To better understand this, imagine a simple quantum experiment where a particle can either spin up or spin down. According to the many worlds interpretation, when the particle is measured, the universe splits into two distinct realities. In one universe, the particle is found to be spinning up, while in a parallel universe, it is spinning down. This branching process continues for every quantum event, creating an infinitely complex web of parallel realities. Therefore, each decision or measurement leads to the creation of a new universe, allowing every possible outcome to manifest. This interpretation has deep connections with multiverse theories, suggesting the existence of countless universes that coexist with one another. In the many worlds framework, each universe reflects a different sequence of events, outcomes, and choices. It aligns closely with concepts like the bubble universe theory, which proposes that each bubble can act as a separate universe. These bubbles emerge not through quantum branching, but under different conditions, each one holding unique physical properties and laws. In this sense, the many worlds interpretation enriches our understanding of multiverse theory, offering elegant solutions to some of quantum mechanics' most confounding paradoxes, such as the observer effect and wave function collapse. Yet, the theory remains a topic of heated debate among physicists. Critics argue that it lacks direct empirical evidence and raises profound questions about the nature of measurement and reality itself. Despite this, the many worlds interpretation continues to fuel philosophical discussions about existence and the nature of the universe, pushing for a deeper exploration of both quantum mechanics and cosmology. String theory and M-theory provide a fascinating extension to this conversation, offering a framework that further implies the existence of multiple universes. String theory proposes that the fundamental building blocks of reality are not point-like particles, but rather tiny, vibrating strings. These strings can oscillate in various ways, which results in the wide range of physical phenomena and particle types that we observe. This model naturally supports the idea of a multiverse because the different vibrational patterns of the strings correspond to different physical laws and constants, potentially giving rise to entirely separate universes. M-theory builds on string theory by suggesting that these strings exist in higher dimensions. While string theory operates in 10 dimensions, M-theory proposes an 11th dimension, a dimension that allows for even more intricate structures and interactions. Among these structures are brains, multidimensional objects that can potentially house entire universes. Each brain could support its own distinct universe, each with its own set of physical laws, reinforcing the multiverse hypothesis. One of the most striking implications of string theory and M-theory is the landscape of possible universes. The mathematics underlying these theories suggest a vast array of disconnected universes, known as the landscape. These universes emerge from the different ways in which strings can compactify or curl up in the extra dimensions. The diversity of these compactification patterns gives rise to a multitude of possible conditions, allowing for the creation of entirely different physical realities. Different energy states in these higher dimensions lead to different laws of physics, meaning that each unique configuration could correspond to a separate universe. While these theories remain unproven and are still the subject of active research, their implications are profound. The landscape of string theory and M-theory challenges our traditional understanding of existence, opening up new possibilities for how universes might interact or exist entirely independently of each other. This radically redefines our conception of space-time and reality itself, pushing us to reconsider the very essence of the cosmos. An intriguing aspect of string theory and M-theory is the concept of brain cosmology, which examines the role of brains in the structure of the universe. In this context, our familiar universe can be thought of as a three-dimensional brain that exists within a higher dimensional space. Just as a sheet of paper exists within the three-dimensional confines of a room, a brain can exist within higher dimensions that are beyond our current perception. The most fascinating implication of brain cosmology is the possibility that numerous other brains exist in this higher dimensional space, each potentially housing its own universe with distinct physical laws. These brains can drift through the larger, higher dimensional space, meaning that different regions of this vast realm could harbor entirely separate universes. These universes could have varying constants of nature, alternative forms of matter, and even entirely different physical laws. In this scenario, the idea of brain collisions presents a captivating explanation for cosmic events like the Big Bang. When two brains come into close proximity, their interaction can result in a massive release of energy, giving birth to a new universe. This model suggests that the Big Bang was not an isolated event, but rather one in a series of recurring cosmic collisions. The process of brain collisions could be cyclical, each event leading to the creation of new universes in a cosmic rhythm that stretches across dimensions and time. This idea of a cyclical multiverse, with universes constantly being born from the collisions of brains, adds a fascinating layer to our understanding of both the origins of our universe and the larger structure of reality itself. It is a reminder that within the framework of string theory and M-theory, the universe we inhabit may be just one of countless others, each emerging from the fundamental principles that govern the very fabric of space and time. In the vast, ever-expanding cosmos, the dynamics of the brain cosmology theory suggest the possibility of a complex, interconnected multiverse. Imagine a vast network of universes, each distinct, yet connected through their origins and evolutionary paths. These universes are not static, but ever-evolving, with the potential for them to branch off from one another as they move through the higher dimensional space. Picture this: as brains, three-dimensional entities existing within a higher dimensional space, ebb and flow, they create diverse cosmic structures, each universe developing its own unique laws and physical characteristics. This interplay leads to the formation of an intricate tapestry of realities, where every universe has its own distinct journey through time and space. This framework offers a profound shift in our understanding of existence, one that stretches beyond the limits of our own universe and into an expansive multiverse, teeming with a multitude of parallel and divergent realities. Each of these universes could experience its own version of evolution, perhaps with varying degrees of complexity, life, and physical laws, vastly different from what we know. And within this framework, the very concept of reality expands. What we perceive as our single three-dimensional universe might only be a narrow slice of an immensely broader and more complex cosmic structure. At the heart of brain theory lies the concept of extra dimensions. These additional dimensions beyond the three spatial dimensions we experience daily enrich the idea of parallel universes. In this view, our universe is imagined not as an isolated entity, but as a three-dimensional brain, short for membrane, embedded in a higher dimensional space. This higher dimensional space could harbor an array of other brains, each one hosting its own universe, complete with its own physical constants, forces, and particles. The relationship between these extra dimensions and parallel universes is fundamental to understanding the diversity of realities that might exist. Each brain, each universe, can be considered as existing within this higher dimensional space, interacting with others in ways that are shaped by the arrangement of these brains. Some brains could be located close together in higher dimensional space, making interactions between them possible, while others may be separated by vast expanses, leaving them isolated from one another. In this cosmic dance, the positioning and movement of brains within higher dimensional space give rise to the potential for the formation of new universes. The way a brain is shaped, or how it interacts with nearby brains, could lead to entirely different cosmic realities, with varying laws of physics or even fundamental constants. A slight shift in the configuration of a brain could be enough to create a new universe altogether, each with its own unique set of circumstances. This, in turn, leads to the possibility of divergent realities, universes that are fundamentally different from one another, yet share a common origin in the higher dimensional space. The vastness of this framework is staggering. It suggests a multiverse that is far more intricate than we might ever have imagined, where the dynamics of higher dimensions and the arrangement of brains can lead to an infinite variety of possibilities. With each new configuration of a brain, a new universe could be born, and with it, an entirely new reality. The implications are mind-boggling. Countless, perhaps infinite, parallel universes, each one with its own set of rules and characteristics waiting to be discovered. Now, consider the ekpyrotic universe model, an alternative theory that challenges the traditional Big Bang view. Rather than proposing a singular, explosive beginning to the universe, the ekpyrotic models suggest that the cosmos has always existed in a cyclical fashion. According to this theory, our universe did not arise from a singular point in time, but from the collision of two three-dimensional brains within a higher dimensional space. This collision triggered a release of energy, which led to the formation of new cosmic structures, much like the Big Bang theory suggests, but with one major difference. The universe in this model undergoes a cyclical process of creation and destruction, with new epochs of expansion followed by contractions over an infinite timescale. In this vision, the universe doesn't have a single beginning, but has experienced countless cycles, each one marked by a collision of brains, giving rise to a new Big Bang with each event. This cyclical process ensures that the universe continues to evolve, with new eras of expansion and contraction emerging endlessly. And because of this, the universe is not simply a one-time event, but a timeless cycle of cosmic rebirth. The implications of the ekpyrotic model extend to our understanding of the large-scale structure of the universe. While the Big Bang theory explains the uniformity of the cosmos, such as the distribution of galaxies and the cosmic microwave background radiation, through the rapid expansion of the early universe, inflation, the ekpyrotic model attributes these features to the dynamics of colliding brains. The interactions of these brains, rather than an inflationary phase, can account for the consistent cosmic background and the homogeneous distribution of matter across the universe. As we explore this idea further, we begin to see a rich and complex picture of the cosmos unfold. One where the universe is not a static, one-time event, but a dynamic, cyclical entity, shaped by the ebb and flow of higher dimensional brains. And within this grand cosmic framework, the potential for countless other universes, each with its own unique history and laws, becomes a tantalizing possibility. In the end, the multiverse, whether envisioned through the lens of brain cosmology or the enigmatic model, invites us to look beyond the limitations of our own universe, expanding our understanding of existence and opening our minds to the infinite possibilities that lie within the higher dimensional space. The journey to explore these cosmic horizons is only just beginning, and as we continue to delve into the mysteries of the cosmos, we may soon discover that our universe is only one of many, each contributing to the grand, intricate tapestry of the multiverse. The erotic model offers a transformative framework that goes beyond the confines of traditional cosmology, providing a new lens to explore the very nature of the space-time continuum. By weaving together principles from string theory and the concept of higher dimensional spaces, it introduces ideas that the Big Bang Theory alone cannot encompass. The erotic model reshapes our understanding of the universe, not as the aftermath of a singular event, but as part of an endless cycle of cosmic rebirths. Through this innovative perspective, the universe is seen as more than a consequence of an isolated beginning. Instead, it is a continuous evolution, marked by the dynamic interactions of higher dimensional objects known as brains. These collisions between brains are central to the creation of new universes. In the context of brain cosmology, when two three-dimensional brains from a higher dimensional space come close to one another, they trigger an energetic interaction akin to the collision of two massive celestial bodies. This interaction is so powerful that it releases an enormous amount of energy, similar to what we understand as the Big Bang. But here's where the erotic model offers a profound revelation. It's not just one Big Bang, but a sequence of cosmic births occurring through repeated collisions. The energy from the collision of brains inflates regions of space and catalyzes the creation of the fundamental particles and forces that define a new universe. This is where reality takes shape. The collision acts as the spark for a universe's genesis, igniting the process that will shape its laws of physics and evolution. Each brain collision is the genesis of a distinct universe, each possessing its own unique set of physical properties, including the nature of matter, energy, and fundamental forces. The differences in these universes depend on the characteristics of the brains involved, such as their energy levels and the configuration of their higher dimensional interactions. Thus, the conditions of each collision lead to a breathtaking diversity of universes, each with the potential for distinct types of matter, different forces, and varied laws of physics. Furthermore, this model propels us toward a cyclical view of cosmic existence. As brains continue their cosmic dance, new universes are born from their periodic collisions. This idea challenges the notion of a singular, one-time creation event, and opens up the possibility that the universe we know today is just one of an ongoing series of cosmic generations, each stemming from similar interactions across vast stretches of cosmic time. This dynamic multiverse is constantly evolving, with the birth of new realities happening over and over again. It reimagines the cosmos not as a fixed entity, but as a living, breathing cycle of continuous creation. What we experience as our universe may merely be a fleeting chapter in this vast cosmic narrative, one of countless others formed through these energetic encounters between brains. However, while this model paints a compelling picture of a universe in perpetual transformation, the observational evidence for brain cosmology is still largely theoretical. Due to the complexity and scale of these concepts, they remain challenging to verify with current technologies and methodologies. Despite this, the erotic model opens new doors to understanding the deepest structures of reality, pushing the boundaries of science and asking us to reconsider the fundamental nature of existence itself. However, certain remarkable features of the universe revealed through ongoing cosmological studies present fascinating clues that may support the idea of brain cosmology and related theories. One of the most intriguing areas of exploration centers on the cosmic microwave background, CMB radiation. This radiation is a leftover signature from the hot, dense state of the early universe, acting as a time capsule of the cosmos' origins. The fluctuations and patterns within this radiation help scientists unravel the history of the universe's formation and evolution. While the standard model of cosmology, driven by the inflationary theory, adequately explains these observations, a subset of researchers proposes an exciting possibility. They argue that the unique signatures stemming from interactions between brains, multidimensional objects in string theory, could leave their mark on the cosmic microwave background. Such signatures might manifest as distinct variations in temperature or polarization, potentially offering insight into the dynamics of brain interactions, including the possibility of brain collisions. The hypothesis suggests that these subtle patterns might be embedded within the radiation, hidden in plain sight. Equally compelling is the question of large-scale structures in the universe, galaxies and galaxy clusters. According to brain cosmology, the distribution and formation of these structures could be fundamentally altered by the interplay of higher dimensional brains. In essence, the unique properties of these multidimensional entities might influence the way matter clusters across vast expanses of space. Recent surveys mapping the universe's distribution of matter hold the potential to offer clues about whether the observable universe's structure aligns with predictions made by brain cosmology. This points to the need for more detailed analysis, with the possibility that forthcoming models could match empirical data in unexpected ways. Gravitational waves, another frontier of cosmological research, may also provide crucial evidence for brain cosmology. When brains collide, they could create ripples in spacetime, detectable as gravitational waves. If scientists can pinpoint patterns within these wave emissions that correlate with the theoretical collisions of brains, it could validate aspects of this theory. Though brain cosmology currently lacks solid observational proof, advances in both technology and survey methods may one day provide clearer evidence. The exploration of the universe's intricate structure continues to challenge our understanding and ignite new theories, emphasizing the evolving nature of cosmological inquiry. As scientists peer deeper into the cosmos, the faintest signs of brain interactions may eventually come into sharper focus, reshaping how we comprehend the very fabric of reality itself. Quantum fluctuations, too, are critical in understanding the universe's creation. These transient changes in energy occur on the smallest scales of space and time, driven by the principles of quantum mechanics. Even in what seems like a vacuum, these fluctuations suggest that empty space is anything but empty. Instead, it teems with virtual particles that appear and vanish, constantly reshaping the quantum landscape. In the context of the universe's birth, quantum fluctuations are vital. They play a central role in the inflationary model, which describes the rapid exponential expansion of the universe in its earliest moments. During this phase, the universe grew at an astonishing rate, stretching quantum fluctuations to enormous scales. These energy density variations gave rise to regions of the universe that expanded at different rates, eventually leading to the formation of the galaxies and clusters of galaxies we observe today. Interestingly, some theoretical models suggest that quantum fluctuations may be capable of creating entirely new universes. In a multiverse scenario, a fluctuation might trigger the birth of a separate region of space with distinct properties, an entirely new universe. Each universe would be shaped by its own unique quantum fluctuations, governed by different constants and laws. In this vision, a vast array of universes could emerge, each a reflection of the specific energy configuration that sparked its creation. This idea envisions a multiverse, a cosmic sea of universes, each with its own dynamic qualities, arising from the intricate dance of quantum uncertainty. The concept of a constantly fluctuating quantum vacuum could be key to understanding not only the quantum mechanics of space, but also the dynamics of the human brain in a higher dimensional context. When brains move within these higher dimensional realms, they might interact with the quantum fluctuations present in those spaces, opening the possibility for new and extraordinary events, such as the creation of new universes or influencing the outcomes of brain collisions. This complex interaction highlights the profound ways in which quantum mechanics and cosmic creation are intertwined. The universe, far from being a static entity, may instead be a living, breathing network, deeply embedded in the fluctuating, ever-changing fabric of reality at the quantum level. At the heart of this fluctuating reality is the concept of vacuum energy, a compelling principle born out of quantum field theory. Even in the emptiest stretches of space, vacuum energy suggests that there is no true emptiness. Rather, a residual energy permeates all of space, a byproduct of quantum fluctuations where virtual particles pop in and out of existence. This seemingly elusive phenomenon raises fascinating questions about the very nature of space. While we often think of empty space as a void, quantum field theory tells us that this emptiness is full of life at the smallest scales. In cosmological terms, vacuum energy is associated with dark energy, the mysterious force accelerating the expansion of our universe. This energy creates a repulsive gravitational effect, pushing galaxies apart and shaping the larger evolution of the cosmos. As scientists explore vacuum energy's impact on our own universe, they are led to ponder whether similar conditions could exist beyond the observable realm. If vacuum energy is a fundamental characteristic of all space-time, its influence could extend far beyond our universe, shaping the very structure and behavior of space outside our cosmic bubble. This thought leads us into the realm of the multiverse. If vacuum energy varies across different regions of space-time, it could give rise to multiple distinct universes, each with its own set of properties, particle types, and fundamental forces. Each universe in this multiverse could be the result of different vacuum energy conditions, creating an expansive, interconnected landscape of realities. The diversity of such universes might range from the familiar to the bizarre, with each reality shaped by its own unique quantum fluctuations. Moreover, vacuum energy may also provide a framework for the emergence of bubble universes. These regions of space could undergo phase transitions triggered by intense energy fluctuations. As these fluctuations rise to critical levels, they could lead to a rapid inflationary expansion, similar to a Big Bang event, creating a new universe completely distinct from its surrounding space. This scenario hints at dynamic forces at play in higher dimensional spaces, where the properties of vacuum energy could be the catalyst for the birth of entirely new cosmic environments. As research continues to unveil the mysteries of vacuum energy, it deepens our understanding of the cosmos in ways we have only begun to comprehend. This exploration goes beyond the confines of our own universe, offering a broader, more intricate perspective on existence. The pervasive presence of vacuum energy suggests a complex and interwoven tapestry of universes, each one shaped by the inherent fluctuations of this invisible force. Equally captivating is the concept of quantum foam, a central idea in quantum gravity. At minuscule scales, far smaller than we can perceive, space-time is anything but smooth and continuous. Instead, it is a chaotic, turbulent sea of fluctuating energy fields and virtual particles, a phenomenon that challenges our classical understanding of the universe. Quantum foam reflects the inherent uncertainty that lies at the heart of quantum mechanics, where our familiar notions of space, distance, and time begin to break down, revealing a fundamentally dynamic structure beneath the apparent calm of the universe. The implications of quantum foam are profound. It suggests that the very vacuum of space is not empty at all, but is a vibrant, energetic medium capable of influencing the fabric of reality itself. These constant fluctuations may not only affect the large-scale evolution of cosmic structures, but could also play a crucial role in the creation of new universes. As quantum foam bubbles and churns, certain regions of space might undergo intense fluctuations, potentially triggering high-energy events that lead to the formation of new cosmic realms. When these fluctuations reach a critical threshold, they could initiate a rapid expansion, akin to the Big Bang, sparking the birth of a new universe. This idea resonates with certain cosmological theories that posit quantum processes as integral to the genesis of universes. It suggests that the universe we inhabit, and perhaps others beyond it, may have emerged from the very quantum fluctuations that define the nature of space-time itself. The universe, then, could be part of an eternal cycle of creation, destruction, and rebirth, driven by the fundamental forces that underlie quantum reality. The very fabric of the cosmos is alive, in constant motion, shaped by the unseen forces of quantum mechanics. Quantum foam might just hold the key to understanding a multitude of phenomena in the universe, including the tantalizing concept of a multiverse. Imagine a sea of fluctuating energy, an unpredictable backdrop where regions of quantum foam experience differing configurations, with each fluctuation potentially giving rise to distinct pockets of space-time. These fluctuations could theoretically birth entire universes, each governed by its own unique laws of physics, creating a rich and varied landscape of existence. By exploring quantum foam, scientists are being pushed to rethink not only the dynamics of cosmic creation, but the very essence of reality itself. How can the behavior of minuscule quantum fluctuations cascade into massive cosmic events? How do these unseen, chaotic phenomena impact the birth and nature of the universe? Delving into quantum foam provides profound insights into the origins of the universe, that offering a potential window into an infinite array of universes, each born from the fundamental building blocks of spacetime. But unraveling this mystery is no small feat. Studying quantum fluctuations in the lab is a monumental challenge that demands the use of advanced techniques and precision measurement. These phenomena, elusive by nature, require methods borrowed from multiple scientific disciplines, including high-energy physics, quantum optics, and condensed matter physics. One of the most remarkable approaches to studying these phenomena involves laser-based technologies that manipulate and detect quantum states. For instance, experiments with ultra-cold atoms trapped in optical lattices offer a unique opportunity to observe quantum fluctuations in action. When atoms are cooled to nearly absolute zero, they defy classical physics and reveal quantum behavior, exhibiting fluctuations in their position and momentum. This setup allows researchers to study how these fluctuations contribute to phenomena such as superfluidity and quantum coherence, opening up new dimensions in our understanding of the quantum world. On a larger scale, high-energy particle colliders, such as the Large Hadron Collider, LHC, provide an even more extreme testing ground. These machines accelerate particles to speeds approaching that of light, creating conditions in which quantum effects become observable. By analyzing the results of particle collisions at these high energies, scientists can indirectly observe quantum fluctuations and trace their influence on fundamental particles. Such research has already led to monumental discoveries like the confirmation of the Higgs boson and the ongoing exploration of supersymmetry, both of which are central to quantum field theories. Quantum fluctuations also play a pivotal role in more nuanced phenomena, such as the Casimir effect. This strange yet fascinating phenomenon arises when vacuum fluctuations between two closely spaced conductive plates lead to an attractive force between them. The precision with which scientists measure this force allows them to explore the nature of vacuum energy, offering insights into the very structure of spacetime itself. The implications of studying quantum fluctuations extend far beyond our current understanding of physics. These investigations are not just testing the limits of existing theories, they're reshaping our perceptions of reality. The interplay between vacuum fluctuations and the fundamental forces that govern the cosmos has led to breakthroughs in technology, such as quantum computing and quantum cryptography. As techniques evolve, our ability to explore the quantum world continues to expand, unlocking mysteries of both the micro and macro realms. At the heart of these quantum phenomena lies a concept known as the zero-point energy, ZPE, the lowest possible energy state of a quantum system. Even when temperatures drop to absolute zero, particles retain a residual energy due to the nature of quantum mechanics, proving that vacuums are never truly empty. This zero-point energy permeates all of space, providing a constant backdrop for all physical processes. It's a field of continuous fluctuations where particles and fields spontaneously emerge and vanish. Understanding the zero-point energy field could have profound implications not just for our observable universe, but for the very expanse beyond it. This omnipresent energy, which acts as a backdrop to all physical phenomena, might be the key to unlocking further mysteries of the cosmos. If zero-point energy is indeed a fundamental feature of the universe, it could serve as the mechanism for the creation of new pockets of spacetime in regions beyond our detection. In these hidden realms, different configurations of zero-point energy could give rise to universes with entirely different physical properties, governed by unique sets of laws and constants. This suggests the possibility of a multiverse, an infinite number of universes, each birthed from fluctuations in the zero-point energy, operating under their own distinct rules. In this speculative landscape, each universe could follow its own trajectory, shaped by the underlying energy fluctuations that determine everything from the strength of gravitational forces to the nature of time itself. Could the zero-point energy be the bridge between the known and the unknown, between the universe we inhabit and the many others that might exist beyond the veil of our perception? In the end, exploring the mysteries of quantum foam and zero-point energy not only challenges the foundations of current scientific understanding, but also opens up tantalizing possibilities for the future. As technology advances, our ability to probe these elusive realms will only grow, bringing us closer to a new understanding of the universe, and perhaps revealing the existence of infinite others. Moreover, the zero-point energy field may hold the key to understanding the early universe and the rapid expansion known as cosmic inflation. This energy, tied to the fundamental nature of space itself, could have played a pivotal role in the moments right after the Big Bang, driving an incredibly fast and vast expansion. If this energy field extends beyond the limits of our observable universe, it could continue to shape regions of the cosmos that lie beyond our detection. These distant areas might harbor unique structures, possibly even their own universes, sculpted by the same universal principles that govern our own reality. The implications of zero-point energy stretch beyond mere scientific curiosity. Delving deeper into this mysterious field forces scientists to challenge our fundamental understanding of time, space, and reality itself. It sparks profound questions about the interconnectedness of everything, about how all things in the universe might be tied together by a single underlying force. In doing so, it opens the door to the possibility of a vast, intricate multiverse, an ever-expanding network of realities, sustained and interconnected by the very energy that pulses through the cosmos. At the same time, another layer of cosmic mystery lies in the study of cosmic topology. This field of research explores the large-scale structure and geometry of the universe, aiming to understand how the overall shape and configuration of space itself influence cosmic phenomena. Cosmic topology isn't just about how the universe bends or curves. It also examines how different parts of the universe connect, or don't, across higher dimensional spaces. The geometry of the universe, in essence, shapes everything, from the paths that light takes across the cosmos to the fate of the universe itself. At its core, the shape of the universe remains one of the most fundamental questions in cosmology. It's influenced by general relativity and the way matter and energy are distributed throughout space. For centuries, scientists have categorized the universe into three basic shapes: flat, closed, or open, each defined by the curvature of space itself. These distinctions are far more than theoretical curiosities. They influence the very fate of the universe. For instance, a flat universe, one where the geometry is perfectly balanced, would continue expanding forever at a constant rate. A closed universe, however, might eventually reach a critical point and collapse back in on itself, pulling all of space into a final singularity. This geometric understanding of the universe is key to grasping not just its origins, but its future. As our exploration into the vastness of space continues, the answers to these questions could reveal a much richer, more complex reality than we have ever imagined, one that stretches far beyond the confines of what we can currently observe. However, cosmic topology takes this idea one step further, delving into the fascinating possibility that the universe might fold or wrap upon itself, forming a far more complex structure than we typically imagine. It introduces the idea that the universe could possess a shape much more intricate, shapes like a torus or even higher dimensional manifolds. This concept, in its simplest visual form, suggests that if you could travel long enough in a straight line in one direction, you might end up right back where you started, just like journeying across the surface of a donut. The implications of cosmic topology are profound. By exploring these ideas, we can gain a deeper understanding of the universe and how we might observe distant galaxies or cosmic phenomena such as the cosmic microwave background radiation. Topological models hint that the shape of the universe could give rise to certain patterns or irregularities, which scientists could potentially measure and analyze. This could provide the key to unlocking the universe's true structure, guiding our understanding of its origins, evolution, and the very forces that govern it. To probe these cosmic questions, researchers are employing sophisticated mathematical models, data from large cosmic surveys, and measurements of gravitational waves. Each new insight from these studies adds a crucial piece to the puzzle, gradually reshaping our understanding of cosmic evolution and the interactions that occur on a grand scale. Cosmic topology not only illuminates the vastness of the universe, but also invites profound questions about the fundamental nature of existence, including the very fabric of space-time itself. The shapes that arise from cosmic topology are not just theoretical curiosities. They reflect the hidden structure of the universe, far beyond the simple models of flat, open, or closed spaces as defined by general relativity. Some of the more intriguing and mind-bending geometric forms proposed include the torus and the Mobius strip. These shapes bring a fresh perspective on the cosmos and have the potential to reshape our understanding of everything from the distribution of galaxies to the distribution of cosmic radiation. The torus, resembling the shape of a donut, is one of the most captivating models for the universe. In this configuration, space itself is connected in a way that traveling far enough in one direction would eventually bring you back to your starting point. In such a model, the universe would seem finite, without edges or boundaries, despite its vastness. It's a fascinating concept because it suggests that even in an infinite universe, observers who start from the same point and move in the same direction could eventually meet again, completing a cosmic loop. This idea carries profound implications for understanding the distribution of galaxies, as well as the cosmic microwave background radiation. It proposes that certain recurring patterns might emerge because of the space's connectivity. The Mobius strip, another mind-expanding idea in cosmic topology, offers a completely different twist, literally. It's a surface with only one side and one edge. To create it, you take a strip of material, give it a half twist, and then join the ends together. Now imagine the universe taking the shape of a Mobius strip. The result would be a universe that allows for unconventional paths through space-time, where an observer could seemingly return to their original point after a journey, but with a twist, literally. Such a universe could flip the observer's entire perspective, causing them to view space from an entirely different angle. This raises intriguing questions about the orientation of cosmic structures and the potential for strange, anomalous phenomena to occur within it. But the ideas don't stop there. More complex shapes for the universe have been proposed, such as the Klein bottle, a structure that's even more intricate and non-orientable, as well as higher dimensional analogs like Calabi-Yau manifolds from string theory. These shapes each present unique challenges to our understanding, but they also open doors to new ways of thinking about cosmic dynamics. They offer fresh opportunities to model the universe, pushing the boundaries of how we perceive its interconnectedness, history, and evolution. By exploring these diverse topologies, scientists are pushing the limits of our understanding, expanding beyond conventional frameworks. This not only helps answer age-old questions about the fate of the universe, but it also provides the potential to reveal the deeper, underlying principles that govern the universe and everything within it. As observational techniques and data analysis continue to advance, researchers delve deeper into some of the most intriguing ideas about the universe, hoping to unveil its most hidden secrets. Their goal is not only to better understand the intricate fabric of reality, but also to comprehend how the very shape of the cosmos could alter our perceptions of existence. The topology, or the shape of the universe, is of critical importance. It directly influences what might lie beyond the reach of our current observations. Space-time itself, the fundamental stage upon which all cosmic events unfold, is molded by the universe's topology. Depending on its specific geometric configuration, the implications for the realms that lie beyond our observable limits could be profound. The way space-time connects, or fails to connect, distant regions could lead to some mind-boggling possibilities about the nature of the universe that extend far beyond the stars we can see. For instance, if the universe were shaped like a torus or a donut, it could wrap around itself. In this scenario, regions of the universe that seem far apart could, in fact, be deeply interconnected in ways that defy our traditional linear understanding of space. Imagine traveling in one direction for an incredibly long time. Eventually, you'd come back to where you started, much like walking in a straight line around the surface of a donut. Under this model, regions just beyond our observable universe might be copies or slight variations of what exists within the observable limits, possibly repeating cosmic structures or phenomena. But the universe's topology may not be so simple. What if, instead of a closed shape like a torus, the universe were shaped like a Mobius strip or a Klein bottle, both of which have non-orientable properties? These strange shapes would fundamentally alter our understanding of space and time. In such a universe, there may be no traditional boundaries. Traversing certain paths could lead to unexpected transformations, like shifting perspectives, or even the experience of time itself warping in peculiar ways. A universe like this could maintain continuity across vast stretches of space, but exist in realms that exhibit a variety of physical realities far from our own. Moreover, the implications of cosmic topology ripple out to the very concept of the multiverse. If different regions of space-time can have different topological characteristics, it may be possible for entirely separate universes to coexist, each with its own set of physical laws. In this view, our universe might not be unique at all, but just one of many in a vast multiversal tapestry, all governed by their own individual rules of physics. Patterns or anomalies in the cosmic microwave background radiation, or even the distribution of galaxies, might provide clues about these exotic structures. These subtle signs could offer hints about a deeper, more intricate reality that lies just beyond our observational reach. The study of cosmic topology forces us to rethink the very foundation of reality. It challenges our assumptions about the interconnectedness of existence and beckons us to explore ideas that may seem far removed from the world we know. As researchers continue to investigate these questions, new insights into the very structure of the universe, both observable and beyond, could have profound implications on how we perceive time, space, and existence itself. While a conclusive understanding of cosmic topology remains elusive, cosmologists are employing a variety of innovative methods to investigate the universe's structure. One promising line of inquiry lies in the analysis of the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang that carries crucial information about the early universe. By closely examining the fluctuations and patterns in the CMB, scientists can search for signs that suggest a more intricate topological configuration than the simple, flat universe we commonly envision. For example, if the universe has a compact topology, such as a torus, certain temperature patterns might repeat themselves, providing clues that the universe is somehow wrapped around. Special techniques like searching for matching circles or unique temperature anomalies could reveal that the universe has a closed shape, folding back on itself in a way that conventional cosmology doesn't predict. Another method to explore cosmic topology is through the study of the large-scale structure of galaxies and galaxy clusters. If our universe has a unique topological structure, it might be reflected in how galaxies and voids are distributed. By mapping the locations of galaxies across enormous distances and analyzing their distribution patterns, researchers can check for irregularities that differ from the expectations of a simple, flat universe. For example, if galaxies exhibit repeating patterns or alignments that are not predicted by standard models, it could point to the presence of a more complex underlying structure. Ultimately, these lines of investigation are just the beginning of a journey into the unknown. Each new discovery, each new anomaly opens the door to more questions and pushes the boundaries of our understanding further into the mysteries of cosmic topology. What we learn next may forever alter how we perceive the universe and our place within it. Gravitational lensing provides a captivating tool for exploring the hidden intricacies of the cosmos. This phenomenon occurs when massive objects, such as galaxies or clusters of galaxies, bend the path of light from more distant sources. The result is the formation of multiple images or distorted views of these far-off objects. By analyzing these lensing effects, researchers can uncover patterns that suggest the presence of unusual spatial configurations. Potentially, pointing to a non-trivial cosmic topology. Although conclusive evidence for specific cosmic topologies remains elusive, these methods are pushing the boundaries of our understanding. With advancements in observational techniques, more refined computational models, and the ever-growing wealth of data from large-scale surveys, we stand on the brink of making groundbreaking discoveries. These advancements may eventually reveal the true structure of the universe, providing insight into how it evolved and perhaps how it connects with realities beyond the limits of our observation. The concept of cosmic topology invites us to rethink the very nature of the universe's structure. Instead of envisioning an infinite expanse of empty space, non-trivial topologies suggest that the universe may have a much more complex shape. Imagine, for instance, a three-dimensional space that's intricately folded or interconnected in ways we can't yet fully comprehend. A popular analogy for this is the shape of a donut. In such a universe, traveling far enough in one direction could eventually bring you back to your starting point, as if you were moving along the surface of the donut. This idea challenges our assumptions about what lies beyond the observable universe. Traditionally, we think of the universe as extending outward into infinite space, filled with galaxies, stars, and cosmic phenomena. But with a non-trivial topology, what lies beyond the limits of our observation may not simply be empty voids of space. Instead, it could be more of the same, regions that are still part of a larger, interconnected cosmic structure. Such a perspective challenges the notion of boundaries or edges in the universe, opening the door to creative and speculative theories about how space might be linked in ways we cannot yet see. For example, there could be distant regions of the universe that are out of our sight, yet remain part of a grander, more intricate structure. This idea suggests that even in the farthest reaches of the cosmos, there may be regions that are causally connected, offering a tantalizing glimpse of what a truly interconnected universe might look like. The implications for our understanding of space, time, and reality are profound. Beyond just the structure of the universe, non-trivial topologies could have far-reaching effects on the very nature of reality itself. If our universe is part of a larger cosmic topology, it raises questions about the fundamental nature of the galaxies we observe. Are these galaxies merely isolated points, or could they be sections of a greater cosmic tapestry? This interconnectedness could potentially influence the way light and gravitational waves travel through space, enabling us to detect traces of distant regions that would otherwise remain beyond our reach. Such discoveries could reshape our view of the cosmos, highlighting the global features that might unite all of space. As scientists continue to gather data from vast cosmic surveys, they may detect patterns and anomalies that suggest a more complex and interconnected structure than we ever imagined. This could fuel a new era of curiosity, inspiring bold, new inquiries into the nature of the universe and existence itself. Understanding how the universe could be connected in ways we have yet to imagine opens fresh avenues for exploration. It challenges conventional ideas about the origin of cosmic structures and invites us to ask profound questions about our place in this vast, potentially interconnected cosmos. Meanwhile, the concept of white holes offers another fascinating avenue for speculation. A white hole, as theorized, is the theoretical opposite of a black hole. While black holes draw in everything that comes too close, trapping light and matter alike, a white hole would hypothetically expel matter and energy. In this model, nothing could enter a white hole, making it a one-way exit from the universe, or perhaps from another region of space-time. This idea excites scientists because it offers a potential resolution to the long-standing mystery of what happens to matter that falls into a black hole. The relationship between black holes and white holes arises from the equations of general relativity, which describe how mass and energy influence the fabric of space-time. Some solutions to these equations suggest that if black holes exist, white holes might also be a theoretical possibility. In this scenario, matter that enters a black hole might eventually be expelled from a white hole, either in another part of the same universe or even in a different universe entirely. This mind-bending idea presents exciting possibilities about the interconnectedness of cosmic structures and the mysteries that still lie ahead in our exploration of the universe's deepest secrets. Moreover, delving into the concept of white holes opens up a rich tapestry of questions, particularly around the nature of entropy and the fate of information within our universe. Black holes have long been known for their chilling reputation. Once something crosses their event horizon, it seemingly disappears, leaving behind no trace. This idea has sparked some of the most perplexing paradoxes in theoretical physics, especially when it comes to the fate of information. According to traditional theories, black holes erase any information that falls into them, yet this contradicts one of the fundamental principles of quantum mechanics, that information cannot simply vanish. Some researchers propose a fascinating possibility. What if matter and energy that enter a black hole could eventually re-emerge through a white hole? This idea offers a potential solution to the information paradox and could shed light on how the universe might preserve information across vast cosmic distances. The relationship between black holes and white holes grows even more compelling when we consider the potential impact on multiverse theories and the very nature of time itself. While white holes remain hypothetical at this point, their study, when paired with the exploration of black holes, offers an opportunity to deepen our understanding of the cosmos. These objects challenge scientists to think in new ways about space-time, energy flows, and the fundamental laws of the universe. Though their existence has yet to be confirmed, white holes continue to captivate theoretical physicists, inspiring a wealth of new ideas and stimulating the imagination of those trying to unlock the mysteries of our reality. The idea of white holes as gateways to other universes or regions beyond our cosmos is an exciting possibility that emerges from the realms of theoretical physics and speculative cosmology. If we entertain the notion that white holes exist, their very nature as objects that expel matter and energy suggests they could serve as exits from the gravitational clutches of black holes. This tantalizing possibility raises the prospect that white holes might not just expel energy back into the universe, but could even connect different regions of space, or perhaps entire universes. A leading theoretical model in this area involves wormholes, tunnel-like structures that link black holes, where matter is absorbed, to white holes, where it is expelled. In this framework, matter that enters a black hole might traverse through the wormhole and emerge from a white hole in a completely different region or dimension. The concept is nothing short of extraordinary, a potential cosmic highway that allows for the rapid traversal of vast stretches of space-time, or even the possibility of exiting our own universe altogether. Some models even go further, suggesting that our universe may be but one of many in a much larger multiverse. If white holes are indeed real, they could act as portals that facilitate communication or transfer between these separate universes. This notion gives rise to the idea of multiversal exchange, the movement of matter and information between realms beyond our own, raising profound questions about the nature of existence and reality. While these ideas are still speculative, they push the boundaries of our knowledge, compelling us to ask deeper questions about black holes, space-time, and the fundamental forces that govern the universe. The search for empirical evidence supporting the existence of white holes remains an open challenge in theoretical physics. However, should white holes be discovered, it could revolutionize our understanding of the cosmos, transforming how we perceive not only the connections between different parts of our universe, but also the relationship between universes in the multiverse. The study of white holes stands as a testament to humanity's unyielding curiosity and its quest for knowledge in an ever-expanding universe. The pursuit of these cosmic gateways showcases the lengths to which scientists are willing to go in order to unravel the deepest secrets of existence. Support for the potential existence of white holes primarily comes from the equations of general relativity, particularly the solutions derived from Einstein's field equations. These equations describe how matter influences the curvature of space-time, offering predictions about phenomena like black holes. One of the most famous solutions is the Schwarzschild solution, which explains the structure of non-rotating black holes, including their event horizons and singularities. Extending these concepts, researchers have proposed that white holes could be natural counterparts to black holes under certain conditions, offering a mirror image of the black hole's gravitational pull. Another crucial piece of the theoretical puzzle is the Kerr solution, which accounts for rotating black holes. This framework also provides insights into rotating white holes, suggesting that if such objects exist, they may exhibit unique characteristics. By studying the angular momentum of black holes and how this influences space-time, physicists are beginning to uncover the possible dynamics that could govern white holes. These findings point to the idea that white holes, much like black holes, may be a fundamental part of the universe's fabric, existing in parallel to their black hole counterparts under specific conditions. In the grander scheme, the possibility of white holes raises profound implications for our understanding of space-time, the structure of the cosmos, and the fundamental forces that govern it. As the search for these enigmatic objects continues, so too does our search for answers to the most pressing questions about the universe's true nature. The idea of white holes is deeply intertwined with ongoing discussions about wormholes, a fascinating concept in theoretical physics. These enigmatic entities could offer a glimpse into the very structure of the universe itself. Some physicists speculate that black holes, those cosmic giants that devour everything in their path, might be connected to white holes through structures called wormholes. A concept known as the Einstein-Rosen bridge visualizes this potential connection, a hypothetical shortcut through space-time that might link a black hole with a white hole. Although these wormholes are still purely theoretical, they open up possibilities for exploring new dimensions in our understanding of the cosmos. Yet, the challenges surrounding wormholes are immense. Stability and the ability to travel through them remain major obstacles. Despite this, the idea of such structures continues to spark curiosity among researchers. Could these bridges between black and white holes be real, or are they simply a theoretical curiosity? They challenge us to rethink the fabric of space-time itself and how different singularities could potentially interact with one another. In recent years, advancements in quantum gravity have led to models that might bring us closer to resolving some of the most profound mysteries in theoretical physics. One of the most captivating of these models proposes that black hole thermodynamics and information theory may not be as contradictory as we once thought. Some researchers believe that instead of erasing information, as traditional views suggest, black holes could release it via white holes. This would provide a possible resolution to the notorious black hole information paradox, which questions how information about matter that enters a black hole could be lost in violation of quantum mechanics. If white holes could serve as a conduit for this lost information, it could pave the way for a deeper understanding of the universe's fundamental nature. Such models push us to adopt a more holistic view of the cosmos, one in which black and white holes are intricately connected. Their theoretical existence invites us to explore new dimensions of reality, where information is neither lost nor forgotten, but transformed in ways we're just beginning to comprehend. The concept of white holes introduces significant challenges to our understanding of thermodynamics and entropy, particularly when placed alongside black holes. Classical thermodynamics tells us that entropy, a measure of disorder in a system, tends to increase over time. This principle, known as the second law of thermodynamics, suggests that natural processes evolve towards states of greater disorder. Yet black holes seem to defy this rule, as they appear to consume matter and energy without contributing to the growth of entropy. In fact, black holes are often described as entropy factories because they absorb information without a clear way to recover it. Now, imagine the existence of white holes, entities that are hypothesized to expel matter and energy. If they were real, they would directly challenge the second law of thermodynamics. How could a system expel matter and decrease entropy locally? Could the expelled matter carry the entropy of its origin, or would it somehow reset the entropy of the universe itself? These questions lie at the heart of one of the most perplexing mysteries in modern physics. Further complicating this puzzle is the black hole information paradox. In classical physics, the idea that information can be lost seems impossible, especially given the tenets of quantum mechanics, which state that information must always be preserved. If white holes could act as outlets for this lost information, they might offer a solution. The expulsion of matter from a white hole could potentially restore the lost information, thus reconciling the laws of thermodynamics with the behavior of black holes. This relationship between black holes and white holes challenges our fundamental understanding of how entropy behaves. Could matter that was once consumed by a black hole regain its original state upon being ejected through a white hole, suggesting that the universe itself might be able to reset entropy in some way? Such an idea opens up a new perspective on the life cycle of matter and energy, not only within black holes, but across the cosmos. Moreover, considering white holes within the broader context of cosmic evolution brings forth compelling possibilities. Could the connection between black holes and white holes shape the ongoing dynamics of entropy in the universe? Some theorists propose that this interplay could represent cycles of creation and destruction, contributing to a delicate balance of entropy on a universal scale. If this theory holds, it could suggest that entropy is not a rigid, unbreakable law, but rather a dimensional feature of the universe that evolves with time. Despite the rich theoretical framework surrounding white holes, there is no direct observational evidence to confirm their existence. While black holes have been studied extensively and observed through indirect means, such as gravitational waves and X-ray emissions, white holes remain elusive. The main challenge lies in the very nature of white holes. Unlike black holes, which attract and absorb matter, white holes are theorized to expel it. As a result, they would not emit detectable radiation, making them exceedingly difficult to detect with current technology. Nonetheless, some astrophysicists have turned to certain astronomical phenomena as potential clues. Gamma-ray bursts, for instance, are intense flashes of gamma rays observed in distant galaxies. Some researchers have speculated that these bursts could be linked to white hole activity, proposing that they might represent sudden bursts of energy and matter being expelled from a white hole. While this idea remains highly controversial within the scientific community, it has nevertheless sparked further investigation. In conclusion, while the existence of white holes remains a tantalizing and unproven theory, the ongoing exploration of their potential implications continues to fuel debates among physicists. Could these entities hold the key to understanding the mysteries of black holes, entropy, and the very nature of spacetime? Only time and further research will tell. The notion of peculiar astronomical objects such as quasars and supernovae has sparked a wave of curiosity among scientists, prompting them to question whether these phenomena might be linked to the elusive concept of white holes. Quasars, with their extraordinary luminosity and incredible energy output, stand out as particularly intriguing. Could these bright beacons of the cosmos be remnants of matter ejected from a white hole? While such hypotheses certainly provide a fascinating avenue for exploration, they remain speculative at best. Current observations, while compelling, do not offer conclusive proof of the existence of white holes. Instead, they serve to highlight the need for further research and a deeper understanding of the universe's underlying physics. To definitively confirm or refute the presence of white holes, advancements in our observational technology and a more thorough grasp of cosmic laws will be required. As our instruments evolve and our techniques grow more refined, it's possible that we will begin to detect subtle, indirect indicators that hint at the presence of white holes. Alternatively, we may uncover entirely new phenomena that redirect our understanding of the cosmos in unexpected ways. Until such breakthroughs occur, the allure of white holes remains largely theoretical, rooted more in speculation and intellectual discussion than in hard empirical evidence. In parallel with these considerations, another concept that captures the imagination of theoretical physicists is that of cosmic strings, predicted in various cosmological models, particularly within the framework of string theory. These one-dimensional defects are thought to have formed in the early universe during phase transitions that followed the Big Bang. Cosmic strings, if they exist, are not only theorized to be incredibly thin, but also immensely dense, with gravitational forces so intense that they could reshape the fabric of spacetime itself. Their study could potentially offer new insights into the structure of the universe and the very forces that govern it. Cosmic strings are thought to have emerged soon after the Big Bang, as the universe was cooling and undergoing significant transformation. During this time, the forces that shape the universe began to settle into their distinct states, potentially leading to imperfections in space-time itself. These imperfections might have resulted in the formation of topological defects, such as cosmic strings. Once created, these strings would stretch across vast expanses of the universe, possibly extending beyond our observational reach, creating gravitational anchors that could shape the formation of galaxies and other cosmic structures. One of the most intriguing aspects of cosmic strings is their potential to extend beyond the observable universe, opening up possibilities for understanding realms we cannot directly observe. If they exist, and if these strings are sufficiently large and massive, they might warp spacetime to such an extent that their gravitational pull could bend light, a phenomenon known as gravitational lensing. This bending of light could allow us to glimpse distant and otherwise invisible regions of the universe, providing a window into parts of the cosmos that lie beyond the reach of our current observational tools. In addition to these insights, cosmic strings could provide a theoretical framework for exploring the existence of multiple dimensions or higher dimensional spaces. These strings might offer clues about how different realms of the universe could interact, potentially supporting theories such as the multiverse. By examining cosmic strings, scientists could delve into questions about the structure and evolution of the universe, probing scales far beyond what we can currently observe. Understanding the nature of cosmic strings could be key to unlocking some of the most profound mysteries of the cosmos. They are intrinsically tied to the earliest moments of the universe's formation, particularly within the context of cosmological models describing the period immediately following the Big Bang. As the universe expanded rapidly and cooled, various phase transitions occurred, similar to the way matter changes state from liquid to solid under certain conditions. During these transitions, fundamental forces could have undergone symmetry breaking, causing them to settle into different states and potentially forming topological defects like cosmic strings. This moment of symmetry breaking, believed to have occurred in the infant universe, could be the key to understanding the origins of cosmic strings. As the universe cooled, the forces that governed it might have separated or unified, creating regions where the symmetry of physical laws was disrupted. In these imbalanced areas, energy densities could have caused the formation of cosmic strings, which would stretch across vast distances, their incredible density and gravitational strength shaping the universe's large-scale structures. The influence of cosmic strings on the formation of galaxies and the distribution of matter is profound. Their gravitational forces could have acted like scaffolding, guiding matter into dense regions where galaxies and other cosmic structures began to form. Rather than gravity alone, cosmic strings could have facilitated a more efficient method for clustering matter across vast expanses of space. This could provide an explanation for the uneven distribution of matter in the universe today, as cosmic strings might have helped organize and direct the formation of the large-scale structures we observe in the cosmos. In essence, cosmic strings could hold the key to understanding the earliest days of the universe, offering a potential explanation for the distribution of matter and the development of the structures that define the observable universe. By studying these theoretical objects, we might uncover new dimensions of understanding that transcend the boundaries of current cosmological knowledge, opening up possibilities for even deeper exploration of the cosmos. The study of cosmic strings holds profound implications for understanding the early universe's dynamics and the interactions between different fields. These enigmatic structures, if they exist, could illuminate our comprehension of key concepts like cosmic inflation, a period of rapid expansion following the Big Bang that effectively smoothed out the fabric of the universe. As researchers delve into the conditions and outcomes of phase transitions in the early cosmos, cosmic strings might offer a glimpse into the fundamental processes that shaped the universe during its most formative moments. The potential existence of cosmic strings suggests that our current understanding of the cosmos may need to be redefined, pointing toward deeper, hidden mechanisms that govern its evolution. Their study might also help explain how complex structures, such as galaxies, stars, and even life itself, emerged from simple, primordial beginnings. This search could ultimately rewrite our perception of how the universe evolved from its earliest moments to the intricate and diverse cosmic landscape we observe today. Similarly, domain walls present another fascinating aspect of cosmological research. These topological defects, which can arise in a variety of field theories, are two-dimensional structures formed when distinct regions of the universe exhibit different field values or phases. Think of it like a phase transition in which boundaries form between regions of differing states, such as ice and water. In cosmology, domain walls emerge where these differences become physically significant, and their role in shaping the early universe's dynamics cannot be understated. Domain walls often form during symmetry-breaking phase transitions, when a field transitions into a specific state, creating regions with different vacuum states. These boundaries separate regions where physical laws, constants, or the properties of matter differ. The presence of a domain wall introduces distinct physical properties to the regions on either side, such as unique energy densities and behaviors. This separation may influence the way matter moves and interacts across different phases, potentially affecting the overall evolution of the universe. Cosmologists have begun exploring the broader implications of domain walls, particularly how they could affect cosmic evolution. For instance, these structures may exert gravitational forces on surrounding matter and fields, acting as barriers that influence how matter accumulates and how density variations form across the cosmos. As with cosmic strings, domain walls could offer a new perspective on the formation of cosmic structures, but through different mechanisms. One particularly intriguing possibility involves the potential for domain walls to separate different regions of space governed by different sets of physical laws. On one side of a domain wall, the fundamental constants and rules of physics might be vastly different from those on the other side. This idea raises the exciting prospect of the multiverse, where distinct regions of space, each following their own physical laws, coexist in parallel. Such theories challenge our understanding of the universe and provoke deeper questions about the very nature of reality itself. The intersection of cosmic strings and domain walls also opens the door to mind-bending possibilities concerning the connection between our universe and others. Both structures could serve as bridges or boundaries between regions of space-time or even entire universes, forming an intricate web of connections across the cosmos. Cosmic strings, being one-dimensional defects in space-time, could potentially stretch far beyond our observable universe, creating pathways through which matter and energy might flow or be transformed. Some hypotheses even suggest that cosmic strings could link to other topological defects, such as wormholes, providing shortcuts or conduits for travel across vast distances, or, in a more speculative sense, between entirely separate universes. On the other hand, domain walls, as two-dimensional structures, could function as barriers or gateways that separate regions of space governed by distinct physical laws. Crossing a domain wall might expose an observer to entirely new and unfamiliar conditions, offering a unique framework in which two different regions of space could experience separate realities. This scenario feeds into the idea that domain walls might delineate entire universes within the broader context of a multiverse. Though primarily theoretical at this stage, cosmic strings and domain walls compel us to rethink the very nature of existence. These extraordinary phenomena raise powerful questions about how our universe and possibly others came to be, how they interact, and what the future of cosmic exploration might hold. By challenging our fundamental understanding of the cosmos, they encourage us to peer deeper into the unknown, perhaps uncovering answers to the most profound mysteries of all. How did the universe begin, and what might it reveal about the infinite possibilities that lie beyond our observational limits? Exploring the enigmatic phenomena of cosmic strings and domain walls requires a fundamental shift in how we perceive the universe. If we consider their roles as potential gateways to understanding deeper cosmic truths, we must delve into the intricate ways in which their presence could alter the very fabric of reality. These cosmic structures are not merely theoretical oddities. They may hold the key to unraveling the mysteries of the cosmos and shaping our understanding of the multiverse. Take, for instance, the cosmic string. A hypothetical, one-dimensional defect that stretches across the universe, this string would influence the surrounding gravitational dynamics in profound ways. Imagine how the gravitational field around a cosmic string could warp the space-time fabric itself, creating distortions in the path of light that reaches us from distant galaxies. The result? A series of unique visual phenomena, rings or arcs formed as light bends around the string, a signature effect known as gravitational lensing. This gravitational lensing would be a cosmic fingerprint, offering a glimpse into the string's presence and providing scientists with a tool to investigate the unknown. Moreover, the cosmic string could leave behind subtle imprints in the cosmic microwave background, CMB, radiation. The CMB, often seen as the afterglow of the Big Bang, provides a snapshot of the universe's early moments. But these strings, with their unique interactions with surrounding matter and energy, might cause slight temperature fluctuations in the CMB, creating irregularities, tiny deviations from the expected smoothness. These anomalies would stand out as non-Gaussian features, offering scientists to detect cosmic strings by analyzing the CMB and searching for patterns that defy standard isotropy. In parallel, domain walls, another type of theoretical defect, may leave behind different kinds of cosmic signatures. These vast, two-dimensional structures could significantly influence the density of matter in the universe. By creating regions of high energy concentration, domain walls could directly affect the formation of galaxies, clusters, and even the distribution of dark matter across the universe. As a result, scientists may turn to the large-scale structure of the cosmos for clues. Unexpected voids, anisotropies, or density fluctuations might hint at the existence of these walls, providing a unique opportunity to observe their effects from afar. Both cosmic strings and domain walls challenge our conventional understanding of space and time. These structures, though abstract in their nature, force us to reconsider the very essence of reality. They speak to a universe that is interconnected in ways we can only begin to comprehend, where what happens in one region can ripple across vast distances, shaping the cosmos in ways we cannot yet fully predict. As such, they present a fascinating frontier for scientific exploration, providing tantalizing possibilities for discovering new layers of reality and expanding our understanding of the fundamental workings of the universe. Through this lens, these cosmic phenomena are no longer just theoretical curiosities. They become potential keys to understanding the multiverse, portals to realities beyond our own, interconnected yet distinct. By uncovering their signatures, we move one step closer to answering some of the most profound questions of existence. What lies beyond the universe we know? How do the unseen forces shaping the cosmos interact with the very nature of reality itself? Only through these investigations can we hope to unlock the deeper truths that lie at the heart of the universe. In the search for answers to the universe's deepest mysteries, domain walls stand out as an intriguing candidate. These theoretical structures could leave an indelible imprint on the cosmic microwave background, CMB, the ancient radiation that traces the birth of the universe. The potential signature of domain walls may show up as distinct non-Gaussian patterns in the CMB, specifically through sudden temperature fluctuations across this radiation. These fluctuations could be caused by density perturbations tied to the presence of domain walls in the early universe. Such subtle disturbances would act as fossilized markers, revealing the presence of these elusive walls, which may have played a significant role in shaping the early cosmos. This concept connects directly to the search for other cosmic anomalies, such as cosmic strings. The pursuit of these and other primordial structures hinges on two primary observational techniques: analyzing gravitational lensing phenomena and probing the large-scale structure of the universe. Gravitational lensing, where massive objects bend light around them, offers a window into the distorting influence of space-time itself. Meanwhile, by studying the cosmic microwave background and mapping the distribution of matter across vast distances, scientists can detect patterns indicative of long-forgotten cosmic events. These signatures, potentially tied to domain walls and cosmic strings, might just hold the key to understanding the forces that shaped our universe from its very inception. As observational technology advances, there is a growing sense of optimism among researchers. The prospect of uncovering these subtle patterns could bring profound insights into the nature of the cosmos and the fundamental processes that govern its evolution. One of the most intriguing concepts emerging from modern physics is the holographic principle. This thought-provoking idea challenges the very nature of reality, suggesting that the universe we perceive in 3 dimensions might be an illusion, a projection based on a 2-dimensional surface that encodes all the information about the space we experience. The holographic principle originates from black hole physics and string theory, especially when researchers notice that black holes have a maximum entropy proportional to the area of their event horizon, rather than the volume of the space they enclose. This odd observation pointed to the possibility that information about everything within a region of space could be stored on its boundary, not within the space itself. This revelation carries profound implications for how we think about space-time and information. The holographic principle proposes that the complex, multi-dimensional reality we experience may emerge from processes happening on a simpler, lower-dimensional boundary. In other words, our universe could be a vast, intricate projection stemming from underlying data encoded on a distant, higher-dimensional surface. This idea not only revolutionizes our understanding of dimensions, but also offers a novel perspective on gravity and quantum mechanics, 2 pillars of modern physics that have long been difficult to reconcile. The holographic principle's implications are especially notable when considering black holes. One of the greatest mysteries in modern physics is the fate of information that falls into a black hole. Traditionally, many have believed that this information is lost forever, leading to what is known as the information paradox. But the holographic principle suggests that this information is not lost. It's encoded on the surface of the black hole. Eventually, this information could be released back into the universe, ensuring that the conservation of information is maintained across all of space-time. This breakthrough could answer some of the most vexing questions about the fundamental nature of reality and the universe's most enigmatic objects. Moreover, the holographic principle pushes us to re-examine our assumptions about space-time itself. What if the space we live in, the fabric of the universe, is not as solid and intrinsic as we believe? Could it be that all of space-time and its associated physical laws are merely the product of interactions in a higher dimensional space beyond the 3 dimensions we know? This is where string theory comes into play. String theory proposes that the universe is composed of tiny vibrating strings, and these strings exist in more dimensions than the 3 we experience in daily life. If the holographic principle holds true, our universe, along with its physical laws, could be the result of fundamental interactions occurring in these extra dimensions. Gravity, as understood in classical physics, is often at odds with the principles of quantum mechanics, which govern the behavior of subatomic particles. However, the holographic principle might offer a way to bridge this gap. It presents a new framework that could provide a more unified view of these 2 areas of physics. Instead of viewing gravity and quantum mechanics as fundamentally incompatible, the holographic principle allows us to explore them as potentially complementary facets of a deeper, underlying reality. By viewing the universe as a projection of higher dimensional processes, the holographic principle offers us a paradigm shift, a new lens through which we can explore not just the cosmos, but the very fabric of reality itself. This perspective opens up new avenues for research in cosmology, quantum mechanics, and gravity, promising to reshape our understanding of the universe's fundamental laws. As scientists continue to delve deeper into these concepts, the holographic principle challenges us to rethink the nature of existence, urging us to consider that reality in all its complexity might be an elaborate projection of information beyond the reach of our direct perception. However, if the holographic principle holds true, it could suggest that gravitational interactions are not just fundamental forces in themselves, but rather manifestations of much deeper, more intricate processes unfolding in a higher dimensional realm. This revelation may offer the key to a unified understanding of the fundamental forces of nature, bridging the gap between the macroscopic forces of gravity and the microscopic world governed by quantum mechanics. Such an idea raises profound existential questions about the nature of reality. If space and time are not immutable truths, but instead emergent phenomena from a deeper, higher dimensional space, it would challenge our very perception of the universe. This opens up new avenues for reconsidering concepts like causality, existence, and even the nature of life within a cosmic framework. Researchers would be compelled to re-examine the very fabric of our universe, exploring the intersections between cosmology, quantum mechanics, and philosophy. In this context, the holographic principle offers a radical new perspective, envisioning our universe as a projection that emerges from the information encoded on a two-dimensional surface in a higher dimensional space. Such a viewpoint not only challenges our current understanding of reality, but it could also provide a profound shift in how we study and interpret the cosmos. This new approach might lead us closer to unlocking the fundamental structure of the universe and uncovering the true nature of the forces that shape it. The implications of the holographic principle extend far beyond what we can observe with our limited senses. If our three-dimensional reality is indeed a projection, it suggests that the universe could stretch far beyond the observable universe, with regions of space that remain fundamentally connected through higher dimensional structures. The laws of physics we observe within our visible universe might be just a fragment of a much larger, interconnected cosmic tapestry, one that exists far beyond the boundaries of our current observational capabilities. This cosmic interconnectedness raises fascinating questions about the flow of information and causality. If all the information that defines our universe can be encoded on a boundary, then it's possible that events in distant, unobservable regions of space could still influence what we experience in our observable universe, albeit in indirect ways. This suggests that patterns or phenomena invisible to our current methods of measurement might ripple through the fabric of space-time, leaving traces of their influence on the universe we perceive. In this light, the holographic principle also offers a fresh lens through which to explore the mysteries of dark matter and dark energy. If these elusive forces arise from higher dimensional structures, their properties and behaviors may be better understood through the lens of holographic relationships. This shifts the quest from merely identifying particles or fields that could represent dark matter and dark energy, to exploring the underlying geometric and informational principles that govern their existence in the cosmos. Ultimately, this reimagining of dark matter and dark energy could lead to groundbreaking discoveries, transforming our understanding of the universe at its most fundamental level. Embracing the holographic principle forces us to reconsider the very limits of our understanding of the universe. It challenges traditional ideas about the boundaries of what is observable and encourages a deeper exploration of the cosmos, where what lies beyond our immediate view could be just as meaningful as what we can measure. This perspective invites profound questions about the nature of reality itself, suggesting that the universe may be far more intricate and layered than we currently appreciate. By extending our thinking beyond the observable, we confront the tantalizing possibility that the universe is far richer and more complex than the constraints of our present observations indicate. The holographic principle is particularly compelling because it touches on some of the deepest questions about space, time, and the fundamental forces that govern existence. It is intimately linked with string theory and the search for a unified theory of quantum gravity, offering potential solutions to some of the most perplexing problems in theoretical physics. At the heart of string theory is the radical idea that the fundamental constituents of the universe are not point-like particles, but rather tiny, vibrating strings existing across multiple dimensions. This notion suggests that the building blocks of reality are far more complex than we can perceive with our everyday senses. These additional dimensions, beyond the familiar three of space and one of time, are not merely abstract ideas, but essential components that ensure the consistency of the theory. In this framework, the holographic principle complements string theory, as both challenge conventional understandings of space, time, and reality itself. The holographic principle proposes that the information contained within a volume of space could be encoded on its boundary, perhaps on a two-dimensional surface. This implies that our entire three-dimensional universe could be a projection of data from this boundary, a concept that aligns seamlessly with string theory's multidimensional structure. Essentially, this would mean that the rich complexity of particle interactions and fundamental forces emerges from more fundamental layers of reality that we are only beginning to comprehend. One of the most exciting implications of the holographic principle is its potential to resolve long-standing issues in theoretical physics, particularly those involving quantum mechanics and general relativity. One of the most famous challenges in this regard is the black hole information paradox. According to classical physics, information that falls into a black hole is lost forever, but the holographic principle suggests otherwise. In the context of string theory, it proposes that information swallowed by black holes may not be lost, but instead stored on the event horizon of the black hole, hinting at a way for quantum mechanics to remain consistent even under the extreme conditions of black holes. This could provide a bridge between quantum mechanics and general relativity, two pillars of modern physics that have been notoriously difficult to reconcile. String theory also provides a framework for exploring higher dimensional phenomena, such as additional spatial dimensions, which could influence gravitational behavior. The holographic principle fits neatly into this picture by suggesting that gravitational degrees of freedom could be fundamentally tied to quantum information. This connection suggests that gravity, as we understand it, might not be a fundamental force, but an emergent phenomenon arising from more basic quantum processes. By linking string theory, quantum gravity, and the holographic principle, we are invited to rethink the very nature of our reality. These ideas propose that our three-dimensional world is not an absolute, fixed entity, but an emergent projection from a higher dimensional framework. Information encoded on boundaries in these higher dimensions could give rise to the space, time, and forces we experience in our universe. This opens new avenues for resolving some of the most fundamental questions about the cosmos, including the nature of gravity, the structure of space-time, and the reconciliation of quantum mechanics with general relativity. The holographic principle has even found experimental support over time, particularly through studies on black holes and the intricate relationship between quantum gravity and the structure of the universe. It remains a bold and promising hypothesis suggesting that the universe may be far more connected, intricate, and mysterious than we have ever imagined. The journey to fully understand the holographic nature of existence is just beginning, and it promises to reshape our view of the cosmos in profound and unexpected ways. One of the most compelling pieces of evidence in the ongoing quest to understand the nature of the universe comes from the field of black hole thermodynamics. The groundbreaking work of renowned physicist Stephen Hawking revealed a striking insight. Black holes, long considered enigmatic voids, actually possess entropy. What's more, this entropy is directly proportional to the area of a black hole's event horizon, not its volume. This discovery suggests something profound. Could it be that the entirety of the information contained within a three-dimensional space is, in some way, encoded on a two-dimensional boundary? This idea, known as the holographic principle, provides a fascinating lens through which we can begin to reevaluate the structure of reality itself. In fact, the theory is not just limited to black holes. String theory, with its intricate models, has provided additional support for this notion. Certain calculations within string theory models suggest that the fundamental forces, including gravity, can be described in a holographic context. Imagine, for instance, a two-dimensional model that reflects characteristics of a four-dimensional spacetime. This theoretical approach, while still in its infancy, has already begun to offer a new way of thinking about gravity, space, and time, by providing evidence that the universe might fundamentally operate in a manner we have yet to fully grasp. The DCFT correspondence, which describes a relationship between higher dimensional gravity theories and lower dimensional quantum field theories, further strengthens this holographic view. But the pursuit of evidence doesn't stop there. Recently, scientists have turned their attention to the cosmic microwave background, CMB radiation, relic radiation from the early universe, which still permeates the cosmos today. By meticulously studying the subtle patterns and fluctuations embedded within the CMB, researchers have begun to uncover hints that might align with the holographic principle. These investigations seek to answer a key question. Can the large-scale structure of the universe be traced back to two-dimensional information encoded at its boundaries? As theories evolve, it becomes increasingly clear that this idea is not just speculative. The growing body of experimental data is gradually painting a picture that suggests that the universe, as we experience it, may have a far more intricate and layered nature than we ever imagined. The theoretical and observational evidence surrounding the holographic principle continues to unfold, creating a rich tapestry of data that challenges our traditional notions of space, dimension, and reality. While these concepts remain subjects of intense research and debate, the interaction between gravity, black holes, and quantum mechanics continues to push the boundaries of our understanding. Each new discovery brings us closer to unlocking the mysteries of the universe, inviting us to reevaluate what we know about the fundamental nature of existence itself. Yet, there is another groundbreaking theory that has captivated cosmologists, the theory of eternal inflation. Building upon the idea of inflation, an era of rapid expansion that occurred in the very early moments of the universe, eternal inflation proposes a far-reaching vision of the cosmos. According to this theory, inflation didn't end uniformly across all regions of the universe. Instead, some areas continued to expand while others ceased, leading to the formation of distinct pockets of space. These pockets, in turn, gave rise to new, separate regions of inflation, creating an ever-expanding multiverse of distinct universes, each with its own set of physical laws and constants. What's astonishing is that the universe we observe might not be unique. Rather, it could be one among countless other universes that coexist within this expansive cosmic landscape. These other universes may resemble our own in some ways, but they could also differ dramatically in their physical properties. In regions where inflation has ceased, cosmic structures like galaxies and stars formed, setting the stage for the universe as we know it today. But in those regions still in the process of inflation, the laws of physics we rely on may not even apply. This concept reshapes our very understanding of the universe. It suggests that rather than a single universe with a defined beginning and end, we might be living in one of many parallel universes, each unfolding according to its own set of rules. The theory of eternal inflation provides possible explanations for some of the most puzzling questions in modern cosmology, such as the uniformity of the universe's structure and the mysterious fluctuations observed in the cosmic microwave background radiation. But it also opens the door to profound philosophical reflections. As we confront the vast multiverse, we are compelled to ask deep questions about the nature of reality, existence, and our place within this intricate cosmic web. Every new step forward in understanding eternal inflation brings us closer to unraveling the mysteries of the universe's origins and its infinite possibilities. This theory, which builds on the foundations of the standard inflationary model, introduces new dynamics that challenge our preconceived notions of space and time. In doing so, it invites us to rethink not just the universe's past, but its boundless future. The standard inflationary model suggests that in the very earliest moments of the universe, a rapid exponential expansion occurred. This inflationary phase lasted a mere fraction of time, roughly between 10 to the power of minus 36 seconds and 10 to the power of minus 34 seconds after the Big Bang. This brief yet intense period of inflation resolved several critical problems in cosmology, including the flatness problem, the horizon problem, and the absence of magnetic monopoles. It also established the uniform, hot, and dense state from which the vast, large-scale structures we observe today in the universe emerged. In contrast to this model, eternal inflation introduces a more complex view, suggesting that inflation did not end uniformly across the universe. While some regions of space stopped inflating and evolved into the observable universe, other regions continued to inflate indefinitely, never ceasing their rapid expansion. As a result, rather than one singular event marking the conclusion of inflation, the universe experienced an ongoing process of expansion that resulted in the formation of multiple distinct regions, or pocket universes. Each of these pocket universes could possess its own unique set of properties and laws of physics, contributing to the concept of the multiverse, a vast collection of universes, each existing in parallel and governed by different fundamental rules. This shift from a single universe to the concept of an infinite, eternally inflating cosmos marks a profound departure from the standard model. In the traditional view, the end of inflation led to a universe that is homogeneous and isotropic, with uniform laws of physics governing its evolution. Eternal inflation, however, suggests a much more dynamic picture. It presents our universe not as a singular outcome of an isolated event, but as a mere bubble in an ongoing, never-ending process of inflation, wherein each bubble universe evolves according to its own set of conditions. The implications of eternal inflation are vast and complex. Not only does it propose a multiverse of universes, each with potentially different physical constants, but it also suggests that the very nature of reality is more fluid and diverse than previously thought. With this framework, it is no longer accurate to think of the universe's evolution as stemming from one single point of origin. Rather, it hints at a dynamic, ongoing process of cosmic expansion that generates new, self-contained universes, each with its own distinct history and characteristics. Bubble universes are the product of this process. As inflation continues in some regions of space, it ceases in others, giving rise to distinct regions where the rapid expansion halts, allowing these bubbles to cool and evolve into fully formed universes. These bubble universes can differ radically from one another. One bubble may share similar properties to our own observable universe, while another could have entirely different fundamental forces or even different dimensional structures. Such diversity is a direct consequence of the varying conditions within the inflating field, which shapes the development of each bubble. For instance, some bubbles might harbor conditions conducive to life, resembling our universe, while others could be uninhabitable, plagued by extreme conditions or the absence of basic elements. In fact, many of these universes might not contain matter at all, or might operate under physical laws completely alien to us. This variability arises from the inherent randomness of quantum fluctuations that occur during the inflationary process, a phenomenon that could lead to an unimaginable range of possible outcomes. The notion that eternal inflation can produce an infinite number of bubble universes is central to the multiverse theory. If each universe can evolve independently, shaped by its own initial conditions and physical laws, then the multiverse presents an infinite and ever-expanding collection of possible realities. Some of these universes may resemble our own, while others could be radically different, offering a multitude of diverse phenomena and evolutionary pathways. This raises intriguing philosophical and scientific questions about the nature of existence. If bubble universes truly exist, what does this say about our place in the cosmos? What does it mean for the concept of fine-tuning in the laws of physics? The possibility that other universes governed by different sets of physical laws may harbor their own forms of life or even vastly different forms of matter challenges our very understanding of the fundamental constants that govern reality. As scientists and cosmologists explore the far-reaching implications of eternal inflation, they continue to push the boundaries of our knowledge about the universe, questioning the very nature of existence itself. The idea that our universe is just one bubble in a vast, ever-expanding multiverse leads to profound inquiries about the origins of the cosmos and the infinite possibilities that may lie beyond our observable universe. In this dynamic model of eternal inflation, as certain regions of space cool and transition into self-contained universes, other regions persist in their rapid expansion, generating countless new bubbles over time. Each bubble represents a universe with unique physical properties, and the process is continuous and potentially infinite. With each new bubble, the multiverse grows, offering an ever-expanding horizon of cosmic possibilities. And as this process unfolds, it could give rise to a universe vastly different from our own, perhaps even challenging the very nature of life, matter, and reality as we understand it. Eternal inflation, an awe-inspiring concept in cosmology, suggests that even if previously formed bubbles cease inflating, new ones can continuously emerge. This means that the creation of universes could, in theory, go on forever. As scientists explore the far-reaching implications of this idea, they are faced with profound philosophical questions that challenge the very essence of existence and the nature of reality itself. Eternal inflation not only transforms our understanding of the cosmos, but also introduces the possibility of a vast, interconnected multiverse, stretching far beyond what we can observe. Each universe, a distinct and intricate reflection of a grand cosmic process, emerges as a product of this ongoing inflationary phenomenon. Though direct observational evidence supporting the theory of eternal inflation remains an area of ongoing research and debate, several indirect lines of evidence lend weight to its plausibility. One such area of inquiry centers on the cosmic microwave background radiation, CMB, the faint remnant of the early universe. Tiny fluctuations in this radiation reveal critical insights into the state of the cosmos just after the Big Bang, and some of these anomalies could very well be the byproducts of an inflationary phase. The temperature fluctuations observed in the CMB are a critical clue. These fluctuations, while minuscule, show a nearly uniform temperature across the sky, punctuated by slight irregularities. Such anomalies could be interpreted as the signature imprint of inflationary dynamics. This process, as proposed in the theory of eternal inflation, would have smoothed out the universe, setting the stage for the complex structures we observe today. The mechanisms suggested by eternal inflation indicate that these temperature fluctuations might have originated from quantum fluctuations that were dramatically amplified during the universe's rapid expansion. This provides further support for the notion that our universe underwent an extraordinary burst of inflation, fundamentally altering its structure and evolution. Another area where the implications of eternal inflation come into play is the large-scale structure of the universe. The distribution of galaxies, clusters of matter, and voids in space shows a remarkable level of uniformity. In particular, the gravitational influence that shaped the universe during its early expansion appears to have been exerted uniformly, creating the intricate cosmic web we see today. This uniformity, which could be linked to the inflationary process, suggests that the mechanisms behind eternal inflation might have created the necessary conditions for such cosmic structures to form. Additionally, one exciting line of investigation involves the search for primordial gravitational waves. If these waves were generated during the inflationary period, they would leave behind detectable traces, possibly seen as tensor modes in the cosmic microwave background. While definitive observations of these gravitational waves remain elusive, their potential discovery could offer a substantial boost to the inflationary paradigm, reinforcing the ideas surrounding eternal inflation. As research in these areas continues, the growing body of evidence may eventually provide a clearer picture of the validity of eternal inflation. Although conclusive observational proof remains just out of reach, the connections to cosmic phenomena and the large-scale structures of the universe present compelling avenues for exploration. The delicate interplay between inflationary dynamics and the evolution of our cosmos might one day reveal more than we could ever have imagined. On the other hand, the cyclic model of the universe offers a radically different perspective. According to this model, the cosmos undergoes an infinite series of expansions and contractions, forming an eternal cycle of big bangs and big crunches. In contrast to the idea of a single, one-time creation event approximately 13.8 billion years ago, the cyclic model suggests that the universe continuously evolves through these cycles. Each cycle begins with a big bang, followed by a period of expansion, and ultimately culminates in a contraction phase where the universe collapses back into a singularity, only to explode once again in another big bang. Thus, the cycle restarts. This cyclic model directly challenges the traditional Big Bang theory, which posits that the universe had a singular beginning marked by the explosion of space from an incredibly dense and hot state. The Big Bang theory implies a finite history for the universe, where expansion has continued uninterrupted since the original event. In stark contrast, the cyclic model asserts that time is infinite and the universe itself has no definitive beginning or end. Rather than seeing cosmic evolution as a linear process, the cyclic model presents a dynamic and eternal view, one in which the universe undergoes endless cycles of birth, death, and rebirth. The cyclic model of the universe is a fascinating and profound theory that challenges traditional concepts of cosmic evolution. At its core, this model hinges on the interplay between gravitational forces, dark energy, and other fundamental forces shaping the universe. As the universe expands, the influence of dark energy becomes increasingly significant, potentially triggering a phase of rapid acceleration. However, the theory suggests that this acceleration might only be temporary. Eventually, gravitational forces could regain dominance, causing the universe to contract, initiating a new cycle. This cycle of expansion and contraction would continue indefinitely, offering a radically different perspective on the universe compared to the conventional Big Bang theory, which posits a singular, one-time event marking the origin of the cosmos. What makes the cyclic model particularly compelling is its ability to account for many unresolved questions about the universe's ultimate fate. The theory not only addresses the expansion and behavior of cosmic structures, but also attempts to explain the nature of inflation, the rapid expansion that occurred in the very early universe. Through this approach, the cyclic model suggests that the universe is not bound by a singular origin, but is instead in a constant state of rebirth, perpetually cycling through phases of expansion and contraction. The parodic scenario takes this idea a step further by proposing an even more revolutionary model of cosmic creation. It presents the notion that our universe originated not from a singularity, as in the traditional Big Bang model, but from the collision of two three-dimensional brains, multidimensional objects that exist in a higher dimensional space. This theory, derived from string theory, suggests that the universe's birth was not a singular event, but rather the outcome of an energetic clash between these two brains, which are embedded in a higher dimensional space known as the bulk. The term pyrotic itself is derived from the ancient Greek word for conflagration, reflecting the intense energy released during the collision. This catastrophic event would have triggered the conditions necessary for the universe to evolve. Within this framework, the brains are not simply flat surfaces. They contain matter and energy, making them dynamic structures that interact with one another. When two such brains collide, the energy released in the process can initiate a phase of rapid expansion, much like the inflationary phase proposed by other models of the early universe. This expansion would lay the groundwork for the observable universe to evolve in the manner we see today. What sets the pyrotic model apart from the traditional Big Bang theory is the idea of cyclical creation. Rather than a one-time event, the pyrotic scenario suggests that the universe's evolution is driven by a series of recurring collisions between brains. Each collision leads to a new phase of expansion and contraction, creating an ongoing process of cosmic dynamics. This cyclical nature allows the universe to adapt and evolve, avoiding the limitations of a singular beginning. Moreover, the pyrotic model provides elegant solutions to some of the most enduring problems in cosmology, such as the flatness and horizon problems. The interactions between the brains could naturally result in a homogeneous and isotropic universe, one that appears the same in every direction, without needing to invoke a rapid inflationary period. Researchers working with this model aim to probe deeper into the fundamental principles that guide the creation and evolution of the cosmos, challenging our conventional understanding and opening up new avenues for exploring the mysteries of higher dimensions and cosmic phenomena. In both the cyclic and pyrotic models, brains play a central role in the evolution of the universe. These multidimensional objects serve as the building blocks for understanding cosmic dynamics. In string theory, brains are crucial elements that exist within higher dimensional spaces, providing a framework for comprehending the universe beyond the three dimensions we experience daily. They are not simply passive structures. Rather, they actively shape the forces and processes that drive cosmic evolution. In the pyrotic scenario, the two brains reside in the bulk, a higher dimensional space. When these brains collide, the energy released in the process triggers a new phase of expansion, setting the stage for the universe we observe today. This event is not a one-time occurrence. It is part of a repeating cycle. Each collision leads to a new phase in the universe's evolution, ensuring a dynamic and ever-changing cosmos. Similarly, in the cyclic model, brains are integral to understanding the interactions between different regions of the universe. The model suggests that our universe exists on one brain, while other branes occupy the higher dimensional space. Collisions between these branes can trigger new phases of expansion and contraction, resulting in a series of big bangs and big crunches. With each collision, the universe is reshaped, transitioning from one state to another, creating a continuously evolving and adaptable system. Both models invite us to rethink our place in the cosmos and challenge the very nature of time, space, and the universe's origins. They open up exciting possibilities for understanding the cosmic evolution we observe today and may ultimately provide new insights into the mysterious forces that shape the universe. The interplay between gravity, dark energy, and higher dimensional branes provides a fresh perspective on the cyclical nature of the universe, an idea that has the potential to reshape our understanding of cosmology in the years to come. The relationship between branes and neighboring dimensions unveils profound possibilities, particularly in terms of the fate and evolution of the universe. It offers a potential mechanism for interactions that could generate the energetic conditions essential for cosmic evolution. These higher dimensional objects challenge the traditional concept of a singular beginning, instead proposing a dynamic, ongoing process where the universe continually transforms as our theories evolve. As we explore the notion of branes, we begin to deepen our understanding of the fundamental forces that shape the cosmos. This exploration invites us to reconsider how higher dimensional physics could interface with our three-dimensional experience, offering a new perspective on the forces and structures that govern the universe. The cyclic and ekpyrotic models in particular provide compelling insights into what might have existed before the universe as we know it, and what could lie beyond its current state. These models reject the idea of a single definitive beginning, instead embracing a vision of the universe as part of a much larger, more complex reality. The cyclic model suggests that the universe is involved in an infinite sequence of expansions and contractions. This idea implies that there was no singular moment when the universe began. Rather, it is part of an eternal rhythm. Each cycle could involve different physical laws, creating a constantly evolving cosmic environment. This concept also opens the door to the possibility that our current universe could have emerged from a previous universe, which contracted into a singularity before rebounding in a new Big Bang event. This cyclical nature of the universe challenges conventional ideas of time and existence, proposing that the universe has always been part of this eternal cosmic process. In contrast, the ekpyrotic model offers a different vision. It suggests that our universe was birthed from the collision of two branes within a higher dimensional space. This introduces the idea that there may be more dimensions and structures beyond our familiar three-dimensional universe. The space in which these branes reside could be teeming with other branes and higher dimensional objects, creating a rich tapestry of interactions that we have yet to fully comprehend. Within this framework, the dynamics of brane collisions could account for the birth of our cosmos, suggesting that entities or structures that existed prior to our universe might have played a role in the formation of the universe itself. Both the cyclic and ekpyrotic models raise profound questions about what lies beyond our universe, viewing this mystery through the lens of higher dimensions and cyclical interactions. These models invite speculation that many more universes or branes exist parallel to ours, each governed by its own unique set of physical laws and histories. Instead of imagining a well-defined edge or boundary to our universe, these models suggest a vast multiverse where different regions could operate under varying principles, potentially giving rise to a multitude of cosmic realities. Such ideas open rich discussions about the nature of existence, the concept of time, and the fundamental forces that shape the cosmos. The cyclic and ekpyrotic models reflect a growing desire to understand the universe not as the result of a singular, isolated origin story, but as an ongoing process with roots extending far beyond our current understanding. They provide new avenues for exploration into the deeper mysteries of the universe's evolution and its ultimate destiny, whether that involves an endless cycle or a continuous transformation in a higher dimensional landscape. Support for these models primarily comes from indirect observational evidence rather than concrete, irrefutable proof. Researchers have focused on various cosmic phenomena, searching for patterns or characteristics that align with the predictions made by these theories. One of the most significant areas of interest is the cosmic microwave background radiation, which contains crucial information about the early universe. In the ekpyrotic scenario, the collisions of brains could leave distinct imprints in the cosmic microwave background, potentially manifesting as temperature fluctuations or anomalies that deviate from what traditional inflationary models predict. Some researchers have analyzed the statistical distribution of these fluctuations in the hope of identifying signs of past brain collisions. While clear evidence remains elusive, this area of study continues to be an exciting avenue of research. The cyclic model also attempts to address certain challenges posed by the inflationary model. For instance, predictions about the uniformity and isotropy of the cosmos can be tested through the large-scale distribution of galaxies and other cosmic structures. Patterns in the clustering of galaxies could reveal the effects of repeated cycles of expansion and contraction, suggesting that our universe may have undergone prior cycles. However, the relationship between these observations and the cyclical nature of the universe remains a subject of ongoing study and debate, and much more research is needed before any definitive conclusions can be drawn. In the end, these models not only challenge our understanding of the cosmos, but also expand the boundaries of what we know about the universe, inviting us to look beyond our three-dimensional experience and explore the higher dimensional structures that may govern all of existence. They are pushing the frontiers of scientific inquiry, encouraging us to rethink time, space, and the very nature of the universe itself. Gravitational waves, ripples in the fabric of space-time itself, may hold the key to unlocking some of the most profound mysteries of our universe. The early stages of cosmic expansion, when the universe was still in its infancy, could have generated gravitational waves that would provide critical evidence for the models surrounding the pyrotic or cyclic theories. These models, which propose that the universe undergoes infinite cycles of birth, death, and rebirth, predict the existence of specific gravitational waves, ones that might be generated by brain collisions or interactions. While gravitational wave astronomy is still in its nascent stages, the detection of these signals could lend powerful support to the cyclic and pyrotic frameworks. These models, which challenge traditional views of a singular Big Bang, are being continuously tested through detailed observations of the universe, particularly in the study of cosmic background radiation. However, while definitive evidence remains elusive, the hunt for patterns, fluctuations, and gravitational waves offers an exciting opportunity to gather data that could either reinforce or debunk these alternative models of cosmic evolution. As observational technologies advance and our understanding of theoretical physics deepens, the potential to unravel these cosmic secrets grows, opening up exciting new vistas for our comprehension of the universe's true nature. At the cutting edge of these explorations lies quantum cosmology, a groundbreaking field that seeks to marry the principles of quantum mechanics with the vast expanse of the cosmos. Traditional cosmology has long relied on classical physics and general relativity to describe the universe's structure and evolution. But quantum cosmology offers a bold new vision, suggesting that the universe itself may exhibit quantum properties that are critical for understanding its origins and its fundamental nature. One of the most profound questions quantum cosmology seeks to address is, what came before the Big Bang? Classical models, limited by the concept of singularities, points where densities become infinite, struggle to provide answers about the initial state of the universe. Quantum cosmology, however, offers a fresh perspective by considering the universe's wave function. This wave function, which describes the quantum state of the universe over time, accounts for all possible configurations of the cosmos, offering a probabilistic view of its origins and dynamics. A key proposal in this realm is the no-boundary condition, introduced by the legendary physicist Stephen Hawking and his colleagues. According to this concept, the universe's geometry is finite, yet without boundaries, much like the surface of a sphere. In this model, as the universe transitions from a quantum state to a classical one, the singularities that once defined its early moments are smoothed out. This provides a more coherent understanding of the universe's origins, suggesting that the Big Bang may not have been a singular moment of creation, but part of a far more intricate and continuous process. As scientists continue to probe the quantum nature of the cosmos, new insights are likely to emerge, reshaping our understanding of the universe's past, present, and future. Quantum cosmology stands as a beacon of hope in answering some of the most fundamental questions about the very fabric of existence itself. Quantum cosmology delves into the idea that the universe could follow multiple histories or paths, evolving in a way that defies traditional deterministic models. This fascinating field takes inspiration from the principles of quantum mechanics, where particles can exist in a superposition of different states. Quantum cosmology suggests that the universe itself might also exist in a superposition of multiple possible trajectories, each leading to distinct physical realities. These possibilities paint a picture of a cosmos far richer and more complex than previously thought, offering a radically different perspective on the universe's development. At the core of this exploration is the attempt to merge the small-scale world of quantum mechanics with the vast expanse of cosmology. The goal is to unlock a deeper understanding of the universe's origins, its structure, and the fundamental laws that govern it. This field not only seeks answers to some of the most profound questions about existence, but also serves as a bridge between two seemingly unrelated realms: the microscopic world ruled by quantum phenomena and the enormous cosmic stage of the universe. As researchers continue to refine their models and collect experimental data, quantum cosmology holds the potential to reshape our very understanding of reality. One of its key components is the Wheeler-DeWitt equation, a cornerstone of the theory that describes the quantum state of the entire universe. Developed by physicists John Archibald Wheeler and Bryce DeWitt in the 1960s, this equation was born out of the effort to combine quantum mechanics with general relativity. Its goal is ambitious: to capture the dynamics of the universe at its most fundamental level, exploring how space and time themselves behave under quantum rules. What's truly groundbreaking about the Wheeler-DeWitt equation is that it operates in a domain where our conventional ideas of time and space no longer apply. It offers a way of understanding the universe through a wave function, a mathematical description of all possible configurations of the universe's geometry and matter. This wave function is central to understanding the universe's evolution, linking it to the concept of multiple universes. In quantum mechanics, particles can exist in superposition, meaning they can be in several states at once. Quantum cosmology extends this idea to the universe itself, suggesting that just as particles follow different paths, the universe too could exist in a superposition of different states. The wave function described by the Wheeler-DeWitt equation can represent an infinite array of possible universes, each one distinct, yet all sharing a connection through the fundamental quantum mechanics that underpins them. As we explore this further, the connection to the multiverse theory becomes evident. The wave function of the universe can be thought of as a probabilistic map, suggesting that every possible configuration of space, time, and matter could correspond to a different universe within a broader multiverse. In this view, each branch of the wave function might represent an alternate universe, one with its own unique physical laws, constants, and initial conditions. This idea aligns closely with the many worlds interpretation of quantum mechanics, which proposes that every possible outcome of a quantum event takes place in a separate, branching universe. In essence, the universe doesn't evolve along a single determined path, but rather branches off, creating distinct realities where different outcomes play out. Each universe exists in parallel, with its state dictated by the solution to the Wheeler-DeWitt equation. This equation thus serves as a powerful tool, providing a mathematical foundation for understanding the cosmos in its most elemental form. It opens up the possibility that our universe is just one of many, each of them existing within a vast, interconnected cosmic tapestry. And as research into quantum cosmology continues, we are likely to uncover even deeper insights into the nature of the universe and the fundamental forces that govern it. The wave function of the universe extends these ideas even further. Representing the quantum state of the entire cosmos, it encapsulates every conceivable configuration of matter, energy, and space-time at any given moment. Far from being deterministic, the wave function is probabilistic, suggesting that the universe could be in one of many possible states at any point in time. When an observation or measurement is made, this wave function collapses, resulting in one specific reality, the one we observe. However, according to quantum theory, other possibilities exist in parallel. Each possible outcome of a quantum event could unfold in a different branch of the universe, forming alternate realities that coexist alongside ours. The wave function's implications are profound. It suggests that multiple universes, each with its own unique physical characteristics, might exist simultaneously. These realities could be governed by the same quantum laws as our own, but they might differ in subtle or dramatic ways. Some might harbor different fundamental constants, while others could have entirely different structures, energies, and even forms of life. This notion raises tantalizing questions about the nature of reality itself. If multiple universes are indeed a consequence of quantum mechanics, how do they interact? Do they remain isolated, or might there be points of contact between them? What would these other realities look like, and how might we explore or even interact with them? These questions are not just theoretical. They point toward potential avenues of investigation that could radically alter our understanding of existence. Furthermore, the concept of the wave function of the universe challenges our traditional ideas of time and space. In the quantum cosmology framework, the universe is not a static, unchanging entity, but rather a dynamic system that can evolve in a variety of ways. Our own universe, as we observe it, is just one of many possible expressions of the underlying quantum reality. In this way, quantum cosmology expands the horizons of what we consider possible, inviting us to think beyond the limits of observable reality and explore a broader, richer cosmic structure. As research in this field progresses, it promises to deepen our understanding of the universe, revealing layers of complexity that stretch our imagination. Finally, one of the central challenges addressed by quantum cosmology is the nature of time itself. In classical general relativity, time is treated as a continuous linear progression, unfolding uniformly across the cosmos. However, this perspective breaks down when we approach singularities, such as those proposed to exist at the beginning of the universe during the Big Bang. At these extremes, the familiar concepts of time and space lose their meaning, and the very fabric of reality becomes a mystery. Quantum cosmology provides a fresh perspective on this problem, suggesting that time may not be the simple, linear progression we've always assumed. Instead, it may be more fluid, shaped by the quantum dynamics that govern the universe. Understanding time in this context is one of the most profound challenges of quantum cosmology, and one of the most exciting frontiers of modern physics. Quantum cosmology, a cutting-edge domain of theoretical physics, provides an innovative approach to understanding one of the most elusive questions in science: the nature of time. Central to this exploration is the wave function of the universe, particularly through the framework laid out by the Wheeler-DeWitt equation. Unlike classical models, which treat time as an independent, absolute backdrop for events to unfold, this equation does not treat time as a fundamental variable. Instead, it represents the universe's state as a function of its geometry and matter distributions. This shift suggests that time may not be an intrinsic element in the early universe, but rather an emergent property arising from deeper quantum processes. In this view, time is not a rigid continuum that stands apart from the universe, but a relational aspect that emerges from the interactions between quantum states. A further breakthrough in this area comes from the no-boundary proposal put forth by renowned physicist Stephen Hawking. This model fundamentally reshapes our understanding of the universe's origins, suggesting that the universe has no boundaries in the conventional sense. Without the traditional boundary that marks the beginning of time, the early universe may be better understood as a kind of quantum foam, where the familiar distinctions between time and space dissolve into an undifferentiated state. Here, time and space are not separate constructs, but instead, they coexist and evolve together in a way that defies our ordinary understanding. According to this idea, The universe's development is not a linear progression from a single point in time, but rather it involves a wave function collapsing into distinct states and future possibilities as the universe unfolds. This approach to quantum cosmology opens up intriguing possibilities, including the concept of multiple histories or trajectories of the universe. In this framework, different quantum states give rise to multiple timelines, each representing a potential path the universe might take. This challenges the traditional linear concept of time, suggesting instead that time is intimately tied to the universe's wave function and its complex evolution. In this interpretation, time does not simply march forward in a straight line, but is contingent upon the dynamic interplay of quantum states and their evolution. Quantum cosmology thus offers a radical new perspective on the nature of time, proposing that it may not be a fundamental, pre-existing feature of the universe, but a secondary property that emerges from deeper quantum realities. This paradigm shift not only enhances our understanding of the universe's origins, but also opens the door to profound philosophical questions about the essence of time itself and its place in the fabric of reality. Testing the theories of quantum cosmology requires a blend of empirical observations and intricate experiments that probe the very fabric of our universe. One of the most promising avenues for testing these theories lies in the study of the cosmic microwave background radiation, CMB, the faint afterglow of the Big Bang. The CMB holds critical information about the early universe's conditions, and subtle anomalies in its temperature fluctuations could offer insights into quantum effects that occurred during the cosmos's birth, potentially validating theories of quantum gravity. Gravitational waves also offer an exciting frontier for testing quantum cosmology. First detected in 2015, these ripples in spacetime are produced by some of the universe's most energetic events, such as black hole mergers or neutron star collisions. By studying these waves, scientists are beginning to understand how gravity operates on a quantum level, particularly under extreme conditions where traditional physics may break down. The detection and analysis of gravitational waves could provide vital clues about the quantum properties of gravity, especially in the context of cosmological phenomena that are beyond the reach of conventional experimental methods. Another promising method of testing quantum cosmology theories involves the observation of primordial quantum fluctuations. These tiny fluctuations in the density of matter in the early universe are believed to have played a crucial role in shaping the large-scale structure we observe today. If scientists can detect these fluctuations, perhaps through advanced instruments that measure the distribution of galaxies, or by analyzing the density variations in the cosmic microwave background, it would provide compelling evidence for the influence of quantum mechanics on the universe's earliest moments. This would further reinforce the idea that quantum principles have a profound and lasting impact on the universe's evolution, right from its inception. Through these various empirical approaches, studying the cosmic microwave background, detecting gravitational waves, and observing primordial quantum fluctuations, scientists are slowly but surely piecing together a new picture of the universe, one that challenges our traditional understanding of time, space, and reality itself. Quantum cosmology invites us to rethink not just the origins of the cosmos, but the very nature of existence. And in doing so, it offers one of the most profound intellectual challenges of the modern era. In the not-so-distant future, groundbreaking technological advances are poised to illuminate the deepest corners of our universe. Among the most promising are developments in quantum computing and high-energy particle physics, which could revolutionize our understanding of the cosmos. These emerging tools are not just theoretical. They may one day simulate the conditions of the early universe, unravel the mysteries of fundamental particles, and even bridge the gap between quantum mechanics and gravity. As our observational technologies continue to improve, the once unimaginable frontiers of quantum cosmology are set to expand, opening new pathways for discovery. One of the most intriguing puzzles on this journey of exploration is the enigma of black holes, regions of space that have fascinated both scientists and the public for centuries. While their mysterious nature has long captured the imagination, it is the potential they hold for reshaping our understanding of the universe that truly excites researchers today. One of the most compelling theories suggests that black holes could serve as gateways to other universes, or perhaps even regions beyond our own. The concept is nothing short of extraordinary. Imagine traveling through a shortcut in the cosmos, where the vast distances of millions of light years are compressed into an instant. This idea, which involves wormholes, hypothetical tunnels in space-time, could allow us to bypass the immense expanse of space between distant stars, or even traverse to entirely different universes. These cosmic bridges could be formed through the collapse of massive stars, creating a pathway that connects distant regions of the universe, or even different universes altogether. In the realm of theoretical physics, a particularly intriguing model proposes that when matter falls into a black hole, it might create a kind of bridge to another point in space-time. This is often referred to as the Einstein-Rosen bridge, a term derived from the equations of general relativity. Although this framework allows for the possibility of such connections, the practical implications are far from clear. The chaotic environments surrounding black holes, with their extreme gravitational forces, present enormous challenges. The question remains, could anything survive a journey through such an unforgiving region of space? Moreover, the idea of a black hole acting as a portal to another universe raises profound questions about the very nature of reality itself. Enter the multiverse theory, a bold concept that suggests the existence of multiple, perhaps infinite universes, each with its own set of physical properties, constants, and dimensions. If black holes do, in fact, function as portals, they might connect our universe to others with entirely different laws of physics, opening up a wealth of possibilities beyond what we can currently imagine. Yet, despite the tantalizing potential of these ideas, our current understanding of black holes suggests that any matter or information crossing the event horizon, the boundary beyond which nothing can escape, is lost to the outside universe. This paradox, known as the black hole information paradox, lies at the heart of one of the most perplexing dilemmas in theoretical physics. According to the principles of quantum mechanics, information cannot be destroyed. It can only be transformed. This concept ensures that the state of a quantum system can always be inferred from its outcomes, regardless of what happens to the system itself. As scientists continue to grapple with this paradox, they are exploring innovative concepts such as holographic principles and quantum entanglement in an effort to reconcile these seemingly incompatible frameworks. Theoretical models are evolving, and with each new insight, we edge closer to a deeper understanding of the universe. Yet, for all the progress made, the mystery of black holes remains as compelling as ever, offering both a window into the fundamental workings of the cosmos and a tantalizing glimpse at the possibility of other realms beyond our own. In the coming years, as both technology and our theoretical models continue to advance, black holes will remain a focal point for understanding the complexities of the universe. They could be the key to unlocking answers about our cosmic origins, and perhaps about the very nature of reality itself. The quest for knowledge continues, with each discovery raising more questions, and each new hypothesis pushing the boundaries of what we thought possible. However, when matter crosses the event horizon of a black hole, it seemingly vanishes, becoming irretrievable. The black hole, over time, evaporates due to Hawking radiation, a process that challenges our understanding of the cosmos. But here lies the crucial question. Has the information about what fell into the black hole truly been lost, or does it somehow escape? This paradox, known as the black hole information paradox, has sparked intense debate among physicists for decades. The quest to resolve this mystery has led to the emergence of various proposals and theories. One of the most compelling theories suggests that information is not lost, but instead encoded on the event horizon itself. This idea gave rise to the holographic principle, which proposes a remarkable notion. All the data contained within a three-dimensional region of space can be represented as a two-dimensional structure at its boundary. In other words, even though it may seem as though the information has been swallowed by the black hole, it may still be preserved on the boundary, potentially in a form we don't yet understand. The implications of solving the black hole information paradox stretch far beyond understanding these enigmatic objects. If information cannot truly be lost, then the nature of reality itself could extend far beyond the limits of our observable universe. Some theories posit that resolving this paradox could involve the concept of the multiverse. In such models, information lost in one universe could manifest in another, suggesting a profound connection between parallel realms of existence. When we ponder the fate of information within a black hole, we may not just be contemplating the end of a particle's journey, but also opening the door to alternate realities. These realms might adhere to entirely different physical laws, universes where the laws of physics as we know them don't apply. Thus, the study of the black hole information paradox not only challenges our understanding of these cosmic giants, but also invites us to think about the possibility of multiple parallel universes where different versions of reality exist. As researchers continue to wrestle with these complex ideas, the excitement surrounding the black hole information paradox only grows. Conversations around it are not just about black holes or the fundamental laws of physics. They tap into a deeper, more tantalizing question. What does this paradox reveal about the nature of the multiverse, and what infinite possibilities might it present? The resolution of this paradox could fundamentally alter our understanding of reality. If information can never truly be lost, it could redefine our very concepts of existence, challenging everything we know about the interconnectedness of all things in the cosmos. At the heart of these discussions lies Hawking radiation, a groundbreaking concept introduced by physicist Stephen Hawking in the mid-1970s. Hawking's theory posited that black holes are not entirely black, but instead emit radiation due to quantum effects near their event horizon. This radiation arises from the strange behavior of particle-antiparticle pairs that spontaneously form and annihilate in the vacuum of space. When such a pair forms near a black hole, one of the particles may fall into the black hole, while the other escapes. The escaping particle carries energy away from the black hole, causing it to slowly lose mass over time. This process suggests that black holes can, in fact, evaporate, a startling idea that challenges the traditional view of black holes as eternal and unchanging. If black holes can radiate energy and ultimately disappear, this leads to one of the most pressing questions in modern physics. What happens to the information that was once contained within the black hole? If a black hole evaporates completely, does the information inside it vanish forever, violating the foundational principles of quantum mechanics? Understanding Hawking radiation is crucial to unraveling this puzzle. It presents a potential bridge between the worlds of quantum mechanics and general relativity, two pillars of modern physics that have long remained at odds with each other. As we continue to probe the mysteries of black holes, the study of Hawking radiation offers a tantalizing glimpse into a deeper understanding of the universe, a universe where even the most mysterious objects, like black holes, may not be as immutable as they once seemed. Furthermore, Hawking radiation fuels speculative theories that delve into the very essence of the universe and its enigmatic structure. If black holes can emit radiation and lose mass, could this process give birth to new universes? Some theories speculate that the energy released as Hawking radiation might not just escape into the void, but instead act as the catalyst for the creation of new cosmic structures. In this view, it's possible that isolated regions of space-time could form, each governed by distinct physical laws. These speculative ideas hint at the possibility of a multiverse, a vast, interconnected network of realities, each existing independently, but perhaps connected by these mysterious cosmic gateways. In this perspective, black holes could serve a dual purpose: as destroyers, consuming everything that falls into them, and as creators, sparking the birth of entirely new realms. This dual role might position black holes as facilitators of a cosmic web, a network linking diverse universes, potentially existing within entirely different regions of space-time, each with their own set of laws. As scientists delve deeper into the implications of Hawking radiation, the pursuit of a unified understanding of quantum mechanics and gravity continues to challenge our understanding of the universe. Each insight drawn from the study of black holes refines our comprehension of these bizarre and mysterious objects. while also opening new doors to questions about the very nature of the cosmos and our place within it. The fuzzball theory provides an alternative and deeply fascinating lens through which to view black holes, offering a stark departure from traditional models. Rather than viewing black holes as infinitely dense points of singularity, the fuzzball theory, rooted in string theory, proposes that black holes are in fact complex, stringy structures. String theory, which suggests that the fundamental particles of the universe are not point-like, but instead composed of one-dimensional strings, allows for the possibility that black holes are not singularities, but rather intricate tangled webs of these strings, in a highly excited state. What we perceive as a black hole is not a point where matter is crushed into an infinite density, but rather a collection of strings spread over an enormous region of space. One of the most compelling aspects of the fuzzball theory is its potential resolution of the black hole information paradox. Traditional black hole theory suggests that when matter falls into a black hole, the information contained within that matter is lost forever. But fuzzballs challenge this idea. According to the fuzzball framework, this information is not lost, but encoded within the intricate architecture of the black hole's stringy structure. The fuzzball, in this view, retains the information about what has fallen into it, rather than erasing it entirely. This aligns more closely with the principles of quantum mechanics, which insist that information should never be destroyed, providing a more unified view of gravity and quantum theory. The implications of fuzzball theory stretch far beyond the black hole itself, potentially offering a glimpse into the nature of other universes. If black holes can be understood as fuzzballs, then it opens up the intriguing possibility that they may serve as conduits to other regions of spacetime, or even entirely different universes. The stringy nature of fuzzballs could create pathways or portals through which different properties of spacetime could emerge, potentially suggesting that black holes may be gateways to alternate realities governed by different sets of physical laws. This could mean that black holes are not simply cosmic traps, but rather vital connections in a much larger and more complex multiverse. By expanding our understanding of black holes through the fuzzball framework, researchers might uncover entirely new dimensions in the architecture of the cosmos. The interplay between strings, gravity, and the information encoded within black holes holds the potential to address some of the most profound questions in physics, including the nature of space-time, the future of quantum gravity, and the tantalizing prospect that multiple universes could exist, each with its own unique laws of physics. As the exploration of fuzzballs continues, it invites a rethinking of black hole physics and challenges us to reconsider the very structure of reality itself. Primordial black holes, thought to have formed during the earliest moments after the Big Bang, offer an entirely different and equally captivating window into the conditions of the early universe. Unlike stellar black holes, which emerge from the collapse of massive stars, primordial black holes are theorized to have formed from density fluctuations in the hot, dense matter that filled the early universe. These enigmatic objects, if they exist, could provide crucial insights into the universe's infancy, offering a glimpse of its formation and evolution during a time when additional observations are difficult or impossible. One of the most fascinating aspects of primordial black holes is their potential mass range. They could be incredibly small, with masses much less than that of an asteroid, or they could be as massive as stellar black holes. The existence of smaller primordial black holes, in particular, raises compelling questions related to dark matter. Some theories propose that these tiny black holes could make up a substantial portion of the elusive dark matter that constitutes much of the universe's mass. If such black holes exist in sufficient quantities, they could contribute to the mysterious and invisible substance that makes up around 85% of the universe's mass. Studying primordial black holes, therefore, could not only enhance our understanding of the early universe, but also bring us closer to unlocking the secrets of dark matter, one of the most profound mysteries in modern astrophysics. In exploring these diverse and complex ideas, from Hawking radiation to fuzzballs, primordial black holes, and the multiverse, we are challenged to rethink what we know about space, time, and the very fabric of the cosmos. Each discovery, each theory, is another step toward a deeper understanding of the universe and our place within it. Primordial black holes, which may have formed in the early universe, hold a fascinating potential to unlock secrets not only about our cosmos, but also about other realities beyond our own. If these ancient objects were created under a variety of conditions or at different mass ranges, they could provide valuable insights into the possibility of multiple universes. Imagine a reality where our universe is only one of many, each with distinct physical laws and principles. This speculative scenario, known as the multiverse, suggests that the cosmos we observe could be just a single thread in a vast, multifaceted web of realities. The formation of primordial black holes might, in fact, be intertwined with the origins of other cosmic structures. These black holes could act as bridges to alternate regions of space-time, potentially opening doors to realms where the laws of physics differ from those we know. Researchers are delving into how these dense objects could relate to cosmic inflation, an event that occurred in the first moments after the Big Bang, when the universe expanded at an unimaginable speed. By understanding how density fluctuations in the early universe gave rise to primordial black holes, scientists may be able to refine their theories on inflation and large-scale cosmic structures, such as galaxies and clusters. As the study of primordial black holes deepens, it not only enhances our understanding of the early universe, but also fuels broader conversations about the possibility of other realities. It pushes the boundaries of our current knowledge, challenging us to reconsider the very nature of existence and reality. The simulation hypothesis? Is reality just an illusion? In parallel with these cosmological theories, the simulation hypothesis presents a thought-provoking notion. What if our reality, our universe, the stars, the galaxies, and even our very existence, is nothing more than a highly advanced computer simulation? This concept suggests that a sufficiently advanced civilization could create simulations so realistic that the inhabitants within them would be unaware of their artificial nature. This idea has gained significant traction in both popular culture and philosophical discourse, especially in light of rapid advancements in technology and virtual reality. The argument supporting the simulation hypothesis revolves around probability. If an advanced civilization has the ability to create multiple simulations, it's likely that the number of simulated realities would far exceed the number of real universes. In other words, the odds that we exist in the original base reality are becoming slimmer by the day. With countless simulated worlds populated by beings whose experiences seem just as real as our own, it's possible that we are living in one of these virtual realities. This idea challenges us to rethink everything we know about existence, consciousness, and our place in the universe. Moreover, the simulation hypothesis aligns with the concept of the multiverse. If our universe is just one of many simulations created by advanced beings, it implies a vast and varied landscape of realities, each with different physical laws, histories, and even evolutionary paths. In this sense, the multiverse extends beyond the traditional cosmological interpretations, where universes emerge from different events or conditions. It now includes the possibility of realities created through intelligent design, realities that may exist purely for exploration, study, or even entertainment. Exploring the simulation hypothesis also encourages us to question the very foundations of our understanding of physics. If the universe is a simulation, then our grasp of the laws that govern reality could be nothing more than a subset of a much larger underlying framework. This opens up profound philosophical questions about the nature of consciousness and existence itself. If we exist within a simulation, are we merely characters in a program, or do we possess free will? How do we define what is real when the very nature of reality may be subject to the whims of an external intelligence? The layers of reality, a simulation within a simulation. If we entertain the possibility that our universe is indeed a simulation, it suggests that there could be multiple layers of reality, each one a different simulation or level of existence. The civilization capable of creating such simulations would need to harness immense computational power to construct intricate environments, simulating everything from subatomic particles to the evolution of galaxies. As technology progresses, our own advances in virtual reality and artificial intelligence give us a glimpse into how such simulations might operate. We are already creating increasingly sophisticated virtual worlds that are difficult to distinguish from reality. What if we are simply participants in a more advanced simulation, unaware of the greater reality in which we reside? In this context, the universe we experience might be a highly detailed simulation designed for any number of purposes: scientific experimentation, entertainment, or even education. The inhabitants of these simulated worlds, us for example, would live out their lives believing in the reality they experience, unaware that they are part of a larger artificial framework. This raises profound questions. What is the purpose of this simulation? Are we being studied, observed, or tested? And what happens when we start to question the very nature of our existence? If we are indeed living within such a simulation, it forces us to reconsider the fundamental nature of our world. What is the relationship between the creators of the simulation and the simulated beings who inhabit it? And what are the implications for free will, consciousness, and our understanding of the universe? As scientists, philosophers, and technologists continue to explore these ideas, the simulation hypothesis serves as a bridge between theoretical physics, cutting-edge technology, and age-old questions about the meaning of life and our place in the cosmos. The concept that our universe could be a simulation within a larger, more fundamental reality invites us to expand our thinking beyond the boundaries of conventional science. It challenges us to rethink everything we know about the nature of existence and the possibility that our perception of reality is far more malleable and mysterious than we could ever have imagined. Moreover, within the broader framework of a simulated reality, multiple simulations might coexist, each with its own set of unique physical laws and experiences. These simulations could operate under different rules, creating a vast and diverse array of realities, ranging from our universe to countless others, each unfolding in its own distinct way. This aligns with the concept of the multiverse, where universes emerge from varying conditions or histories, each one shaped by its own set of circumstances. Together, these ideas offer a compelling vision of a reality far more complex and interconnected than we've ever imagined. The possibility that our universe could be a simulation within an even grander reality fundamentally challenges how we perceive existence and urges us to reconsider the very fabric of everything we experience. The notion of simulated universes brings with it a cascade of philosophical and scientific questions that challenge our understanding of reality, consciousness, and existence. One of the most profound philosophical inquiries raised by this hypothesis is the nature of existence itself. If our universe is, in fact, a simulation, it leads us to ask, what does it mean for something to be real? Are our emotions, thoughts, and experiences any less valid if they are occurring within a constructed reality? This question pushes the boundaries of traditional metaphysics, inviting us to reconsider the essence of reality and to question whether what we perceive as real is truly so, or merely a projection of something larger and unseen. The simulation hypothesis also sparks debates about free will and determinism. If our lives are dictated by predetermined algorithms programmed by an external creator, do we truly possess free will? Alternatively, if free will does exist within this framework, how do we reconcile it with the limitations of a programmed reality? This dilemma complicates our understanding of moral responsibility, as concepts like right and wrong might change drastically in a world where outcomes are scripted, or where the rules of the simulation can be altered at will. How do we assign moral accountability if our decisions and actions are determined by an outside force? This shifts the conversation into the realm of ethics and human agency and creating a deeper dialogue about autonomy within a potentially deterministic world. From a scientific standpoint, if the simulation hypothesis holds water, it would call into question the very foundations of physics and cosmology. The laws that govern our universe, including quantum mechanics and relativity, might not be immutable truths, but rather mere constructs within a larger computational framework. Such a shift would require a radical rethinking of how we approach the study of the universe. Scientists would need to devise new methods of inquiry, looking not just at physical phenomena, but also at the underlying code or principles that structure these phenomena. This could lead to the emergence of entirely new scientific paradigms that blend technology, consciousness, and fundamental cosmic laws, exploring how these concepts interrelate within a potentially simulated environment. Furthermore, the existence of simulated realities raises significant questions about consciousness itself. If consciousness can emerge within a simulation, what does this tell us about the source of consciousness in general? Are the conscious beings within a simulation truly aware, or are they sophisticated imitations of consciousness? This contemplation challenges our assumptions about artificial intelligence and the potential for machines to develop true self-awareness. As technology continues to advance, it forces us to ask, can a machine ever truly be conscious? And if so, what ethical obligations do we have to such entities? These questions not only provoke philosophical reflection, but also impact real-world debates surrounding artificial intelligence and robotics, particularly in terms of their potential to mimic or even surpass human-level consciousness. As we continue to explore these themes, the conversation becomes increasingly interdisciplinary, bridging the realms of philosophy, science, technology, and ethics. Through this dialogue, we can begin to form a deeper understanding of our place in the cosmos, challenging our notions of reality and existence, and questioning what it truly means to be alive within a universe, whether simulated or not. Detecting whether our universe is a simulation is, of course, an immensely complex challenge. However, intriguing methods of investigation have emerged within both philosophical and scientific circles. One compelling idea is to search for computational limitations embedded within the universe itself. Proponents of the simulation hypothesis argue that, like any digital simulation, our universe may display anomalies or discontinuities that suggest it is not a perfectly continuous reality. For instance, physical phenomena that appear quantized, such as the discrete energy levels in atoms, might point to the presence of pixels or resolution limits in the simulated universe. Another avenue of investigation could involve looking for mathematical patterns or inconsistencies that appear more akin to programming shortcuts than to natural processes. If the universe operates based on rules resembling coding principles, researchers might eventually uncover traces of these structures through highly precise measurements in fields like particle physics or cosmology. Inconsistencies in the behavior of fundamental particles or unexpected correlations in cosmic microwave background radiation could serve as signals that point to the simulated nature of reality. As we push the boundaries of our scientific tools and methodologies, we may eventually uncover hidden patterns that reveal the code behind the cosmos. In the end, the question of whether we live in a simulation remains one of the most profound mysteries of our time. Whether through philosophical inquiry or scientific exploration, the search for answers to this question may lead us down a path of discovery that fundamentally reshapes our understanding of reality, existence, and the nature of consciousness itself. As technology continues to evolve, particularly in the realms of quantum computing and artificial intelligence, the possibility of exploring the nature of our own reality intensifies. Advancements in these fields offer the potential to probe whether we are living within a simulation, a concept that has captivated the minds of scientists, philosophers, and technologists alike. With the development of increasingly sophisticated algorithms and simulations, researchers may begin to notice parallels between their own artificial creations and the universe around us. These observations could illuminate how a far more advanced civilization might design and construct a simulation, an artificial reality that mirrors the features of our own. The question of whether we live in a simulated universe is no longer confined to the realm of science fiction. It is being tackled with growing seriousness as quantum mechanics, AI, and computational power evolve. A critical aspect of this exploration lies in understanding the limits and patterns of our universe. As scientists push the boundaries of technology, they are faced with questions about how complex simulations might operate, what limits they could encounter, and how those limits might align with what we perceive in our reality. Furthermore, the philosophical and theoretical frameworks that underlie our understanding of the universe provide important pathways to investigating the possibility of a simulated existence. One key area of exploration is the nature of consciousness and its role in shaping reality. Quantum mechanics suggests that observation plays a significant role in determining outcomes at the subatomic level. If consciousness truly influences the way we perceive and interact with the world, it opens up the possibility that our perceptions could be manipulated within the confines of a simulation. This presents a profound challenge to our understanding of reality, urging us to reconsider the very nature of what we observe and experience. Could our perceptions be the result of carefully constructed algorithms designed by entities beyond our comprehension? The intersection of physics, technology, and philosophy offers an interdisciplinary approach to the detection of a simulated universe. The tools we have at our disposal, advanced computing, quantum experiments, and philosophical inquiry, can collectively deepen our understanding of reality. Though the idea of discovering whether we live in a simulation may seem elusive, the exploration of these questions could spark innovative research that might eventually shed light on the true nature of our existence. By expanding the boundaries of what we think is possible, we may uncover hidden truths that reveal the very framework of our universe. However, the very notion of creating simulated universes brings with it a host of ethical considerations that demand careful examination. As we delve into the potential of simulating intelligent life, we are forced to confront fundamental moral questions about the treatment of these beings. If a simulation were to include sentient life, beings capable of thought, emotion, and suffering, how would we treat them? Are these entities entitled to the same rights and ethical considerations as real-life conscious beings? Could their experiences, their joy, pain, or autonomy matter if they exist only as constructs in a simulation? This line of inquiry challenges our understanding of consciousness and compels us to reflect on the responsibilities we might hold towards entities that bear similarities to us. The ethical issues become even more complex when we consider the dynamics of power and control within simulated environments. Those who create and maintain these simulated worlds would hold immense power, able to manipulate the very fabric of the reality within their design. This could result in significant disparities of control and authority, where the creators of simulations hold absolute dominion over the lives of their simulated inhabitants. Such power dynamics echo the ethical concerns present in our own world, questions of social structures, oppression, and exploitation. The creators of simulated universes, much like the authorities in our real world, would have a profound responsibility not only to design but to ethically steward the beings and environments within their creations. Moreover, the ability to simulate different cultures, societies, or even entire historical events raises additional ethical dilemmas. If a creator were to simulate a society enduring trauma, pain, or suffering for the sake of observation or study, what moral justification could they offer for such an act? This becomes particularly troubling when we consider the potential for simulating atrocities, whether historical events such as wars, genocides, or social collapses. Would it be ethically permissible to run simulations of such tragedies in order to study the outcomes or for the mere sake of entertainment? The risk here is that the creators and observers of such simulations could become desensitized to real-world suffering, leading them to view moral questions through a detached clinical lens. In the worst-case scenario, the ability to create simulated worlds could lead to a dangerous erosion of ethical considerations. Those responsible for the design and management of these simulations might begin to lose sight of the real-world implications of their actions. As the line between reality and simulation blurs, there is a risk that the creators could become complacent or even callous about the lives they are manipulating. This desensitization could result in a failure to address the ethical issues that arise, both within the simulation and in the real world. The exploration of simulated realities, then, is not only a scientific and philosophical inquiry, it is also a deeply ethical one. As we approach the frontier of creating our own artificial worlds, we must grapple with the profound moral questions that arise. In the end, the prospect of creating simulated universes compels us to confront the very nature of existence, our responsibility to sentient beings, and the ethical limits of our creativity. What does it mean to create life, and more importantly, what does it mean to shape the reality in which those lives exist? The distinction between the creator and the creation inevitably sparks profound philosophical inquiries about identity and existence. At the core of these questions is the nature of reality itself. which, when viewed through the lens of a simulated construct, begins to blur the boundaries between creator and the beings formed from their design. Are these creators to be seen as gods? If so, what ethical responsibilities must they bear? Such reflections propel us into a deeper examination of our own humanity and ethical obligations. They compel us to consider frameworks that can guide our behavior should we ever gain the power to create complex, meaningful simulated worlds. This contemplation calls for a rigorous approach to the design and manipulation of simulated environments, grounded not in mere curiosity, but in responsibility, compassion, and respect for consciousness itself. These ethical principles should not be confined to theoretical simulations alone. They echo the values that must govern our actions in the real world. If we as creators possess the ability to shape realities, we must confront our moral duty to the sentient beings that inhabit these constructs, just as we must consider the implications of our actions in the tangible universe. String theory, which offers a radical shift in our understanding of the cosmos, delves into this very idea by challenging our perception of the fundamental nature of matter. It proposes that the smallest building blocks of the universe are not point-like particles, but rather one-dimensional entities known as strings. These strings, vibrating at different frequencies, manifest as different particles, thus unifying the fundamental forces and constituents of the universe into a coherent whole. One of the most captivating facets of string theory is its suggestion of additional dimensions that extend far beyond the familiar four of space and time. In order to maintain mathematical consistency and accommodate the myriad vibrational patterns of strings, string theory posits that the universe must possess extra spatial dimensions. While we experience three dimensions of space, length, width, and height, string theory hypothesizes that 6 or 7 more dimensions exist, curled up so tightly that they remain imperceptible to our current methods of observation. These compactified dimensions, though minuscule, potentially smaller than even subatomic particles, hold profound implications for the forces that shape our universe. The structure and configuration of these extra dimensions could govern the types of particles produced by string vibrations and influence the strength and interactions of fundamental forces such as gravity and electromagnetism. Depending on how these additional dimensions are arranged, they could even explain some of the long-standing mysteries and inconsistencies observed in both particle physics and cosmological studies. In essence, string theory proposes a unified framework that redefines how we perceive reality, intertwining the visible and invisible, the known and unknown, and inviting us to explore not only the universe's fundamental nature, but also our own role within it. Through this lens, the questions of creation, power, and ethical responsibility transcend beyond philosophy into the very fabric of how we understand existence itself. The existence of additional dimensions could suggest a far richer and more intricate cosmos than we ever imagined. If these extra dimensions truly exist, they may play pivotal roles, potentially influencing the behavior of other critical phenomena like black holes and even the very fabric of space-time itself. According to some of the more advanced interpretations of string theory, the dynamics of these hidden dimensions could offer crucial insights into pressing cosmological mysteries, such as the true nature of dark matter and dark energy. As physicists continue to explore the vast implications of string theory and its higher dimensional framework, the possibility of a multidimensional universe grows ever more tantalizing. This concept promises not just a deeper understanding of the fundamental aspects of reality, but also opens up exciting new pathways toward unifying the various forces of nature. These ideas invite researchers to rethink everything we once believed about the universe, challenging our assumptions about the nature of reality, and urging us to expand our perception of what might lie beyond our known world. One of the most groundbreaking frameworks that delves into the potential of higher dimensions is Kaluza-Klein theory. This theory represents an innovative attempt to reconcile general relativity with electromagnetism by introducing extraspatial dimensions beyond the familiar 3 and 1 temporal dimension. Originally developed in the early 20th century by mathematician Theodore Kaluza and later refined by physicist Oscar Klein, Kaluza-Klein theory was initially conceived as a way to unify gravity and electromagnetism in a more elegant and cohesive manner. The core idea of Kaluza-Klein theory lies in the incorporation of a fifth dimension, one that is compactified, meaning it is folded into a tiny circle and thus imperceptible in our everyday experiences. This compactification allows for the existence of additional physical phenomena that do not interfere with the four-dimensional space-time we perceive. In this framework, the extra dimension does not disrupt the fabric of space-time, but rather alters the equations governing the motion of particles, leading to the emergence of electromagnetic interactions as a natural extension of gravitational theory. The consequences of Kaluza-Klein theory extend far beyond the unification of gravity and electromagnetism, reaching into the realm of higher dimensional physics and the exploration of multiple universes. By suggesting that our universe may be embedded within a higher dimensional framework, Kaluza-Klein theory naturally invites speculation about parallel or alternate universes. In certain versions of the theory, different compactification schemes could lead to universes governed by distinct physical laws, with variations in the strengths of forces or even the types of particles that exist. This opens up the possibility of multiple universes, each shaped by the unique geometric configuration of the extra dimensions. Moreover, the extra dimensions proposed by Kaluza-Klein theory could provide essential clues to understanding the fundamental forces that govern the cosmos. In the broader context of string theory, which also incorporates higher dimensions, these extra spatial dimensions serve as crucial building blocks for explaining previously unfathomable properties of particles and forces. This interconnectedness emphasizes the role of extra dimensions in modern physics, compelling researchers to consider cosmological scenarios where multiple universes might emerge from different arrangements of these dimensions. In essence, Kaluza-Klein theory marks an important early effort to unify gravity with the other fundamental forces through the lens of higher dimensions. It has paved the way for further exploration into the nature of reality, the potential existence of multiple universes, and the intricate relationships that govern the underlying structure of the cosmos. As physicists continue to explore these ideas, Kaluza-Klein theory remains a vital stepping stone in the quest to unravel the complexities of the universe. The notion of objects or even beings existing in higher dimensions presents fascinating possibilities for how we understand reality beyond our conventional experiences. In our daily lives, we perceive a three-dimensional world, one defined by length, width, and height, along with a fourth dimension, time. Yet, if additional dimensions exist beyond our awareness, they could fundamentally alter how we comprehend the very fabric of existence, urging us to rethink the boundaries of what is possible and opening up new realms of understanding for what might lie beyond our sensory limitations. However, if additional spatial dimensions indeed exist, as proposed by theories such as string theory and Kaluza-Klein theory, the implications are staggering. Beings or entities that occupy these dimensions could experience reality in ways that are fundamentally alien to us. Their perceptions of the world around them would transcend the limits of our understanding. Take, for example, the way we experience the universe in three spatial dimensions. We move freely within this space, but imagine a being that exists in a higher dimensional world. To them, movement could seem impossible to us, as they might navigate in ways that defy our comprehension. Such beings could potentially pass through solid objects or perceive relationships between space and matter that are hidden from our senses. This idea is often explained using the analogy of a two-dimensional being trying to understand the three-dimensional world. Picture a flat creature that lives in a two-dimensional plane. This creature would only be able to perceive the edge of a solid sphere, seeing it as a simple circle, unaware of the sphere's depth or volume. Similarly, entities existing in higher dimensions would experience our universe's intricate structures in a way that we simply cannot visualize. If such beings interacted with our three-dimensional world, their perception of reality would likely encompass multiple viewpoints simultaneously. They could see our universe not as a simple three-dimensional space, but rather as a slice or projection of a much more complex and higher-dimensional reality. They might have the ability to observe all possible configurations of particles, forces, and energies at once, an insight into the nature of existence that remains out of our reach. Moreover, their understanding of time could be vastly different from our own. For us, time is a linear progression, an irreversible flow from past to present to future. But higher dimensional beings might experience time as a multidimensional entity, viewing it not as a sequence, but as something far more complex. This radical shift in the way they perceive time could lead to an entirely new understanding of causality, existence, and even the concept of life itself. The very existence of these higher dimensional entities challenges our deepest assumptions about consciousness and the nature of being. If they were to interact with our world, what kind of consciousness would they possess? Would they even be aware of their dimensionality, or would they exist in their own reality, isolated from the limitations that define our existence? These questions invite us to reimagine intelligence, consciousness, and existence itself, pushing the boundaries of what it means to be alive and aware in the context of a potential multiverse. The exploration of higher dimensional beings isn't just a thought experiment. It brings us face to face with some of the most profound questions about the universe and our place within it. The pursuit of understanding is more than an academic exercise. It is the key to unlocking the mysteries of reality itself. By investigating these complex concepts, we challenge the limits of imagination and science, encouraging ongoing dialogue and exploration into the very nature of existence. In theoretical physics, the quest for experimental evidence of higher dimensions is an ongoing and complex endeavor. While direct proof remains elusive, several approaches are providing tantalizing glimpses into what might be. One prominent avenue is particle physics, particularly in large-scale particle accelerators such as the Large Hadron Collider. Here, researchers are exploring the potential existence of particles or interactions that could arise due to the presence of extra dimensions. In these extreme conditions, the behavior of fundamental particles might reveal specific signatures that hint at the existence of higher dimensional space. For instance, if additional dimensions exist, they could influence how fundamental particles behave at high energy collisions, possibly creating phenomena like mini black holes. The detection of these or other unusual particles could offer key evidence that higher dimensions are at play. Scientists are also keenly watching for anomalies in these particle collisions that could suggest the presence of hidden spatial dimensions beyond our three-dimensional experience. Another cutting-edge approach is the study of gravitational waves, the ripples in spacetime caused by massive astrophysical events such as colliding black holes. Detecting these waves through observatories like LIGO and Virgo opens up an entirely new frontier of study, one where the very fabric of spacetime is examined in unprecedented detail. Should gravitational waves reveal unexpected patterns or anomalies, it might suggest the influence of higher dimensions on our universe's structure, stretching beyond the limits of general relativity. Cosmic observations also offer clues about the potential existence of higher dimensions. Dark matter and dark energy, the unseen forces that seem to govern much of the universe, might be explained in part by extra dimensions. Some models propose that the interactions between ordinary matter and dark matter could be drastically different if additional dimensions are involved. As scientists probe the distribution and behavior of dark matter in galaxies, they are working to distinguish between the predictions of standard physics and the theories that incorporate higher dimensions. Thus, the search for evidence of higher dimensions is not merely an academic pursuit. It is a key to understanding the true nature of our universe, its forces, and its fundamental building blocks. Through these efforts, we may one day gain a glimpse into the hidden realities that lie just beyond the reach of our three-dimensional experience. The study of cosmic inflation, the rapid expansion of the universe right after the Big Bang, presents one of the most profound mysteries in modern physics. This explosive period of growth raises key questions about the mechanisms that drove the universe's rapid acceleration. While traditional models have provided answers, new theories that explore the possibility of higher dimensions offer alternative insights into the nature of this event. These theories suggest that there may be additional hidden dimensions beyond the four that we can perceive, potentially leaving behind traces in the cosmic microwave background radiation. These faint signals, though difficult to detect, could serve as indirect evidence that extra dimensions exist. As of now, solid experimental proof of higher dimensions remains elusive. However, the increasing interest and research in this area are paving the way for future breakthroughs. The more we learn about the fabric of the universe, the more it becomes clear that our current understanding is only the beginning. With advancements in technology and further developments in theoretical physics, the search for the elusive signatures of higher dimensions will continue, possibly reshaping our comprehension of reality. One of the most captivating aspects of higher dimensional theories is their potential to explain phenomena like dark matter and dark energy, two of the most perplexing components of the universe. Traditionally, we understand our reality through three spatial dimensions, with time serving as a fourth. However, theories like string theory suggest the existence of additional dimensions that are not directly observable. These extra dimensions could provide fresh perspectives on the origin and behavior of dark matter and dark energy. For instance, instead of being composed of unknown particles, dark matter might be the result of gravitational influences from another dimension. In this scenario, dark matter would not be made of particles that we have yet to detect, but instead, it could be the manifestation of gravitational effects originating from matter residing in a higher dimensional space. This theory could help explain why galaxies rotate at such high speeds, a mystery that has baffled scientists for decades. The gravitational pull we associate with dark matter may, in fact, be the result of forces exerted by unseen dimensions, offering a far simpler explanation for this cosmic puzzle. Similarly, the enigmatic force known as dark energy, responsible for the accelerating expansion of the universe, could also be explained by higher dimensional theories. If additional spatial dimensions exist, the energy pushing the universe apart may not originate solely from within our three-dimensional space. Instead, it could be a natural consequence of the geometry and dynamics of a higher dimensional universe. This would suggest a deep connection between the structure of space-time and the expansion of the cosmos, far beyond what our current models allow us to grasp. Exploring higher dimensions not only enhances our understanding of dark matter and dark energy, but also opens up a wealth of possibilities for new discoveries. The interplay between these dimensions could reveal connections between forces that we currently think of as separate. As physicists delve deeper into the mysteries surrounding these phenomena, it is likely that our conceptual framework of reality will evolve, unveiling a universe far more intricate and interconnected than we ever imagined. Equally fascinating is the phenomenon of quantum entanglement, which hints at the possibility of connections between our universe and others. At its core, quantum entanglement describes a process by which two or more particles become interconnected, such that the state of one particle instantaneously affects the state of another, regardless of the distance separating them. This bizarre behavior challenges traditional notions of communication and locality, suggesting that information can be exchanged across vast distances in ways that defy our conventional understanding of space and time. In the context of the multiverse, a collection of possible universes, quantum entanglement could serve as a bridge linking these realities. If entangled particles originated from different universes, a change in one would immediately affect the other, regardless of the physical distance between them. This interconnectedness implies that the boundaries between universes might not be as rigid as we once thought, suggesting that there may be a shared reality that transcends the isolated conditions we experience in our own universe. As our understanding of quantum mechanics and the nature of reality evolves, the possibility of exploring connections between universes becomes ever more tantalizing. Theories of higher dimensions, quantum entanglement, and the multiverse are beginning to converge, offering the potential for a profound transformation in our understanding of the cosmos. What lies beyond the limits of our current perception may be far more extraordinary and interconnected than we can even imagine. Moreover, some physicists speculate that entangled states could transcend the boundaries of our own universe, suggesting that quantum information might flow seamlessly between multiple universes. In this scenario, each entangled state could represent not just a connection within our universe, but also an intricate link to others that coexist alongside ours within a vast multidimensional framework known as the multiverse. This concept brings with it profound implications for our understanding of reality, as it proposes that events in our universe might not be isolated. They could be influenced by or perhaps influence occurrences in parallel worlds. The exploration of quantum entanglement, with its potential to unravel these cosmic connections, represents one of the most exciting frontiers in modern physics. As researchers continue to decode the enigmatic complexities of quantum mechanics, the ramifications for how we perceive the structure of the universe, and even the possibility of existence beyond our own, invite us to reconsider the very fabric of reality. What we may once have seen as a singular, isolated universe could in fact be part of a grander, interconnected quantum system. This new perspective challenges us to think about the universe as a vast, dynamic web of interacting forces, where what happens in one part of the cosmos might resonate in others, even across separate dimensions. At the heart of this theoretical leap is quantum decoherence, a fundamental process that bridges the gap between the bizarre world of quantum mechanics and the everyday reality we perceive. In the quantum realm, particles can exist in a state of superposition, meaning they can occupy multiple states at once, something that seems impossible in the classical world. However, when a quantum system interacts with its environment, this delicate superposition collapses. The result is a definite outcome, where the once multiple possibilities converge into one. This is why, in the macroscopic world, we never witness the strange behaviors predicted by quantum mechanics, even though they are intrinsic to the microscopic scale. Quantum decoherence's relationship to the concept of parallel realities is particularly captivating. Many interpretations of quantum mechanics suggest that all potential outcomes of a quantum event occur, leading to the creation of multiple universes, each representing a different path taken by a quantum system. According to this view, every interaction that leads to decoherence effectively splits the universe, with each reality evolving independently, like branches sprouting from a single tree. Thus, what we perceive as a singular universe is actually a rich and complex tapestry, where countless potential outcomes are realized in parallel worlds. Decoherence, in this sense, provides the necessary mechanism for how these parallel realities can coexist without interfering with one another. Once a quantum system becomes entangled with its environment and undergoes decoherence, the different possible outcomes no longer interact. Each reality develops its own distinct timeline, ensuring that the many possible worlds remain separate, even if they originated from the same initial quantum state. This framework suggests the existence of a multiverse, where the outcomes of quantum events give birth to entirely different realities. But the implications of quantum decoherence don't stop at the realm of theoretical physics. They extend far beyond, touching fields like quantum computing and information theory. Decoherence highlights one of the biggest challenges in harnessing the unique properties of quantum systems for technological advancements. In quantum computing, for instance, maintaining quantum coherence is essential for processing and storing information in ways that classical systems cannot replicate. As researchers continue to delve deeper into the role of decoherence in quantum mechanics, their findings could reshape our understanding of not only the universe's structure, but also the potential of quantum technologies to revolutionize the future. The many interacting worlds interpretation of quantum mechanics offers a particularly intriguing perspective on parallel universes. Departing from traditional interpretations, such as the Copenhagen model, it eliminates the need for wave function collapse whenever a measurement is made. Instead, it suggests that all possible outcomes of quantum events are realized simultaneously, each in its own distinct yet interconnected branch of existence. According to this interpretation, when a quantum event occurs, say, when a particle's position is measured, rather than collapsing into a single state, the universe splits into multiple realities, each representing a different outcome of that quantum measurement. For instance, if a particle has a 50% chance of being in one state or another, the many interacting worlds interpretation proposes that both outcomes occur, but each in its own separate reality. These parallel universes, while distinct, are far from independent. They interact with one another in ways that are still not fully understood, creating a cosmic dance of possibilities and outcomes that extends far beyond our observable universe. The concept of these interacting worlds challenges not only our understanding of quantum mechanics, but also our very perception of reality itself. As scientists continue to explore these theories, they may unlock new ways to think about space, time, and existence, potentially leading to discoveries that redefine our place in the cosmos. However, these branches do not drift apart entirely. They maintain the potential for interaction through the fascinating phenomenon of quantum entanglement. What makes the many interacting worlds interpretation of quantum mechanics especially intriguing is the idea that these parallel worlds are not isolated. Instead, they can influence each other. This interaction may give rise to interference patterns similar to those observed in quantum systems, suggesting that the behavior in one branch of reality could ripple through and impact another. Such a scenario implies a vast, intricate web of interconnected universes, an existence where every choice, every action, and even every chance encounter might resonate across a broader tapestry of reality. This interpretation offers a profound shift in how we perceive our place in the universe. Rather than living in a single linear timeline, we are now part of a grand, expansive multiverse, each decision unfolding new pathways that lead to multiple, simultaneously existing realities. In this view, we become more than mere observers of a fixed reality. We are active participants in a dynamic, multidimensional cosmos. This enriches our understanding of quantum mechanics, suggesting that it may not only govern the microscopic world of particles, but also the very fabric of existence itself, intertwining our experiences with infinite parallel histories. Experimental evidence supporting the cosmic reach of quantum effects further blurs the boundaries between the quantum and the astronomical. One of the most striking examples is the cosmic microwave background radiation, the faint, lingering glow from the Big Bang. Tiny temperature fluctuations within this radiation, as captured by instruments like the Wilkinson Microwave Anisotropy Probe, offer a glimpse into the quantum fluctuations of the early universe. These subtle variances are not just minor quirks. They are the seeds that would eventually blossom into the large-scale structures we observe today: galaxies, star clusters, and vast cosmic networks. Equally compelling is the evidence from large-scale entanglement and quantum coherence in cosmological settings. Research into the behavior of distant light sources reveals that quantum effects can persist over vast distances, challenging the classical view of separability in physics. Experiments with entangled photon pairs, for instance, suggest that quantum entanglement remains intact even when the particles are separated by great distances, a phenomenon that defies classical understanding. The persistence of quantum states across such massive separations is not only fascinating, it points to a deeper, more profound connection between distant parts of the universe. The study of celestial phenomena, such as supernovae and neutron stars, provides additional insights into quantum mechanics at a cosmic scale. These extreme environments create conditions where quantum behavior dominates. Neutron stars, composed primarily of neutrons locked in intricate quantum states, provide a direct example of how quantum mechanics governs the behavior of dense matter. The pulses emitted by these stars, electromagnetic signals that sweep across the cosmos, imply that quantum processes are at play in their rotation and radiation emission. This connection between quantum mechanics and astrophysical phenomena underscores the central role of quantum effects in shaping the cosmos. Another fascinating frontier lies in the study of gravitational waves. Experiments like those conducted by the Laser Interferometer Gravitational Wave Observatory, LIGO, seek to detect ripples in space-time caused by events like black hole mergers. These experiments rely on incredibly sensitive quantum technologies, bridging the realms of quantum mechanics and general relativity. The precise measurements required to capture gravitational waves highlight the undeniable interplay between the microscopic quantum world and the vastness of the universe, reinforcing the idea that quantum mechanics is not confined to tiny particles, but is woven into the very fabric of space-time. This body of evidence continues to inspire ongoing research into the connections between quantum physics and cosmology, revealing a universe far more interconnected than we once imagined. It suggests that the fundamental principles of quantum mechanics stretch across the cosmos, influencing the grand scale of galaxies, the behavior of light, and even the earliest moments of the universe's existence. One particularly captivating idea that emerges from these insights is the possibility of using quantum entanglement to communicate or interact with other universes. The concept of entanglement allows particles to become deeply interconnected, such that the state of one particle instantaneously affects the state of another, regardless of distance. This property raises intriguing questions about the potential for entangled particles to facilitate communication across parallel universes, especially within frameworks that propose the existence of a multiverse. In theory, if we could create entangled pairs of particles across different branches of the multiverse, changes to one entangled particle might instantly influence its counterpart in another universe. This suggests the possibility of a kind of interuniversal communication, where information could flow freely between parallel realities. While still speculative, this concept hints at new ways to understand the very nature of information, existence, and the connections between different worlds. Another concept worth exploring is quantum teleportation, the process by which the quantum state of a particle is transferred to another particle without the particle itself being physically moved. This phenomenon has already been demonstrated in controlled laboratory conditions over short distances, but what if it could be extended across universes? If we could find a method for quantum teleportation between different branches of reality, it could potentially allow for the transfer of information, or even particles, across these alternate worlds. The challenges, however, are enormous. We would need an intricate understanding of how quantum states are connected across universes and a way to maintain the delicate entanglement over vast cosmic distances. Despite the daunting challenges, the possibilities that quantum mechanics offers are awe-inspiring. As our understanding of these phenomena deepens, we may one day unlock the ability to explore not only the universe we know, but also the vast interconnected multiverse that could exist beyond it. This profound exploration of reality, where quantum mechanics meets the cosmos, could ultimately reshape our entire understanding of existence. In the quest to understand the very fabric of our reality, the exploration of quantum entanglement opens a door to potential breakthroughs in the understanding of parallel universes. Furthermore, entangled particles may provide clues about the nature of these realities, offering a glimpse into the unknown. By examining how the states of these particles differ or correlate, we may be able to measure their outcomes and, in turn, gather data that could point to corresponding states in universes beyond our own. The idea of using quantum entanglement to explore or even communicate across different realities remains a deeply theoretical concept, fraught with enormous challenges. However, the potential is tantalizing. As our understanding of quantum mechanics advances, it paves the way for future technologies that might one day be capable of bridging these cosmic divides. The more we strive to comprehend the boundaries that separate universes, the closer we come to uncovering the profound implications of the interconnected multiverse. But as we turn our gaze to the vast stretches of space, another mystery unfolds: the cosmic voids. These vast, empty spaces between galaxies make up a significant portion of the universe's large-scale structure, stretching for tens, even hundreds of millions of light years. They represent the greatest emptiness in the cosmos, a striking contrast to the dense filaments and galaxy clusters that form the web-like distribution of matter across the universe. Contrary to their seemingly void nature, these regions are far from insignificant. Recent studies have revealed that cosmic voids play a crucial role in the evolution and dynamics of the universe. Though they lack matter, their gravitational influence is far-reaching, affecting the motion of galaxies and the distribution of dark matter. As galaxies traverse the cosmos, they tend to cluster along the edges of these voids, creating boundaries that define the structure of our universe. Through careful observation of the properties and distributions of these voids, astronomers can unlock critical insights into the forces that shaped our cosmic environment. One of the most captivating aspects of cosmic voids is their potential relationship with regions beyond our observable universe. These vast empty spaces might not just exist within the limits of our current observational horizon. they could also stretch far beyond it. As the universe continues to expand, light from distant regions has yet to reach us. This means that vast regions, filled with voids or distinct structures, might exist beyond the scope of our current instruments, forever just out of view. Furthermore, some cosmological models propose that these voids could be a critical link to the multiverse, a collection of parallel universes, each potentially governed by its own unique set of physical laws. If our universe is just one of many, the principles that govern the formation and arrangement of matter could vary significantly across realities, giving rise to entirely different patterns of voids and structures. By studying cosmic voids within our universe, researchers can glean valuable clues about the nature of regions beyond the observable universe, offering us a tantalizing glimpse into the deeper mechanics of reality itself. Within the vastness of these voids, another enigma arises: the supervoids. These colossal regions, even more expansive than typical cosmic voids, are areas of the universe that contain far fewer galaxies than the average region. Spanning hundreds of millions of light years, supervoids stand in stark contrast to the denser structures of galaxy clusters and superclusters. Their existence challenges our fundamental understanding of how matter is distributed across the cosmos, especially when considering the evolution of the universe's large-scale structure. One of the most intriguing challenges posed by supervoids lies in their implications for current cosmological theories. Models of the universe's evolution have long assumed that matter is distributed relatively uniformly, creating a cosmic structure akin to a sponge, filled with vast filaments and large voids. Yet, the discovery of supervoids suggests that enormous stretches of space may remain relatively empty, defying expectations and prompting scientists to rethink how these massive voids can form without disrupting the surrounding structures through their gravitational effects. Supervoids also bring into question the role of dark energy in the evolution of the universe. Dark energy, the mysterious force believed to be responsible for the accelerated expansion of the cosmos, could have a direct influence on these vast emptiness regions. Observations of light passing through supervoids have revealed intriguing distortions in the cosmic microwave background radiation, along with gravitational lensing effects that offer potential insights into the role dark energy plays in the evolution of cosmic structures. By studying the impact of dark energy within these supervoids, scientists may unlock crucial knowledge about the forces that drive the expansion of the universe. This research could reveal new dimensions of understanding regarding cosmic structure formation, the influence of dark energy, and the overall dynamics that govern the universe's expansion. Furthermore, the enigmatic nature of supervoids continues to challenge our fundamental understanding of physics. These vast, empty expanses of the universe, devoid of galaxies and matter, are not just mysterious in their structure, but in their potential implications for the very fabric of the cosmos. Researchers have begun to consider that supervoids could be linked to large-scale inhomogeneities in the universe, offering clues that may even point to the existence of exotic cosmic phenomena, such as anomalies or previously unknown forms of matter. These insights could revolutionize how we understand the intricate interplay between gravity, dark matter, and the fundamental forces that govern the universe. As studies into supervoids unfold, they become a fascinating lens through which we can refine our understanding of cosmic structure and formation. These investigations encourage scientists to delve deeper into the nature of void growth and the underlying principles that shape the grand expanse of the universe. The presence of supervoids suggests that the cosmic landscape may be more complex than previously imagined, far beyond mere empty space. One of the most compelling pieces of evidence of the universe's complexity comes from the cold spot found in the cosmic microwave background radiation, CMB. This mysterious region, cooler than its surroundings, was first identified through measurements taken by satellites like the Wilkinson Microwave Anisotropy Probe and the Planck spacecraft. These tools measured the faint remnants of the Big Bang, allowing scientists to explore the oldest light in the universe. What makes this cold spot particularly intriguing is its size. It spans a vast portion of the sky, far larger than expected, and defies the predictions made by standard cosmological models, which suggest a more uniform temperature across the CMB. This anomaly has led some researchers to propose an exciting, if controversial, theory that the cold spot could be a remnant of a collision between our universe and another. According to this idea, if two universes were to collide, the resulting interaction could leave a distinct imprint on the cosmic microwave background, manifesting as a localized temperature anomaly like the cold spot. This hypothesis, if proven, would suggest that our universe might not be a solitary entity at all. Instead, it could be part of a vast multiverse, where countless other realities coexist alongside our own. But the multiverse theory is not the only explanation. Other hypotheses propose that the cold spot might be the result of large-scale cosmic phenomena, structures that formed during the evolution of the universe. Another suggestion is that the gravitational influence of supervoids, those vast regions of empty space, could cause this anomaly by distorting the fabric of space-time. Some scientists even consider the possibility that the cold spot is not an actual anomaly at all, but rather the result of systematic measurement errors or the interference of emissions from our own galaxy. While the true nature of the cold spot remains an open question, it serves as a striking reminder of the complexity and mystery that lie at the heart of cosmology. As researchers continue to probe this intriguing phenomenon, the cold spot offers tantalizing clues about the universe's fundamental nature. It challenges our understanding of the cosmos and hints at possibilities far beyond our current grasp, perhaps even suggesting that the reality we know is just a small piece of a much larger, interconnected cosmic landscape. Cosmic voids themselves, with their eerie emptiness and lower-than-average densities, have captured the fascination of scientists and physicists alike. These voids, often thought of as mere empty regions, may hold the key to understanding some of the deepest questions about the universe, including the potential existence of other realities. In the context of multiverse theories, cosmic voids might serve as portals or gateways to parallel universes, opening up the possibility that there are other realms beyond our own. The unique gravitational effects of voids could play a crucial role in these theories. Because voids are so underpopulated, their influence on space-time differs greatly from that of denser regions filled with galaxies. This warped space-time could, in theory, create pathways through which we might be able to observe or even interact with other universes. If these universes exist, with properties distinct from our own, the gravitational pull from the voids might allow their fields to interact with our universe, potentially leading to observable effects. Moreover, the very concept of cosmic voids aligns with current theories about the expansion of the universe and the formation of its structure. These theories often predict the existence of other dimensions or universes, each with their own unique properties and laws of physics. Some physicists speculate that voids with their vast emptiness might be the boundary markers between our universe and others. In this scenario, the voids could represent regions where the fabric of reality itself is less dense or differently configured, offering hints of alternate, perhaps more exotic realms that are intrinsically connected to our own. As our understanding of these cosmic voids deepens, we may find that the empty spaces of the universe are not as empty as they seem. Instead, they could be filled with hidden connections to other realities, offering a glimpse into a broader, if more complex, cosmic tapestry. The study of these vast, unexplored regions might hold the key to unraveling some of the universe's most profound mysteries, offering us new insights into the true nature of existence itself. The study of cosmic voids, those vast expanses of seemingly empty space between galaxies, offers an exciting opportunity to unravel some of the deepest mysteries of the universe. While they may appear to be barren and void of matter, these regions could be far more significant than we once thought. By probing the secrets of these cosmic gaps, scientists may uncover crucial insights into the fundamental structure of space-time itself. If these voids are linked to hidden dimensions or realms, they might hold the key to understanding the intricate forces that shape the evolution of matter throughout the cosmos. Such discoveries could ignite groundbreaking theories, potentially opening doors to entirely new realms of scientific exploration. Concepts like interdimensional interaction, reminiscent of quantum entanglement, might take center stage, providing a bridge between alternate realities. This is where cosmic voids may hold their true power, not merely as empty space, but as potential gateways into a broader multiverse. A world of possibilities awaits, and each new piece of the cosmic puzzle brings us one step closer to uncovering its deeper truths. As we venture into the study of these enigmatic voids, our very understanding of the universe could be dramatically reshaped. These discoveries could challenge existing notions, encouraging scientists to rethink what they know about reality itself. How might the voids influence cosmic dynamics? Could these empty spaces serve as the backdrop for interactions between different realities? These questions stretch the boundaries of our current comprehension, inviting us to embrace new ways of thinking and exploring. To investigate cosmic voids, astronomers employ a range of sophisticated techniques. By observing the large-scale distribution of galaxies across the sky, they can trace the patterns of voids that scatter the universe. Surveys like the Sloan Digital Sky Survey provide rich data sets, mapping the positions and redshifts of galaxies. This information allows researchers to identify voids by analyzing regions with lower galaxy density and to better understand their size, shape, and behavior. Another critical tool in the Cosmic Void Detective Kit is gravitational lensing, a phenomenon that occurs when mass, such as galaxies or dark matter, distorts the light emitted by more distant objects. In regions of space where gravitational influence is weaker, like the voids, the light from distant sources is less affected. By examining these distortions, scientists can infer the distribution of unseen matter, dark matter, and gain a deeper understanding of the void's impact on the surrounding cosmos. Gravitational lensing offers a fascinating window into the universe's most elusive structures and gives clues about the underlying forces shaping the universe. The cosmic microwave background radiation, a faint glow left over from the Big Bang, serves as yet another key tool for investigating cosmic voids. Temperature fluctuations in this ancient radiation can reveal the ways in which large-scale structures, including voids, influence the early universe. By analyzing these variations, researchers can begin to understand the formation and evolution of cosmic voids and their role in the expansion of the universe. This technique is particularly useful for exploring how voids are linked to the broader cosmic web, a delicate network of galaxy clusters and filaments that make up the universe's large-scale structure. Simulations and computer models are also integral to the study of cosmic voids. These sophisticated tools allow scientists to simulate the evolution of the universe under different conditions and to predict how voids will form and evolve over time. By comparing the results of these models with actual observational data, researchers can refine their understanding of the dynamics of voids, helping to uncover how they influence the larger cosmic structure. These simulations provide a deeper insight into the fundamental processes that govern the formation of galaxies, dark matter, and other cosmic phenomena. The combination of these advanced observational techniques is pushing the boundaries of our understanding of cosmic voids. Not only are they helping to expand our knowledge of these enigmatic regions, but they are also shedding light on the fundamental processes that shape the universe as a whole. By uncovering the hidden nature of voids, scientists are unlocking new avenues of research that could lead to revolutionary discoveries about the cosmos and our place within it. Beyond our observable universe, the concept of time itself becomes even more enigmatic. In the familiar cosmos, time flows consistently, shaped by the curvature and expansion of space-time as described by Einstein's theory of general relativity. But as we consider regions beyond the limits of our observation, the very nature of time may change. It is possible that, as we move further from the observable universe, variations in gravitational fields and cosmic structures could cause time to behave differently. One possibility that arises from these considerations is the phenomenon of time dilation. In regions with stronger gravitational fields, time passes more slowly, a concept confirmed by experiments within our own universe. Could this effect be amplified in areas beyond our sight? Is it possible that time flows at different rates in distant, unseen corners of the cosmos? In the absence of empirical data from these remote regions, These questions remain speculative, yet they highlight the profound challenges and mysteries that lie at the heart of cosmological research. As we look further into the void, we are left to wonder, what lies beyond the boundaries of our understanding? Could the fabric of space-time itself be more fluid and dynamic than we ever imagined? And what secrets might be waiting to be uncovered in these dark, silent regions of the universe? Only time and our growing body of scientific knowledge will tell. The concepts of cosmic inflation and the multiverse theory introduce groundbreaking ideas that challenge our understanding of the universe. These theories suggest that the very fabric of space-time may not be as continuous and unified as we once thought. If our universe underwent a rapid period of inflation shortly after the Big Bang, it could indicate the existence of other regions of space-time that are possibly disconnected from our own, each harboring its own unique timeline. These regions could operate under entirely different temporal rules, raising profound questions about how events unfold independently of our universe's timeline. Interestingly, quantum mechanics provides hints that time itself may not behave as we expect. In interpretations involving quantum entanglement or superposition, time seems to lose its rigid structure, suggesting that in certain conditions, it could behave in non-classical ways. This raises the possibility that time, as we know it, might dissolve into a more fluid or unpredictable entity, one that could function very differently beyond the observable universe. If these principles extend to distant regions of space, we could be faced with a reality where the flow of time is no longer linear or universal, opening up new realms of thought in both cosmology and theoretical physics. As we explore the potential variations of time in far-off regions of the cosmos, we expand not only our understanding of cosmological principles, but also the boundaries of what we can theorize about the universe. The pursuit of these mysteries could reveal profound insights that reshape our very comprehension of time, its universality, and the very structure of reality itself. In essence, the more we question, the closer we come to discovering new dimensions of existence. One such phenomenon that adds depth to our exploration of space and time is causal disconnection, a concept grounded in the framework of relativity. Causal disconnection occurs when certain regions of space become isolated, unable to interact or communicate with each other. This isolation is due to the finite speed of light, which sets a fundamental limit on the rate at which information or influence can travel. When two areas become causally disconnected, events in one region cannot affect or be observed in the other, because any signal or light emitted would take longer than the age of the universe to bridge the gap between them. This principle plays a crucial role in shaping our understanding of the observable universe. Defined as a spherical region centered around us, it extends outward to the farthest distance that light has traveled since the Big Bang, about 13.8 billion years ago. Beyond this boundary lies a vast expanse of space that remains unobservable to us, as the light or signals from those regions have yet to reach our instruments. These regions, forever out of reach, are causally disconnected from our observable universe. As the universe continues to expand, galaxies and other cosmic structures may move beyond our observational limits. This phenomenon occurs because the expansion of space itself can cause objects to recede faster than the speed of light, taking them beyond our capacity to observe or interact with them. This process highlights a startling reality. Vast sectors of the cosmos may remain forever out of sight, hidden from us by the stretching fabric of space. The concept of causal disconnection has profound implications for how we understand the universe's structure and the nature of reality itself. It suggests that there may be entire regions of space, regions that we can never observe, that operate under entirely different physical laws or conditions, rendering them permanently beyond our reach. These unobservable areas deepen the mystery of the cosmos and our place within it. The idea of closed time-like curves, CTCs, introduces another fascinating possibility, one that arises from the equations of general relativity. CTCs describe paths through space-time that loop back on themselves, theoretically allowing an object or observer to return to an earlier point in time. While our universe appears to follow the conventional flow of time, the existence of CTCs invites us to speculate about how they might manifest in other regions of space or in different universes altogether. A key theory that involves CTCs is the concept of wormholes, hypothetical tunnels through space-time that could connect distant points in space and time. If such a wormhole were traversable, it might allow an object to travel back to an earlier moment in time, thereby creating a closed time-like curve. Although there is no empirical evidence to support the existence of wormholes, the mathematics of general relativity suggest that such structures are theoretically possible. They could represent regions of space-time configured in a way that permits time loops to occur. In addition to wormholes, certain cosmological models, such as those involving rotating black holes, known as Kerr black holes, could also give rise to closed time-like curves. The space-time geometry around these rotating black holes is so extreme that it may create conditions where time loops occur, allowing for the possibility of returning to a prior moment in time. The intense gravitational influence and curvature near these black holes could make time behave in ways that are radically different from what we experience in the everyday universe. Exploring the existence of CTCs also leads to intriguing questions about parallel universes or multiverse theories. If multiple universes exist, each with its own distinct set of physical laws and configurations, it's conceivable that some could support the formation of CTCs while others do not. This diversity could produce entirely different temporal landscapes across the cosmos, each with its own rules and behaviors, further challenging our understanding of causality and the linear progression of time. While the concept of closed time-like curves invites speculation about the possibility of time travel and the structure of reality itself, it also prompts deeper inquiry into the very fabric of space-time. As scientists continue to probe the boundaries of theoretical physics, the search for evidence supporting or disproving these ideas could expand our understanding of the universe in ways we have only just begun to imagine. What these discoveries might ultimately reveal is a universe far more complex and mysterious than we could ever have anticipated. In the vast expanse of the cosmos, beyond the limitations of our own time and space, lies a tantalizing possibility: the existence of baby universes. These hypothetical miniature realms of space-time could be birthed within the boundaries of our own universe, emerging as separate entities that grow and evolve independently, governed by their own unique laws of physics. The idea that new universes might form as offshoots of our own is a captivating concept, particularly within the context of modern cosmological theories such as inflation, black holes, and the multiverse. The formation of baby universes could be linked to the incredible, rapid expansion of space that occurred shortly after the Big Bang, a phenomenon known as cosmic inflation. During this brief yet extraordinary period, fluctuations in the density of energy within space might have caused regions to undergo an accelerated inflationary process. In these localized pockets, inflation could continue unabated, giving rise to distinct, smaller universes that detach from the parent universe. Over time, these baby universes would expand and evolve on their own, developing characteristics and physical properties shaped by the same laws that govern our own universe, yet different in their specific manifestations. In addition to cosmic inflation, black holes present another intriguing avenue for the formation of baby universes. Within the singularity of a black hole, space-time itself behaves in ways that are incomprehensible to our current understanding. The intense gravitational forces at play might create conditions in which an entirely new universe could emerge, one that is fundamentally separate from our observable universe. In this scenario, the matter and energy drawn into a black hole might be channeled into the creation of a new realm of existence, completely isolated from ours. This idea offers a possible explanation for the seemingly impenetrable nature of black holes. They could be the gateways to entirely new, independent universes, where the physical laws we are familiar with may no longer apply. This concept ties seamlessly into the broader framework of multiverse theories, which propose that our universe is just one of countless others. In such a model, baby universes would be the natural byproduct of cosmic evolution, continuously forming and detaching from one another. Each of these universes could bear the imprint of the original universe, carrying its basic physical laws and constants, but they would evolve in their own directions, leading to potentially very different forms of existence. Some universes might develop distinct physical laws, varying constants of nature, or even alternative forms of life. While the notion of baby universes remains largely speculative, it challenges our fundamental understanding of reality and invites deeper exploration of the cosmos. As scientists continue to probe the mysteries of the universe, the mechanisms behind the formation of these miniature universes could reveal profound insights into the very nature of existence itself, opening the door to a broader understanding of the interconnectedness of all things in the vast, infinite expanse of space. One of the most profound implications of this exploration is the concept of the arrow of time. Time, as we experience it, flows in one direction, from the past to the future, an unidirectional progression that is intrinsically tied to the second law of thermodynamics. According to this law, in any isolated system, entropy or disorder naturally increases over time, creating a consistent forward flow. But when we consider the idea of a multiverse, the arrow of time becomes a much more complex and intriguing concept. Each universe in the multiverse may experience its own distinct flow of time, governed by its unique initial conditions and physical properties. In our own universe, time moves in a predictable direction, driven by the relentless increase of entropy as the universe continues to expand. However, in other universes, the arrow of time may take on entirely different forms. Some universes might experience time flowing in reverse, while others could exhibit complex temporal behaviors shaped by their own unique histories. The distribution of matter and energy, the nature of cosmological events like inflation or collapse, and the thermal history of each universe could all influence how time behaves in that particular realm. These variations in the arrow of time have profound implications for the evolution of each universe. The way in which time flows affects the formation of structures, how galaxies, stars, and planets arise, and how life, if it exists, develops and evolves. In some universes, the passage of time could lead to conditions where life forms evolve in ways we cannot yet imagine, shaped by the unique flow of time and distinct physical laws governing that universe. The idea of multiple independently evolving universes, each with its own distinct arrow of time, challenges our most basic assumptions about the nature of time, existence, and reality itself. It opens up a whole new realm of possibilities, encouraging us to rethink the very fabric of the cosmos and consider the astonishing potential for diverse forms of existence beyond the boundaries of our observable universe. As scientists continue to delve into these theories, the pursuit of understanding the birth and evolution of baby universes will likely remain one of the most profound frontiers in modern cosmology, offering a window into the unimaginable complexities of the multiverse and the deep mysteries of existence. The concept of the arrow of time has long fascinated scientists and philosophers alike, and when explored in the context of quantum mechanics, it opens the door to even more intriguing possibilities. In certain interpretations, such as the many worlds interpretation, the branching of realities is influenced by quantum events and superpositions. Here, each quantum measurement creates its own distinct reality, a branch where time might move differently depending on the outcome of the quantum interaction. Each branch, in this view, carries its own unique arrow of time, diverging from the others in ways that underscore a deep connection between the directionality of time and the unfolding of quantum events. This idea has profound implications for both the macroscopic and microscopic realms, linking the flow of time across different universes, each with its own particular set of circumstances. In fact, this branching of realities could point to the interconnected nature of time, extending its influence across an intricate network of universes, each shaped by its own quantum choices. The fundamental relationship between time and the structure of multiple universes calls for a deeper exploration of reality itself. As researchers delve into this fascinating realm, they grapple with some of the most profound and complex questions about time, existence, and what might lie beyond our own universe. In cosmology, a similarly captivating phenomenon known as dark flow has caught the attention of researchers. This refers to the unexpected large-scale motion of galaxy clusters in a particular direction, something that challenges the conventional models of the universe's expansion. First identified through careful measurements of the cosmic microwave background radiation, Dark flow became apparent when clusters of galaxies were found to be moving in a way that defied the expected uniform expansion. Instead of simply receding in all directions as the universe itself expands, these galaxy clusters seem to be experiencing a gravitational pull from some unseen force, something beyond the boundaries of our observable universe. The most plausible explanation for dark flow is the presence of massive structures that exist beyond the observable cosmos. These structures, possibly vast galaxy clusters or superclusters, could emit gravitational forces strong enough to influence the motion of galaxy clusters within our view. Because these regions are beyond our observational reach, their existence remains hidden from direct detection. Yet, the gravitational effects we can observe through dark flow provide a vital clue, hinting at what might lie in the universe's farthest reaches. The implications of dark flow are vast, especially when considering the possibility of a multiverse. If these gravitational anomalies are caused by structures outside our observable universe, it raises profound questions about the very nature of the cosmos. Could these unseen forces be the result of interactions with other universes? Might there be a shared cosmic environment, one with different laws of physics, densities, or other fundamental properties? Such interactions could provide an explanation for the large-scale motion we observe and could offer deeper insights into the overall topology of the universe. As scientists continue to investigate dark flow, they are not only exploring an intriguing anomaly, but also challenging our understanding of cosmic dynamics. This phenomenon underscores the need for more sophisticated methods to study the large-scale structure of the universe, particularly the gravitational forces that shape galaxy clusters. With continued research and more data, dark flow could reveal critical information about the cosmic landscape, potentially shedding light on the enigmatic forces that govern our universe and those that lie beyond our current horizon. Large-scale structures, like galaxy filaments and walls, are vital for understanding the universe, especially in relation to the boundaries of what we can observe. These cosmic structures form an intricate web composed of galaxies, dark matter, and other forms of matter, all interconnected by gravity. Over billions of years, the gravitational attraction of matter has caused galaxies to clump together, creating regions of high density, while vast voids remain largely empty. The study of these structures, especially their relationship to the limits of the observable universe, provides insight into the architecture and evolution of the cosmos. Within the observable universe, galaxy filaments are the long, thread-like structures that weave through space, often stretching across hundreds of millions of light years. These filaments connect clusters of galaxies, forming a vast network that reveals the distribution of cosmic matter. Galaxy walls, by contrast, are enormous flat structures that represent the densest regions of the cosmic web. These walls act as the boundaries where galaxy clusters group together in vast agglomerations. But here's where it gets even more intriguing. As we peer deeper into space, we encounter a limit to our observations. The observable universe is defined by the distance that light has had time to travel since the Big Bang. Beyond this, there are regions of space that remain invisible to us due to the limitations of our instruments and the finite speed of light. Consequently, large-scale structures like galaxy filaments and walls may exist beyond our current observational reach, creating a cosmic boundary that defines what we can and cannot see. This limitation in our perception of the universe has profound implications for our understanding of the cosmos. The visible universe might only be a fraction of the entire structure that surrounds us. Could there be even larger or entirely different forms of cosmic organization in the unobservable parts of the universe? And what might the patterns we observe in the visible universe tell us about the hidden regions that remain beyond our current sight? The relationship between large-scale structures and the boundaries of the observable universe sparks a wealth of possibilities about the nature of reality itself. Some theories suggest that these unseen regions could hold answers to fundamental questions about the very makeup of the universe. Are there similar structures out there, or are there entirely different types of arrangements beyond our detection? As our observational tools advance, we may soon push the limits of what we know. gaining new insights into the true nature of the universe and perhaps discovering the existence of entirely new cosmic structures that lie just beyond our grasp. In the vast expanse of the universe where mysteries abound, one enigma stands out: the axis of evil in cosmology. This term refers to an unexpected alignment found within the cosmic microwave background, CMB, radiation data, a key relic of the early universe. The discovery, made through the analysis of angular structures in the CMB, suggests that large-scale features in the universe may possess a surprising directional bias. Specifically, this axis seems to point toward a particular region in the sky, raising profound questions about the nature of the cosmos. Does the universe truly adhere to the principle of isotropy, the idea that it should appear the same in all directions on a large scale? Or is there something deeper at play? At the heart of this discovery is the challenge to a fundamental assumption of cosmology, that the universe is both homogeneous and isotropic. If the universe were perfectly isotropic, the cosmic microwave background should display uniform properties regardless of our vantage point. However, the alignment of temperature fluctuations and the peculiar orientation of large-scale structures along this axis of evil suggest otherwise. The observations point toward an underlying asymmetry that defies the conventional understanding of the universe. Various theories have been proposed to explain this anomaly. Some scientists argue that the alignment could be the result of statistical flukes, or that our view of the universe is somehow tainted by foreground contamination from within our own galaxy. But what if the explanation is more profound? Could the axis be a signal of previously undiscovered cosmic structures, or perhaps even interactions with regions beyond our observable universe? The possibility that the universe's large-scale structure is influenced by phenomena hidden from our view invites bold new questions about what lies beyond the cosmic horizon. If the axis of evil is not just an anomaly, but a true feature of the cosmos, it could force a major reevaluation of our understanding of cosmic expansion, the formation of structures, and the very nature of the universe. Such a discovery would reverberate through fundamental physics, potentially altering our understanding of dark energy, gravity, and even suggesting that the multiverse theory, where local anisotropies could emerge from interactions with parallel universes, might hold some truth. As scientists continue to investigate the axis of evil, the implications of this strange alignment continue to fuel vigorous debates. New data and refined measurement techniques will undoubtedly shed more light on the phenomenon, offering insights that may confirm or challenge the current cosmological models. What we learn could lead to breakthroughs in our understanding of the universe's structure, dynamics, and the fundamental laws that govern its behavior. Meanwhile, a new frontier of exploration is unfolding in the detection of gravitational waves, ripples in the fabric of space-time caused by some of the most energetic events in the universe. These waves, produced by cataclysmic events like black hole mergers or neutron star collisions, offer scientists a novel way to probe the cosmos, bypassing the limitations of traditional electromagnetic observations, such as light. Gravitational waves provide an unprecedented opportunity to study phenomena that occur in regions far beyond our observational reach, revealing information about distant cosmic events that would otherwise be hidden from view. Because gravitational waves travel at the speed of light and are less influenced by matter than electromagnetic radiation, they can carry data from parts of the universe that are otherwise obscured. For instance, gravitational waves generated by black hole mergers might originate in areas of space beyond our observational capabilities, allowing us to gain indirect insight into events occurring outside the observable universe. The characteristics of the gravitational waves, such as their frequency, amplitude, and waveform, offer additional clues about the sources of these waves, revealing the mass and energy dynamics of the colliding bodies. The potential for gravitational waves to deepen our understanding of the universe is immense. If we were to detect waves from events connected to the early universe, such as primordial black holes or processes related to cosmic inflation, it would mark a monumental leap in our knowledge. These signals could provide crucial information about the conditions that shape the cosmos, allowing us to glimpse regions that have since moved beyond the limits of our visible universe. As the scientific community continues to refine its tools and methods for detecting gravitational waves, we stand on the brink of an era where previously unreachable corners of the cosmos may come into view. This opens up exciting possibilities for understanding the universe's origins, its evolution, and the hidden forces that shape its fate. Gravitational waves, subtle ripples in the fabric of space-time, may be the key to unlocking some of the universe's deepest secrets. These waves, which travel at the speed of light, could reveal more than just the cataclysmic events like black hole mergers. They may hold the answers to some of the most profound mysteries of the cosmos, specifically the elusive and enigmatic forces of dark matter and dark energy. Dark matter and dark energy are invisible components that influence the universe's large-scale structure, but their nature remains a mystery, hidden from conventional observational tools. The beauty of gravitational waves lies in their potential to illuminate these unseen forces. As researchers continue to probe the ways in which gravitational waves interact with dark matter and dark energy, they could gain unprecedented insights into how these unseen forces shape the universe. This emerging field of gravitational wave astronomy is on the verge of a revolution. As detection methods improve, scientists are uncovering new phenomena, venturing deeper into cosmic regions once considered beyond our reach. The implications are profound. We may soon be able to peer into the farthest corners of the universe, revealing a rich tapestry of discoveries that could radically alter our understanding of both cosmic history and the very nature of existence itself. At the heart of this cosmic mystery is dark matter, a strange and invisible substance that constitutes about 27% of the universe's total mass and energy. It doesn't interact with electromagnetic forces like ordinary matter, which is why we cannot see it directly. Instead, dark matter reveals itself through its gravitational effects on galaxies and large-scale cosmic structures. But dark matter's role extends beyond our observable universe. In the context of the multiverse theory, some scientists speculate that dark matter could be the key to connecting different universes. If there are multiple universes, each governed by its own physical laws or dimensions, dark matter may manifest differently across these realities. For instance, certain forms of dark matter might interact with the very fabric of space-time in unique ways, creating pathways or distortions that could connect our universe to others. Such interactions, though invisible to us, might still leave traces detectable through gravitational waves. These faint signals could offer rare glimpses of universes far beyond our own. In a similar vein, dark matter's influence on the formation of galaxies and cosmic structures could provide clues about how other universes might evolve under different physical laws. If the properties of dark matter vary across different realities, it could result in divergent evolutionary paths for galaxies and other large-scale structures. The study of dark matter, therefore, holds the potential to bridge some of the most fundamental gaps in physics. The possibility that dark matter might involve quantum effects could suggest a more intricate web of interactions between dimensions or even entire realms beyond our universe. It might even offer a glimpse into hidden dimensions or realities, as posited by some models of particle physics. As scientists continue to explore the strange properties of dark matter, they are not only pushing the boundaries of our understanding of the cosmos, but also raising questions about the very nature of existence itself. If dark matter could connect our universe to others, it might offer answers to questions that have long remained beyond the reach of science. Meanwhile, the study of quantum gravity continues to challenge our understanding of reality. Quantum gravity seeks to unite the principles of quantum mechanics, which govern the tiny world of particles, with general relativity, which describes the massive forces at play in the cosmos. One of the most exciting prospects of quantum gravity is its potential to reveal the true nature of spacetime. Theoretical frameworks such as string theory and loop quantum gravity suggest that spacetime is not a continuous, unbroken entity as we perceive it, but is instead made up of discrete elements or fundamental strings. This perspective opens the door to the possibility that our universe might be part of a much larger, more intricate structure. In regions beyond our observational limits, the very geometry of spacetime could take on properties we can hardly imagine. Such theories could offer new insights into how other dimensions or even other universes might interact with our own. As we peel back the layers of the cosmic onion, we may uncover a complexity to reality that transcends everything we've known so far. Ultimately, the search for dark matter and the study of quantum gravity are not just academic pursuits. They are voyages into the very heart of existence itself. By exploring the foundations of space-time, gravity, and the unseen forces that govern the universe, we are embarking on a journey that could reshape our understanding of the cosmos, from the smallest quantum particles to the grandest structures across the multiverse. Through this, we may find that the boundaries of our universe are far less rigid than we ever imagined, with the potential for a far greater interconnected reality lying just beyond our perception. When it comes to the intricate and mind-bending domain of quantum gravity, a new horizon of understanding begins to unfold. Quantum gravity holds the potential to illuminate some of the most profound mysteries of the universe, especially in the realm of black holes and singularities. In these enigmatic regions, matter collapses into points of infinite density, and the familiar laws of physics break down. This creates extreme conditions that challenge everything we know about time, space, and reality itself. Exploring these extreme environments could unlock crucial insights into the very fabric of the cosmos, particularly regarding the informational structure of black holes. These celestial giants, far from being mere cosmic anomalies, could act as conduits or even portals to other regions of the universe, or perhaps even other universes altogether. This idea hints at the possibility that information, far from being lost in these dark abysses, could be preserved and potentially transferred across the vast stretches of space-time, connecting disparate realities through gravitational interactions. Such discoveries would mark a significant turning point in our understanding of the universe, suggesting that black holes may not be the ultimate endpoints, but rather bridges to unknown realms. This also raises tantalizing possibilities about how information might never truly be destroyed, a concept that defies traditional notions of entropy and suggests a deeper, more interconnected reality at play. As research progresses, the implications of quantum gravity may extend beyond the study of black holes, offering new paradigms for understanding the cosmos itself. Quantum gravity could revolutionize our understanding of cosmic phenomena such as the Big Bang and the enigmatic period of cosmic inflation. If we develop a deeper theory of quantum gravity that accurately models the early universe's dynamic processes, it could offer profound insights into how space-time itself emerged from nothingness. This may even point toward the existence of other universes, all part of a vast multiverse framework, each universe forming from its own unique set of conditions. Such revelations could reshape our conception of the universe's expansion, evolution, and the underlying forces that govern it. As researchers continue to delve into quantum gravity's potential, they are uncovering a treasure trove of knowledge that not only illuminates the universe we live in, but also expands our understanding of what lies beyond its observable boundaries. By pushing the frontiers of human knowledge, these investigations are opening up entirely new realms of discovery, providing glimpses into realms that were once purely speculative or unimaginable. This leads us to the captivating idea of the multiverse, which has emerged primarily from string theory and cosmological models. The theory proposes that our universe is merely one of an innumerable set of universes, each with its own distinct set of physical laws and constants. In this vast multiverse landscape, the structure of each universe is dictated by different vacuum states, each corresponding to a unique configuration of fundamental parameters. These varied configurations could give rise to a multitude of universes with dramatically different properties, ranging from alternative versions of physical forces to entirely different dimensional structures. Researchers exploring this multiverse landscape employ a range of theoretical and computational tools to probe its intricacies. One of the key methods involves delving into the mathematical frameworks of string theory, which predicts a multitude of possible solutions, each corresponding to a different vacuum state. By studying these solutions, scientists can explore the potential physical characteristics of different universes and the observable consequences that might arise in each. The mathematical complexity of string theory allows them to make predictions that extend beyond our current understanding of physics, offering new ways to interpret the universe and its possibilities. In addition to theoretical approaches, cosmological and astrophysical observations are crucial in testing the validity of multiverse hypotheses. For instance, anomalies detected in the cosmic microwave background radiation or irregularities in the large-scale structure of the universe could offer indirect evidence that other universes exist and may have interacted with our own. Scientists carefully scrutinize these observational data to identify patterns that might provide further validation of the multiverse theory, searching for traces that hint at the existence of a grander cosmic framework. Moreover, numerical simulations play an indispensable role in unraveling the multiverse landscape. By constructing sophisticated computational models, researchers can simulate the evolution of the cosmos under different sets of parameters, effectively creating a virtual universe. These simulations allow scientists to explore how variations in physical constants, forces, and initial conditions could shape the structure of space-time, galaxy formation, and even the behavior of subatomic particles. Comparing the outcomes of these simulations with real observational data helps researchers refine their models and offers crucial insights into the possibility of other universes beyond our own. Through these multifaceted approaches, scientists are gradually peeling back the layers of the universe's most profound mysteries, advancing our knowledge of quantum gravity and the multiverse. What they are discovering has the potential to rewrite our understanding of the cosmos, revealing a reality far more intricate, interconnected, and expansive than we have ever imagined. In the ongoing exploration of the universe, discussions around the implications of fine-tuning and the anthropic principle hold profound significance, especially when considered within the framework of the multiverse landscape. The anthropic principle proposes a compelling idea. The physical constants we observe in our universe are not the result of random chance, but rather are finely tuned to support the existence of observers like us. This idea introduces an intriguing dimension to the study of the cosmos, suggesting that the very nature of our universe might be shaped by conditions that allow for life to emerge, while other potential universes may remain inhospitable. This perspective opens up crucial discussions about why certain conditions seem to favor the emergence of life in some universes, while others may lack the necessary qualities for such existence. The anthropic principle provides researchers with a powerful lens to examine the multiverse landscape, an expansive theoretical framework that stretches beyond the boundaries of our current understanding of reality. It pushes the limits of theoretical physics and invites exploration into the fundamental nature of existence itself. As our scientific methods and technologies continue to advance, the study of the multiverse may reveal deeper, interconnected truths about the nature of the cosmos, enriching our knowledge of the universe and our place within it. Looking to the future, space-based telescopes and observatories offer immense potential for expanding our understanding of the universe's boundaries in profound ways. By positioning advanced instruments outside the distortions of Earth's atmosphere, scientists can eliminate many of the obstacles that currently limit our observations, such as atmospheric interference and light pollution. These technologies promise to offer a clearer, more detailed view of distant cosmic phenomena, allowing us to observe the universe across a broader range of wavelengths. Such advancements will dramatically enhance our ability to probe the intricate structure of the cosmos and extend our observations far beyond the limits of what we can see today. One of the most exciting areas of exploration for future space-based observatories lies in the study of distant galaxies and the large-scale structure of the universe. Instruments capable of capturing infrared, ultraviolet, and even submillimeter wavelengths will give astronomers the ability to detect light from the very first stars and galaxies that formed after the Big Bang. This could lead to groundbreaking discoveries that trace the evolution of the universe, providing deeper insights into its expansion history and the formation of cosmic structures that lie at the farthest reaches of our observable universe. Moreover, space telescopes will also play a pivotal role in the study of some of the most enigmatic elements of the universe, dark matter, and dark energy. These invisible forces, which govern much of the cosmic dynamics, remain largely mysterious. However, advanced instruments designed to map the gravitational effects of dark matter and measure the expansion rate of the universe may offer crucial insights into these phenomena. By characterizing these elements more precisely, scientists hope to refine our models of cosmic growth and deepen our understanding of the unseen forces that shape the universe. In addition to these advancements, future observatories will also enhance our ability to detect and study gravitational waves. These ripples in spacetime produced by cataclysmic events like the merging of black holes or neutron stars offer a novel way to observe the universe. Missions such as those inspired by the Laser Interferometer Space Antenna (LISA) concept will be able to measure gravitational waves on a cosmic scale, potentially revealing high-energy events occurring far beyond our galaxy. This capability could link us to phenomena occurring in regions of space well outside our current observable limits, offering unprecedented insights into the most violent and energetic processes that shape the cosmos. Together, these advancements represent the next frontier in the search for knowledge about our universe. They are set to open new windows into the fundamental processes that govern existence, offering a deeper, more nuanced understanding of the nature of reality itself. As the study of the multiverse landscape continues to evolve and our observational technologies advance, we are poised to make discoveries that will not only reshape our understanding of the cosmos, but also redefine our place within it. Beyond merely observing the vast expanse of the known universe, space-based telescopes now offer the opportunity to probe deeper into the cosmos, unveiling secrets hidden within the fabric of reality. These powerful instruments have opened up new frontiers for understanding the universe's origins, particularly through the study of the cosmic microwave background radiation. By mapping its temperature fluctuations with unprecedented precision, we can gather critical information about the early conditions of the universe. This data could potentially reveal insights into cosmic inflation or uncover anomalies that point to structures beyond the observable limits of our current reach. As new technologies and ambitious space missions are developed, they promise to push the boundaries of human exploration. No longer content with simply gazing at distant stars, researchers are now poised to confront the most profound questions of existence. What lies at the farthest edges of the universe? What is the true nature of its vast structure? These discoveries could reshape our understanding of the cosmos, giving rise to groundbreaking theories about reality itself. The results may even lead to the discovery of connections between our universe and others beyond the grasp of our current observational capabilities. Artificial intelligence, AI, is set to play a transformative role in this next era of exploration. By advancing the development and testing of theories about what lies beyond our universe, AI is poised to revolutionize the field of cosmology. Its ability to enhance data analysis, simulations, and theoretical modeling is already proving invaluable. With astronomical data growing at an exponential rate, AI techniques offer a way to efficiently process these vast data sets, detecting patterns and uncovering insights that might otherwise remain hidden. Machine learning algorithms can be trained to identify subtle signals or anomalies within the noise of cosmic data, allowing astronomers to distinguish between true astrophysical events and spurious results. One of the most promising applications of AI lies in its ability to analyze cosmic microwave background radiation. By scanning this relic of the Big Bang for irregularities or anomalies, AI could help uncover clues about realms beyond the observable universe, sparking new investigations into the multiverse or other cosmic phenomena. Furthermore, AI can revolutionize the way complex physical systems are modeled. In the realms of cosmology and particle physics, researchers rely on computational models to simulate the behavior of matter and energy under various conditions. With the help of AI, these simulations can be optimized, enabling scientists to explore a broader array of scenarios and uncover new insights into how matter and dark energy might interact. This predictive power holds immense potential, allowing researchers to test existing theories while simultaneously generating new hypotheses about what lies beyond the observable cosmos. AI can also assist in refining theoretical frameworks by quickly evaluating the viability of competing models. By assessing how well different theories explain observed phenomena, or by generating predictions that can be tested against real-world data, AI can streamline the scientific process. It allows researchers to focus on the most promising avenues of inquiry, particularly in relation to the universe's larger structure or its potential connections to alternate realities. In addition to its technical prowess, AI's capabilities in natural language processing offer another significant benefit. As the body of scientific literature expands, AI can help synthesize vast amounts of research, identifying relevant studies, uncovering relationships between findings, and summarizing complex ideas. This ability to facilitate collaboration across disciplines is crucial for tackling the complex questions surrounding what exists beyond our universe. By fostering interdisciplinary dialogue, AI can accelerate progress in astrophysics and cosmology, enhancing our understanding of the universe's deepest mysteries. The integration of AI into these fields promises to be a game changer. As these tools continue to evolve, they will empower researchers to push the boundaries of exploration, potentially leading to breakthroughs that reshape how we perceive reality and our place within it. These advancements may reveal not just new phenomena within our own universe, but also suggest connections with realms and universes that lie beyond our current observational reach. Simultaneously, progress in particle physics, particularly through experiments conducted at cutting-edge facilities like the Large Hadron Collider, LHC, stands poised to enhance our understanding of multiple universes. The LHC allows researchers to conduct high-energy collisions that replicate the conditions present shortly after the Big Bang. This experimental approach offers insights not only into the fundamental building blocks of matter, but also into theories that posit the existence of parallel universes. The LHC's contribution to the multiverse hypothesis lies in its exploration of particles and interactions that extend beyond the well-known standard model of particle physics. Theories such as supersymmetry or string theory suggest that there may be a hidden layer of particles waiting to be discovered. Finding these elusive particles could offer evidence for extra dimensions and other energy states that may be linked to the idea of a multiverse. If phenomena like these are detected, it would provide compelling support for the notion that our universe is just one of many, interconnected in a complex, multidimensional framework. Through the combined power of space-based telescopes, artificial intelligence, and particle physics research, humanity is embarking on a new chapter in its quest to understand the cosmos. These technological advancements hold the potential to unveil new layers of reality, offering profound insights into the nature of the universe and what might lie beyond its visible borders. The exploration of the Higgs boson's properties plays a pivotal role in unraveling the mysteries of the early universe and its fundamental structure. The discovery of the Higgs boson at the Large Hadron Collider, LHC, was nothing short of monumental. It confirmed one of the Standard Model's most crucial predictions, but its full implications are far from being understood. Scientists are still probing the mechanisms of the Higgs field and its interactions with other particles. Understanding this intricate dance could be key to unlocking the secrets of cosmic inflation, the theory proposing an explosive, rapid expansion of the universe in its infancy. If cosmic inflation can be linked to a larger framework involving multiple universes, the investigation into the Higgs boson may provide a bridge to these alternate realms. High-energy particle collisions at the LHC may offer insights into how the early universe behaved under extreme conditions. In particular, phase transitions occurring in these collisions could illuminate the processes that gave rise to the formation of other universes, as suggested by certain theoretical models. According to the multiverse hypothesis, different regions of space could exist in distinct vacuum states, each generating its own universe with its own set of physical laws. Investigating particle behavior under these intense conditions might, in fact, hold the key to understanding how such cosmic bifurcations could occur. Moreover, the discoveries at the LHC are not confined solely to the early universe's origins or the multiverse. The research underway may also shed light on the most enigmatic components of the cosmos: dark matter and dark energy. These mysterious substances are thought to account for most of the universe's mass energy budget, yet their properties remain elusive. By studying their interactions and behaviors in particle collisions, scientists may be able to make significant strides in understanding how these forces work, possibly revealing connections to other universes. This could suggest that dark matter, in particular, manifests in unique ways across alternate realms, further deepening our understanding of the cosmos. In conclusion, the work being conducted at particle physics facilities like the Large Hadron Collider is crucial to expanding our knowledge of the universe's fundamental principles. As researchers decode the complex web of particle interactions, they open the door to groundbreaking revelations about the very nature of reality. Through these investigations, we are not only drawing closer to understanding the structure of our own universe, but also uncovering potential links to alternate realities, reshaping our view of the cosmos at its most profound level. The idea of our universe as a cosmic cell within a larger, living superorganism offers a compelling philosophical and scientific framework to contemplate the nature of existence. This concept suggests that our universe is not only a part of something grander, but that it also operates in ways akin to biological systems, interconnected and hierarchical. Imagining our universe as a cell within a cosmic organism raises thought-provoking questions about the nature of life, consciousness, and the very fabric of existence itself. Could it be that, just as cells are the fundamental building blocks of life, our universe serves as a fundamental unit of a larger, sentient existence? Such a perspective invites deep reflection on how the laws of physics might reflect a deeper, more purposeful order, one that unites cosmology with philosophy, offering a new lens through which we can explore the implications of purposefulness and interconnectedness in the cosmos. Furthermore, this idea opens up a fascinating avenue for exploring the interactions between different cosmic cells. Just as biological cells communicate through chemical signals or electrical impulses, different universes might interact or influence one another in ways we have yet to fully comprehend. Theories in physics, such as those addressing quantum entanglement or the concept of parallel universes, provide valuable insights that could guide this exploration. These theories suggest that there may be connections between our universe and others, hidden within a metadimensional framework that we have yet to unravel. The concept of our universe as part of a larger, living superentity presents an intriguing parallel to how biological systems maintain homeostasis and adapt to environmental changes. The properties of dark matter and dark energy, coupled with the observed acceleration of our universe's expansion, might point to an underlying mechanism of awareness or adaptation, hinting at a dynamic and evolving cosmic system. This perspective, while speculative, invites us to consider that the universe may function as an interconnected, self-regulating entity. Ultimately, while the idea of our universe as a cosmic cell within a grander living organism remains speculative, it encourages a multidisciplinary approach to the fundamental questions of existence. It challenges scientists and philosophers alike to consider the broader implications of the intricate cosmic tapestry in which we are embedded. This idea propels us toward deeper discussions on consciousness, interconnectedness, and the nature of existence itself, offering new possibilities for exploration as our understanding of the cosmos continues to evolve. Such imaginative concepts could fuel the next stage of our quest for knowledge, inspiring us to investigate the profound mysteries of life and the universe in ways we've not yet dreamed of. The metaphor of cosmic DNA, encoding the properties of different universes within a multiverse, offers a captivating framework for understanding the fundamental structures that might govern various realities. Just as DNA carries the genetic instructions that define the characteristics and functions of living organisms, this concept suggests that there may be deep underlying codes that determine the properties and laws of each universe in the multiverse. In the context of physical theories, this cosmic DNA might represent a set of variables or constants that define the unique characteristics of each universe, such as the strength of gravity, particle masses, and the nature of dark matter and dark energy. By elaborating on the rules and initial conditions encoded within this cosmic DNA, we may be able to systematically describe how universes branch off or differ from one another. One way to approach the idea of cosmic DNA is through the lens of string theory, particularly its multitude of solutions. In this framework, there are countless ways to compactify extra dimensions, with each configuration leading to its own set of physical laws and constants. Each unique compactification scheme could be considered a distinct genome, encoding the specific behavior of a corresponding universe. Consequently, the observable properties of our own universe, such as the values of physical constants, could be determined by the particular structure of our cosmic DNA. Another fascinating layer to consider is the role of quantum mechanics in shaping the concept of cosmic DNA. Certain interpretations of quantum mechanics suggest that every quantum event spawns multiple branches of reality, leading to divergent outcomes across a vast array of universes. The rules governing these quantum events and their interactions could form yet another aspect of cosmic DNA. In this view, the nature of quantum phenomena could dictate the evolution and properties of each universe in the multiverse, reinforcing the idea that our understanding of reality might be governed by deeper cosmic rules that are encoded in the very fabric of existence. The concept of cosmic DNA invites profound contemplation about the potential interactions between different universes, especially if each one encodes its own set of physical laws and unique attributes. Could there be pathways or connections that link them? Perhaps shared structure principles facilitate these bonds, echoing ideas found in theories about wormholes or higher dimensional pathways that connect multiple universes. This speculative framework suggests a far more intricate and interconnected web across the multiverse than we might typically imagine. The idea of cosmic DNA serves as a powerful metaphor for understanding the fundamental principles that could define reality across a vast expanse of universes. As researchers delve deeper into the frontiers of theoretical physics and cosmology, this notion compels us to reflect on how the laws of existence might manifest in diverse, often unimaginable ways. It casts light on the complex fabric of the cosmos, urging further exploration into the very essence of reality. Equally captivating is the idea of the expansion and contraction of universes as part of a cosmic respiration cycle. This metaphor likens the cosmos to a living, breathing entity, suggesting that universes may undergo rhythmic cycles of growth and decay, much like the inhalation and exhalation of biological organisms. In such a model, the expansion phase symbolizes a period of energy dispersal and growth, akin to the aftermath of the Big Bang. This is when galaxies stretch apart and cosmic structures evolve, a phase supported by current observations like the redshift of distant galaxies. On the other hand, the contraction phase mirrors the exhalation process, when gravitational forces take over, drawing matter back together. This stage could culminate in a big crunch, where the universe collapses into a singularity, potentially setting the stage for a new cycle. In this sense, the universe breathes in a perpetual loop, transitioning from expansion to collapse, then back again, just as air is expelled and drawn back into the lungs. The implications of cosmic respiration extend far beyond our own universe. If multiple universes exist, each following a similar cycle of expansion and contraction, it suggests that the life cycles of these realms might be interconnected. The rhythmic ebb and flow could be a characteristic shared by all universes, with the energy and properties of one cycle influencing those of others within the broader multiverse. As each universe undergoes its own unique rhythm, the resulting conditions may vary, yet they are part of a grander, unified pattern that stretches across the fabric of the multiverse itself. This captivating theory not only challenges our understanding of time and space, but also hints at the underlying unity that could exist within the most distant reaches of reality. Moreover, this model beckons us to consider the roles of dark energy and dark matter in the cosmic respiration cycle. Understanding how these enigmatic forces influence the expansion and contraction dynamics of the universe could shed light on the deeper mechanisms of its life cycle. If dark energy continues to drive the accelerated expansion we observe today, it may hold the key to determining whether the universe will one day contract or enter an entirely new phase. Ultimately, the idea of cosmic respiration serves as a compelling metaphor for the universe's evolution, hinting at the possible existence of cycles that stretch far beyond our perception. As scientists delve deeper into this concept and explore the intricate dynamics of cosmological expansion and contraction, they could uncover pathways toward answering some of the most profound questions about reality, the existence of multiple universes, and the hidden connections that could unite all forms of existence throughout the cosmos. One fascinating extension of this idea is the concept of interuniversal synapses, a framework that could illuminate how communication or energy transfer might occur between different universes within a multiverse. This metaphor borrows from biology, where synapses enable the flow of information between neurons in a complex nervous system. Just as synapses facilitate communication within the human brain, interuniversal synapses could act as channels, allowing interactions between distinct realities. The mechanism behind these interuniversal synapses may involve the existence of higher dimensions, realms that extend beyond the 3 dimensions of space we're familiar with. Theoretical models, such as string theory, suggest the possibility of additional dimensions that could serve as conduits between parallel universes. In this framework, these synapses might represent pathways or bridges that connect higher dimensional structures, facilitating the transfer of matter, information, or energy between universes. These interuniversal synapses could manifest in several ways. One possibility is through gravitational or quantum entanglement, where particles or energy fields in different universes become intertwined. If particle states are entangled across universes, events in one universe might influence corresponding states in another instantaneously, an effect that defies classical physics, but could provide a mechanism for real-time exchange or coordination across separate realities. Furthermore, the idea of interuniversal synapses might extend to the realm of exotic particles, hypothetical entities that could exist in other universes but not in our own. These particles could facilitate energy transfer between universes, perhaps enabling the sharing of resources or physical properties. Such an idea not only challenges our understanding of physics, but also invites speculation on how these interconnections could reshape our comprehension of fundamental laws across the multiverse. As we explore these interuniversal connections, new discussions may emerge around core cosmological principles, such as the conservation of energy and information. If communication or energy transfer across universes is possible, it could revolutionize our understanding of how these laws operate in a multiverse context. This fresh perspective might provide profound insights into the very nature of existence and the complex relationship between universes. In the end, the notion of interuniversal synapses offers a captivating framework for understanding the connections between universes and challenges us to reconsider how the multiverse might function. As scientific inquiry continues to push the boundaries of what we know, these ideas may inspire new models of reality, broadening our comprehension of the cosmos and the myriad interactions that occur within its many layers. Additionally, the theory that dark energy might result from our universe being consumed by a larger cosmic organism presents a strikingly imaginative way of viewing the universe's dynamics. Dark energy, currently understood as the mysterious force accelerating the expansion of the universe, accounts for roughly 70% of the universe's total energy density. This conceptualization, however, suggests that dark energy is more than just a force or constant. It may be a symptom of a much larger living entity that encompasses our universe. If we entertain the idea that our universe is part of a greater cosmic organism, it raises profound questions about what it means for one universe to engage in such a biological process. In this model, the accelerated expansion driven by dark energy might be likened to a metabolic process, where the universe is being transformed or repurposed by a larger cosmic system. As our universe expands, it could be releasing energy or information into this broader entity, becoming an integral part of a system that affects not only itself, but other universes or cosmic structures as well. This metaphorical digestion of the universe by a larger cosmic organism might also explore the relationship between different parts of the cosmic environment. Just as biological systems maintain homeostasis, this cosmic organism might oversee the balance and interaction between various universes or cosmic structures. The properties of dark energy, which influence the rate of expansion, could point to a mechanism where energy circulates or is exchanged with the greater cosmic entity, suggesting a dynamic and interdependent relationship rather than an isolated existence. In essence, this conceptual framework invites us to reimagine the universe as part of a larger, living cosmic system. By exploring how dark energy fits into this idea, we may gain new insights into the nature of cosmic forces and the profound interconnections that govern the life cycle of the cosmos itself. Furthermore, this idea could profoundly challenge our current understanding of dark energy and the fate of the universe. The very notion that our universe might be alive in some sense proposes that cosmic evolution may involve more than mere physical processes. It introduces the possibility of purpose, intentionality, or even conscious influence within the dynamics of the cosmos. If dark energy is a byproduct of a larger organism's interaction with our universe, this would suggest that the universe's expansion could be part of a grander cosmic strategy, one aimed at fostering growth, evolution, or maintaining balance within a larger cosmic ecosystem. Such a perspective shifts the discussion from the purely physical to something far more intricate, where the universe's very existence could be viewed as a dynamic and purposeful event. While the idea of our universe being digested by a larger cosmic organism remains speculative, it serves as a springboard for rich philosophical and scientific debates about the nature of existence itself. It challenges us to rethink our understanding of life, energy, and their relationship to the universe. What if biology and cosmology share deep connections at levels we have yet to discover? Could there be an underlying unity that ties together the mechanisms of life with the forces shaping the cosmos? As scientists continue to probe the mysteries of dark energy and the structure of the universe, they may stumble upon insights that bridge these imaginative concepts with rigorous scientific investigation. This could vastly expand our comprehension of the universe and illuminate our place within it, perhaps revealing a deeper interconnectedness of all things. The concept of probability waves, deeply rooted in quantum mechanics, offers another fascinating layer to this discussion. In quantum theory, particles do not have defined positions, but rather exist as probabilities, described by wave functions. These waves stretch across both space and time, presenting a range of potential outcomes that coexist until an observation collapses the wave function into a single definite state. When we consider the boundary of our observable universe, the so-called cosmic horizon, this concept of probability waves takes on particular significance. At the edge of the known universe, where uncertainty reigns, probability waves could represent the very fabric of potential realities. They suggest that under the right conditions, new configurations of matter and energy might emerge, leading to the birth of entirely new realms of existence. This idea aligns with the theory of cosmic inflation, which postulates that tiny quantum fluctuations in the early universe sparked the vast structures we observe today. If these probability waves are capable of creating diverse regions of space, each with distinct properties, they might trigger processes that give rise to new realities, new pockets of existence where the fundamental laws of physics could take on entirely different forms. In addition to this, the theory of parallel universes gains support from the many worlds interpretation of quantum mechanics. According to this view, each quantum event creates a branching reality, where every possible outcome plays out in its own separate universe. If the edges of our universe are imbued with probability waves, the interaction and collapse of these waves could lead to the formation of new branches, giving rise to alternative realities shaped by different quantum paths. In this context, the boundary of our universe becomes a fertile ground for the creation of new worlds, each shaped by its own set of quantum events. This shift in perspective could open up entirely new realms of exploration in both cosmology and quantum mechanics, where the lines between reality, possibility, and existence itself blur into something far more intricate than we could have previously imagined. Furthermore, the dynamics of probability waves could play a pivotal role in how the various components of our universe interact with realms and structures beyond the scope of our perception. Consider this: if probability waves stretch out from the boundaries of our observable universe, They might touch upon regions that we cannot directly see or measure. These unseen areas could harbor connections that facilitate the exchange of energy, information, or even matter with realities that exist beyond our own. Such exchanges could have profound implications, possibly shaping the evolution of these distant realms. They might draw upon the foundational properties of our universe while simultaneously developing their own distinct characteristics. As researchers delve deeper into the foundational principles of quantum mechanics and cosmology, studying probability waves at the very edges of our universe could yield astonishing revelations about the complex interrelations between different realities. This line of exploration doesn't merely push the boundaries of our scientific understanding, it challenges us to rethink the very nature of reality itself. It beckons us to contemplate the profound interconnectedness of all existence, which could radically expand our view of the universe. It opens the door to a myriad of possibilities that might arise from the inherent uncertainties embedded within the fabric of the cosmos. One of the most intriguing hypotheses to arise from these explorations is the idea that our universe might be a cosmic hologram, projected from a higher dimensional reality. This hypothesis marries concepts from quantum mechanics, theoretical physics, and cosmology, forming a bridge between abstract theoretical ideas and the observable universe. The holographic principle at the core of this concept proposes that all the information contained within a region of space might be represented as a two-dimensional surface. This suggests that the three-dimensional universe we experience could, in fact, be the result of information encoded on a lower dimensional boundary. If this hypothesis holds true, it would fundamentally alter our understanding of reality. The universe we perceive, vast and three-dimensional, could merely be a projection of information residing in higher dimensions. Such a framework could reveal that the nature of reality is far more intricate and interconnected than we currently perceive. Higher dimensions could provide the scaffolding from which the phenomena of our universe emerge. This idea invites us to rethink the very fabric of existence, from the laws of physics to the constants we assume are universal. But what does it mean if our universe is merely a hologram? This perspective would suggest that the fundamental laws of physics, the ones we've long believed to be intrinsic to the fabric of reality, might be emergent properties of a deeper, more complex structure. If so, concepts like time, space, and causality might not be the absolute, unchanging pillars of reality that we've always assumed them to be. Instead, they might emerge from more fundamental principles shaped by the interactions of higher dimensional spaces. Moreover, if the holographic projection originates from a higher dimensional reality, it implies that other dimensions could be influencing the behavior of particles and forces within our universe. These dimensions could act as a bridge connecting the seemingly disparate realms of quantum mechanics and cosmic structures. This opens the door to the possibility of a unified framework where the smallest quantum particles and the largest cosmic entities are linked. It may even offer new insights into dark matter and dark energy, mysterious forces that could be the effects of higher dimensional phenomena rather than independent entities of their own. As we explore the holographic nature of the universe, we are also forced to reconsider our understanding of black holes and entropy. Notably, physicists Jacob Bekenstein and Stephen Hawking's work on black hole thermodynamics suggests that the information content of a black hole is proportional to its surface area, not its volume. This aligns with the holographic principle. This realization invites us to rethink the nature of black holes, energy, and information, and how they intersect with the broader cosmos. Could the behavior of these enigmatic objects reveal hidden dimensions of reality, further connecting the dots between the micro and macro worlds? In conclusion, contemplating the universe as a cosmic hologram projected from a higher dimensional reality challenges the very foundations of how we perceive existence. As scientists continue to explore the implications of the holographic principle, we might be on the cusp of groundbreaking discoveries. These insights could radically shift our understanding of the universe, unveiling a far more intricate tapestry of reality than we ever imagined. Another concept that stretches the boundaries of conventional physics is the idea of quantum foam and its relationship with wormholes. This concept arises from the intersection of quantum mechanics and general relativity, suggesting that at the smallest scales of space-time, specifically at the Planck scale, the universe is not smooth and continuous. Instead, it's made up of tiny, constantly fluctuating bubbles, or foam, that could give rise to transient connections or tunnels between different points in space-time. These fluctuations might even provide a potential link between our universe and others within the multiverse. At the heart of this idea lies the concept of wormholes, hypothetical passages through space-time that could connect distant regions of our universe or even entirely different universes. Quantum foam proposes that these wormholes might not be stable, permanent structures, but rather fluctuating entities that emerge momentarily due to quantum fluctuations. In essence, they might appear and disappear on incredibly small timescales, creating fleeting windows through which information, particles, or energy could be exchanged between different universes. Such interactions might be imperceptible to us, as these wormholes would exist only for brief moments, further emphasizing the probabilistic nature of quantum mechanics. If these fleeting connections exist, they could offer a glimpse into how universes might influence one another, or even hint at a more profound underlying reality where the boundaries of space and time are far more fluid and interconnected than we ever thought possible. The chaotic, fleeting nature of quantum foam could in fact harbor profound implications for the dynamics of universes that exist at the smallest, most transient scales. These connections, while ephemeral, may hold the power to influence cosmic systems during their brief moments of existence. The quantum foam wormholes are more than just theoretical constructs. They open a doorway to a deeper understanding of how information and energy travel across vast cosmic distances, potentially reshaping our comprehension of the universe itself. At the heart of this exploration lies the intriguing connection to information theory and the holographic principle, a groundbreaking idea that suggests that the structure of space-time is intricately linked to the information it contains. If this principle holds, the seemingly minute and temporary connections within the quantum foam could be key to understanding how information is transferred across the cosmos. These wormholes might offer crucial insights into the behaviors of dark matter and dark energy, two of the most mysterious components of our universe. Moreover, quantum foam wormholes might offer explanations for some of the most perplexing quantum phenomena. They bridge the gap between the macroscopic and the microscopic, suggesting that the behavior of particles may not be confined solely to the three-dimensional space we know. Instead, there could be interactions with higher dimensional structures or even neighboring universes. This opens up entirely new possibilities for the way we perceive the fundamental workings of reality. In conclusion, the notion that quantum foam wormholes could connect our universe to others at the tiniest scales is a tantalizing frontier in theoretical physics. As researchers continue to delve into the complex realms of quantum mechanics, general relativity, and the fabric of space-time itself, the exploration of these wormholes could unlock new insights into the interconnectedness of all things. This could help answer some of the deepest questions of existence, and perhaps reveal how diverse realities interact within the vast cosmic tapestry. Equally captivating is the idea that the very constants of nature, such as the gravitational constant, the speed of light, and the fine structure constant, might not be as fixed and immutable as we once believed. Instead, these fundamental constants could emerge through a cosmic evolutionary algorithm, a dynamic and ever-evolving process that mirrors the principles of natural selection and biological evolution. This concept suggests that the properties we observe in the universe today are not the result of random chance, but the outcome of an optimization process that guides the development of these constants over time. In this model, the cosmic evolutionary algorithm acts as a mechanism that tests and refines various configurations of physical constants, much like how genetic variations are tested through survival and reproduction in biological systems. The universe undergoes a continuous process of trial and error, with different combinations of constants leading to different outcomes. Those configurations that promote stability, complexity, and the conditions necessary for the emergence of structures like galaxies, stars, and life itself are selected to persist. The implications of this idea extend far beyond just the constants of nature. If the laws of physics themselves are adjustable within this algorithmic framework, it suggests that our universe might not be a static or finished product, but rather the result of an ongoing dynamic process. This could lead to an entirely new way of understanding how the fundamental forces like gravity, electromagnetism, and the strong and weak nuclear forces work together to produce the complex, ever-evolving universe we observe today. In the context of a multiverse, this evolutionary process could unfold across countless universes, each with its own unique combination of physical constants. In such a multiverse, some universes may experience evolutionary processes that are more conducive to complexity and stability, leading to the emergence of life and consciousness. Over time, the interplay of these constants could act as a cosmic filter, enhancing the likelihood that certain universes will develop the right balance of forces to support life. The notion of a cosmic evolutionary algorithm is revolutionary, offering a new lens through which to view the universe. Rather than seeing the laws of physics and the constants of nature as fixed and unchanging, this model suggests that the cosmos is in a constant state of flux and adaptation, an ever-evolving reality shaped by the interplay of fundamental forces and constants. This paradigm has the potential to unlock new avenues of exploration in the fields of quantum mechanics, cosmology, and the nature of existence itself, providing us with a deeper understanding of the dynamic processes that shape the very fabric of our universe. Furthermore, this perspective challenges our current understanding of fine-tuning, especially the apparent precision with which the constants of nature permit life and complexity to emerge. If the constants we observe are, in fact, the outcomes of a cosmic evolutionary process, it forces us to reconsider the very nature of life itself and its relationship with the cosmos. In this framework, life is no longer a passive observer of the universe. It becomes an essential factor in the evolutionary algorithm that shapes the cosmos. Life may even play a role in determining how these constants are set or modified, potentially influencing the conditions of neighboring universes. Ultimately, the idea of a cosmic evolutionary algorithm opens up an exciting and provocative avenue for exploration across the fields of cosmology, physics, and philosophy. As researchers continue to probe the foundations of the universe and the origins of the physical constants, this concept invites a deeper reflection on the interconnectedness of existence, evolution, and the mysteries of the cosmos. It could lead to groundbreaking insights into our understanding of reality, suggesting that the universe is not just a random collection of events, but a process shaped by an ongoing cosmic evolution. In parallel, the concept of reality fractals presents a fascinating framework for understanding the universe's structure. Fractals are mathematical constructs that display repeating patterns at various levels of magnification. These patterns are self-similar. Smaller sections of the fractal resemble the whole, regardless of the scale. When applied to cosmology, this idea suggests that the universe might not only display structural similarities at large scales, such as the clustering of galaxies in vast filaments, but also replicate these configurations on smaller and smaller scales, potentially leading to the idea of infinite nested universes. In this model, each universe could be viewed as a unique fractal, with its own set of physical laws and properties, yet shaped by similar underlying principles. Large-scale structures like galaxy clusters might retain features indicative of the same fundamental laws governing phenomena at much smaller scales, such as atomic structures or even subatomic particles. This notion suggests that as one zooms in on any point in the universe, they might discover structures that mirror the larger cosmic framework, creating a seamless connection between the largest and smallest scales of existence. The concept of reality fractals could also offer an intriguing explanation for the multiverse theory, which has gained traction in modern theoretical physics. If our universe is merely one iteration of a fractal pattern, then it's plausible that countless other universes exist, emerging from the same foundational principles but exhibiting distinct characteristics. Each nested universe would preserve certain aspects of the larger fractal pattern, but could diverge in crucial ways due to differences in initial conditions, physical constants, or dimensional constraints. Moreover, the idea of nested universes introduces exciting implications for our understanding of quantum mechanics and the behavior of particles. Quantum phenomena, often seen as bizarre and counterintuitive, might exhibit fractal-like behavior. This suggests that particles could interact with one another and with their environment through mechanisms that are self-similar across different scales. Such a framework would imply that the processes governing particle behavior are inherently tied to the larger cosmic structure, further blurring the lines between the micro and macro scales. In addition, reality fractals could challenge our traditional understanding of time. If the structure of the universe is governed by fractal principles, different layers of existence could experience time in unique ways. Perhaps time itself is not uniform across the cosmos, and different universes, or different regions within our own, might perceive or experience time differently. The interconnectedness of these layers could allow for extraordinary interactions, even spanning across universes, enhancing the complexity of reality and the interactions within it. In the end, the notion of reality fractals, an infinite series of nested universes, provides a powerful framework for exploring the fundamental interconnectedness of structures across various scales of existence. As scientists continue to probe the very nature of the cosmos, this concept could inspire innovative new theories and models that push the boundaries of human understanding. Such inquiries may not only reveal the true nature of our universe, but also unveil deeper truths about the very fabric of reality, fundamentally reshaping our view of the cosmos and our place within it.